May I request you all to please settle down? In a few moments from now, we'll start with our inaugural session. So I'm requesting you all to please be seated. Thank you. Thank you. Thank you.
once the session start ना हम कोशिश करेंगे टाइम से खत्म प्लीज आपके हिसाब से होगा नहीं नहीं मतलब एक टाइम उनको बोल देंगे ना अगर इनके स्लेट
हाँ ऑब्वियसली हाँ यार
क्योंकि 5:40 पे लास्ट एंड कर ऐसा ऐसा खींचेंगे ना तो 6
but it's not in our hands now depends इतने सारे स्पीकर्स
सो प्लीज कोऑर्डिनेट कुछ टाइम होगा तो
हाँ जो
मॉडरेटर
मॉडरेटर ज़्यादा और
हाँ
उसमें देते रहेंगे प्लीज़ मेरे पास सब कुछ जल्दी है भाई जल्दी आ रहा है नमस्कार वी वेलकम यू थोड़ा सा और अच्छा ठीक है श्योर श्योर थैंक यू Ladies and gentlemen, may I request you all to please be settled down. We are just about to start with our today's proceedings, so I'm requesting you all to please be seated, please settle down. Thank you. Thank you.
I've already said thrice. Thrice.
Ladies and gentlemen, as I have been told that our Secretary Sir is arriving within 2-3 minutes, so I'm requesting you all once again to please be seated. Thank you. टेक्निकल टीम वॉल्यूम प्लीज़ थोड़ा सा और लाउड कर दीजिए. I request you all to please be seated. Thank you. Namaskar, good morning, ladies and gentlemen. A very warm welcome to all of you in the second International Quantum Communication Conclave, organized by Telecommunication Engineering Center in collaboration with CDOT and TSDSI. We are deeply honored to have the gracious presence of respected Professor Ajay Kumar Suchi, Principal Scientific Advisor to Government of India, respected Dr. Neeraj Mittalji, Secretary Telecom and Chairman Digital Communication Commission, Department of Telecommunications, Dr. Subrata Rakshit, Director General, Technology Management, DRDO, and Srimati Tripti Saxena, Senior Deputy Director General and Head Telecommunication Engineering Center. We are pleased to have with us speakers, experts, officials from various departments and organizations, industries, startups, academic and research institutions. We extend a hearty welcome to all the respected guests and speakers who are joined online and all others present here in this hall. We welcome you in the second International Quantum Communication Conclave. And now to inaugurate this conclave, may I request all the esteemed dignitaries on the dais to kindly light the lamp. Please, sir. Please, ma'am, do the honors. Yesterday we celebrated Basant Panchami and we are seeking blessings of Ma Saraswati. Thank you, ma'am. Thank you, sir. And now, ladies and gentlemen, I request Ms. Bhumika Gaur, ADG Radio Tech, to kindly present a sapling to Honorable Professor Ajay Kumar Suchi. Ms. Bhumika Gaur, please. So ADG Radio Tech, Ms. Bhumika Gaur will now present a sapling and welcome Honorable Professor Ajay Kumar Suchi. I'll now request Shri Rakesh Goyal, ADET Quantum Technology TEC, to please welcome Honorable Dr. Neeraj Mittal by presenting a sapling. I now invite Ms. Namrata Singh, ADG, IoT Tech, to kindly felicitate respected Dr. Subrata Rakshit by presenting a sapling. I call upon Shri Arjun Singh, ADET, Telecom Certification, TEC, to please present a sapling to respected Srimati Tripti Saxena ji. And now for the welcome address, ladies and gentlemen, may I request Srimati Tripti Saxena ji, Senior Deputy Director General and Head Telecommunication Engineering Center. Ma'am, please.
A very good morning to all the honored guests on the dais and in the hall, distinguished experts and delegates from academia, R&D institutions, industries, startups, and various government organizations present in the person and as well as online. On behalf of the Telecom Engineering Center working under Department of Telecommunication, it's my privilege to extend a warm welcome to you all to the second International Quantum Communication Conclave. As we all know, quantum technologies are disrupting the world, promising unprecedented communicational capabilities. However, it also poses a significant threat to our communication infrastructure. It is a happy situation that a lot of work towards developing the quantum security solutions are being done by our Indian academia and its industries, with an aim to bring all the stakeholders together and promote the collaborative ecosystem. The first edition of this conclave was held in March 2023 by TEC. It is due to all your enthusiasm and encouragement and positive feedback that we are conducting the second edition of this conclave. We are truly honored by the presence of Dr. Neeraj Mittal, Secretary to Telecom, who has been the main pillar of support and guiding force for us. He is very keen that India should take a leading position in emerging technologies. He is the main inspiring power behind arranging and effectively directing this event. We truly feel energized and motivated with your esteemed presence, sir. The field of quantum communications holds immense promise, particularly in its potential to enable unbreakable encryption. In the era of quantum computing, a capability pivotal for the defense sector, I welcome Shri Rakshit from DRDO, who has spared his valuable time to come to the event and share his insights and guide us on India's journey on the quantum revolution. We are also blessed to have Professor Ajay Kumar Sood, Principal Scientific Advisor to Government of India, amongst us on this occasion, who has been instrumental in steering the National Quantum Mission. We look forward to hearing from you, sir. I believe this initiative of TEC will give an impetus to R&D and deployment of quantum technologies, and also pave the way for positioning India as a global leader in quantum technology. The role of press and media is extremely essential for positive, favorable outcome of any conclave. I extend a warm welcome to them and to the effort of organizing team for conceptualizing and organizing this event. Let's engage on a journey of shared knowledge and experience. Thank you.
Thank you, ma'am. Srimati Tripti Saxena ji for the opening remarks. And now for the keynote address, ladies and gentlemen, may I request Dr. Subrata Rakshit, Director General, Technology Management, DRDO. Sir, please.
Professor Sood, Dr. Mittal, Ms. Saxena, all the dignitaries and participants to this conclave, ladies and gentlemen. It gives me great pleasure to be here before you on behalf of Secretary DRDO, who, as is often the case in Delhi, had a sudden meeting scheduled with the minister. So I have come in instead. From DRDO's perspective, the quantum technologies, especially the QKD, has been a focus activity. We recognize that in time, both the QKD and the quantum computing could potentially have significant consequences to national security posture, both in our ability to defend, as well as perhaps give us the options of being able to discern what others are doing. So far we have looked more at quantum key distribution systems, because we have found that those seem to be holding the early promise in terms of maturity. But there are also fledgling exploratory efforts by DRDO itself in the other two domains of computing and sensing. given the deep physics and exploratory nature of the work, much of this is perhaps not going to be immediately done by DRDO itself. DRDO has a very rich ecosystem around it consisting of academia, startups, MSMEs, and we would fund and nudge these efforts to make sure that the correct ecosystem develops in the country such that the defense aspects of these technologies are properly nurtured. Having said that, and yes, we have certainly had good progress. We have got wide participation from industry and academia. We have lots of research groups. And it is definitely our perspective that rather than playing catch up, this is something where we should be in the forefront as one of the peer nations driving the technology and taking a lead where required. Having said all that, uncharacteristic of a keynote address, I have to give a kind of a negative announcement. If you go to the NSA website of the US, right now, it is having the following statements on quantum key distribution. NSA does not recommend the usage of QKD and QC for national security systems unless certain limitations are addressed. Now, we need to understand very clearly where this is coming from. This is a very uncharacteristic statement. They never make such negative statements normally. The issue is that when we started off on this quantum journey, there were very clearly 4 very weird things about quantum mechanics which forced us to rethink. One was the quantization itself. Second was this uncertainty principle and delocalization aspects of it, that you could not measure conjugate variables very accurately simultaneously. Then there was superposition, and then there was entanglement. Now, early on, we got a fairly good grip with a lot of effort by a galaxy of brilliant scientists on the first 2 parts. So the 20th century development of quantum-based technologies was effectively on those 2 fronts, and the entire electronics industry is a testament to it. Anything using, everybody here would know, that anything to do with band gaps and so on and so forth, effectively even your cell phone is very much based on quantum mechanics. So don't think it's classical. Only an abacus would be classical. But at some point we started wondering whether we could not also use the other 2 aspects. Now, the theoretical progress on that was not as forthcoming as it was in the other 2. And I would say somewhere around 90s, we were forced to make a tough call. Do we wait for those theorists to get their act together? Or do we back ourselves to just do the technology based on what we are aware of and proceed? Definitely we are aware of superposition and entanglement. We have no doubt that they are real, and we have no doubt that they can be exploited. And effectively that is what has happened since the 1990s. And the assumption would have been that either the theorists catch up and give us the precise equations in terms of natural parameters and constants, or we make sufficient progress to settle the issue once and for all, and we have the quantum technology based on the 2nd generation of technologies. However, 30 years later, neither of the 2 has quite happened. The efforts at coming up with objective collapse theories and continuous localization models, none of them have convincingly settled anything. So Roger Penrose and his friends are at it, but it would also seem that the vast majority in the community feel that they are doing it for their own emotional angst reasons, and the rest of us don't need to bother. But as I will tell you, that lack of theory is actually beginning to impact adversely the system engineering aspects. And from DRDO's perspective, that's what causes us some worries. So if one looks at the definition of TRL3, it says that you should have analytic understanding of all the relevant aspects, and you should be able to quantifiably verify those predictions. So let's take QKD. You want to do a communication. So A will do some encoding, it will transmit somewhere, B will do a measurement and decide something. But except in, say, Hollywood and superhero movies, it is never the case that Mother Nature suddenly goes still and somebody buzzes around doing what they want. So even as we are pulling off our QKD system, nature is furiously doing all kinds of other things in the background. And we definitely need to have a model of what nature is doing, is likely to do, the probability distributions, the parameters on which it determines the whole bang. If we do not have that, we have a model of the quote unquote signal, but not of the noise. And that's a bad state to be in. If you want to build standards, if you want to go for scalability, if you want to go for robustness, so somewhere that research does need to catch up. And as DRDO, we are willing to sponsor long-term research in our DIA COEs, which 15 of them we have established. Some of them have actually got verticals in quantum technologies. So not just to promise us a QRNG or a QC that we can use tomorrow. Even if you come up with a good proposal saying this is how we intend to study and characterize the physical characterization in terms of physical constants of superposition and entanglement, we would be happy to sponsor such research. So that's one thing from DRDO's side. Now, the value proposition typically is with respect to security. It's not the case that you'll have bigger range or greater bandwidth if you use quantum, but you'll have security. Now, this security is typically of the type that somebody cannot eavesdrop and get away with it. They may eavesdrop, but they will get caught. So the confidentiality is kind of guaranteed by the delicacy with which a quantum system is working. Now, the full picture on security is confidentiality, integrity, availability. So when you go from an Avogadro number of photons, so to speak, down to one photon carrying one bit of information, your availability is at an all-time high risk. So when you do a security evaluation of these systems, one needs to show that you have got a joint optimization of confidentiality and availability, and this is what is not happening. What is worse, in trying to go after high bandwidths, effectively the pure QRNG bits are getting parlayed into creating a much higher data rate of bits, say in MBs and GBs starting from tens of KBs. In doing that, you are reintroducing every doubt and vulnerability that the non-quantum systems had. So when you submit any of these for a national security level evaluation, it's going to get into trouble. These are the two aspects that has caused the NSA to pretty much say that for the time being, we are not even going to look at it. But these are doable things. And I think collectively, if we decide on a strategy for tackling these issues, we should be able to do it. It will require innovation in the technology domain. It will require some research in the academic domain, both of which we know how to do. So let us be clear that we can't get away with the homework not done behind our back and charge ahead with purely a technology growth. Given this, there is a lot of applications which can come up. I can speak from the defense sector. One of the biggest problems we have is when we are trying to ensure communication secrecy, and we typically do it using encryptors. Ultimately, it boils down to having a secure way of distributing the key. So what the QKD systems can do, and in fact that's the only thing they can do, is give you a very high assurance of confidentiality in coming up with a shared key. And practically that's all you need in the defense sector at least, because the rest of the paraphernalia is already in place. We already have good line encryptors which will tackle your GBs and hundreds of MBs and whatever. You do not really need to crook a QRNG to start delivering a 10 GB output. If all you can do in terms of a QRNG which you can defend under evaluation is even 10 or 20 kilobits, believe me, that is enough to bootstrap the system. But the purity in terms of every bit mapping to a quantum mechanical output is absolutely necessary if you want to get the benefit of Q as part of evaluation. So these are some of the design choices which we would like to give guidance to the industry, as even as part of DIA COE, and we have done it in episodic basis, that if these kinds of things are addressed, then we could build practical systems based on QKD which can successfully undergo an evaluation and which can then bootstrap the existing system to be far more user-friendly. The services right now are having to send human beings as trusted couriers from point A to point B with the top level keys. So there is a data, there is an encryptor, there is a key for the encryptor, there's a key encrypting key, and that box itself needs another key. So, it's like a turtles all the way kind of situation. When you terminate it in QKD, you're suddenly saying now in God we trust and end of story. And that's beautiful. But we need to get the system design right in order to really reap that benefit. So in this conclave, I'm sure some of these ideas will get discussed. Conclave is not just about the presentations people have prepared and brought. It is just as much about the peer-to-peer exchanges, the coffee break conversations, and the planning of action for the days ahead. And I certainly hope that this will be a very successful conclave in that sense, that the various delegates will take the opportunity of sharing their pains and gains, and collectively we should be able to come up with a range of quantum-based systems, whereby quantum we mean either superposition or entanglement, which will deliver value to the defense, and I'm sure it will also help the civilian sector. One final thing, we have actually gone ahead and had a TEC-GR on some of these QKD systems, and that was in fact a very illuminating experience for those of us who are involved with it, because you got to see the amount of progress made in the country, the availability of various resources, experts, and already invested technical capabilities in the country. It also turned out that while initially we had assumed that we will leverage the existing telecom fiber networks, the standards which needed to be followed for the QKD class of applications turned out to be far more stringent than what you would normally need for a telecom application. So the standards that ended up getting evolved are not things which are automatically fulfilled by commercial telecom fibers in terms of the dispersions, in terms of the leakage of stray photons into the fiber, so on and so forth, and even the temperature fluctuations and variations in terms of transmission times. Because these QKD systems are really that delicately balanced on the edge of failure. If that is the case, we have to rethink whether we simply want to stick to those particular telecom wavelengths and redesign the fibers to be that much better, or could we have gone ahead and done some other wavelength and other physical media in the first place. These are early days. We should not get stuck into a stated position just because we took it in the year 2022 or 21. It might have to evolve, so be it. And with the broad support across various ministries in India for this effort, I can assure you government support won't be lacking. And in any case, as far as quantum is concerned, you got the central banks worried that they'll get looted, and you've got the defense worried that they'll get checkmated. So really, you got the two best funding sources on your side. So don't think about that as a constraint, but you do need to get the basic science and technology right, such that the effort is going to be long-term and scalable. I mean, if we are going to be working on exploiting coherent phenomena, I think it's ironic if we adopt a development strategy which is fundamentally incoherent in itself, and everybody is the master of his own technique and it doesn't operate with anybody else. So we do need to get the basics right. We need to get an alignment across ourselves. Only then we'll have defensible standards. And with all of that, I'm sure that this is a field which is going to grow by leaps and bounds. And once again, from DRDO's side, both in terms of doing the security evaluation at the topmost level, as well as funding the basic research at the bottommost level, and including intermediate MSCs and startup supports as required. For the full spectrum, we are very much committed to supporting this space. Thank you so much.
Thank you, sir, for your address, for throwing light on certain areas. Ladies and gentlemen, Dr. Subrata Rakshay, Director General, Technology Management, DRDO. And now it is indeed my proud privilege to invite respected Professor Ajay Kumar Suchi, Principal Scientific Advisor to Government of India, and request sir to kindly deliver his keynote address.
Dignitaries on the dais, Shri Rajiv Mittal, Dr. Subrato Rakshit, Srimati Tripti Saxena ji, participants from industry, academia, government, and media. It is indeed a pleasure to be back at this conclave almost a year back in this very hall, and I would like to thank DOT for inviting me to share my thoughts in the second conclave. Since this is a gathering of eminent experts and industry leaders in this field of quantum communication in particular, but quantum technologies in general, I thought there is no point of my going into scientific and technological excitement of the field. All of you are excited, that's why you are here. That's obvious. So I thought that I'll take this few minutes given to me to focus on important policy measures that have been taken in the past 1 year in the Indian context since we met here in March 2023. So I'll just remind you what has happened. So before I come to that, let me draw your attention to the latest World Economic Forum Quantum Economy Blueprint, which came out in January 2024. I am sure some of you would have read it. They have quoted McKinsey's Quantum Technology Monitor of April 23 and said that the global quantum technology market is projected to reach 106 million US dollar by 2040. So it is not only the scientists and engineers and technologists have the challenge for exploration before them, but it's obvious that there are enormous opportunities for the industrial sector, for the startups, for MSMEs, and so on. And this is the way the quantum world will evolve in future with all the stakeholders. So when we met last, as I said a year back, there were a lot of expectations in the air about Indian quantum technology trajectory. I must say that the year following that has been very eventful for this entire sector, and briefly I'll point out a few points. So as you know that this mission, National Quantum Mission, was approved by the government in April 2023 with a budget of almost 6,000 crores. And it has identified well thought out deliverables. Now, here the other ministries are also involved, and so Department of Science and Technology is the lead agency which will be implementing this mission. But along with this, there are other departments like Department of Telecommunication, MIT, Department of Defense, DAE, and Department of Space. So you can see that by design, right from the beginning, it is a multi-agency mission, and collaborations among different arms of the government is built into this right from the beginning. So soon after getting the approval of the cabinet on this proposal, DST got into action to put in place the governance structures and other nuts and bolts of the mission. And I am sure there are people from DST here who can tell you more about it. While this was being done by DST, our office and DST got together and we organized 4 national state-of-the-art discussion meetings on quantum computing software, quantum computing hardware, quantum communication, quantum sensing, and quantum devices needed for all the sectors. So this was during July-August 2023, and more than few hundred people participated in these 4 events, and I can see many of you in the hall who were present during those discussions. So the aim of that exercise was to do a capability profiling of the country in this upcoming field and to discuss the challenges in delivering the goals of the mission. That was the very specific objectives, and 4 booklets have been produced by DST, and I am sure they will be available. Maybe Ekta, you can tell where it is available. Some of those documents are very useful to know what our capabilities at present are and where do we go from here. Now, so here the structures, so what after that it has been done, as you know, that we had to have a call for the proposal, and that call for the proposal has come out a few days back, and in that we have made it, I think, quite explicit what our expectations are. So as you know that I mean, I hope many of you might have looked at the call, and probably your DST talk will tell you more about it, Ekta's talk. But in general, what we are aiming is to have 4 hubs, and each hub will have many technology groups. For example, in quantum communication, there will be 2, 3 technology groups or 4 groups, and each group will be a consortium of academic institutes, startups, industry, and all the players who want to play a role. So that is the way the hubs will be formed, and the goal is that we have to focus on the very fundamental R&D. Obviously, this field has yet to have more breakthroughs, but also to see that it translates into products at the end of the day. So it has the full bandwidth of expectations, and our hope is that this hub and spoke model would be the right way to go about doing it. So you would also notice in the last 1 year that this quantum technologies has been an important area which has been discussed at various bilateral and multilateral collaborations. And for example, in the ISET with the US government, this is one of the important areas. In the Quad, it's an important area. Again, 4 countries, as you know, Quad countries wish to collaborate, and so on. So our goal is that all these bilateral and multilateral collaborations should help to access advanced fabrication facilities, test beds, and so on. And this is what is being negotiated, and as some of you who are in the hall are part of that exercise. So let me briefly mention the broad picture which has come out of various consultations. Now here I must compliment DST for the early steps they took by Quest program, which initiated this quantum technology effort almost like 4 or 5 years back, and few hubs were formed, and also the cyber physical system which is ongoing, that also contributed to really come out with a more definitive plan for quantum technologies. So they were the pre-runners of this quantum mission. So also the major software, major players are also encouraged to be a part of this, so that quantum computing as a service can emerge very soon. So this mission will have all aspects of this. I will not go into all the details, but hope is that in about 3 to 5 years, as we go along, we will have high-end research, also the products which will come out at different levels of their maturity. So this conference like this is a great step, And I must compliment the Department of Telecommunication because they came out with a very comprehensive interministerial report last year, which was also shown. And that is the way that a collective effort should go in all aspects of quantum technologies. So this is what I think will take us forward to work together. So the message is that we need to work together with all the players, and here industry, academia and government labs and government departments and all the policy making bodies should come together to see how do we take it forward. So I think I will not take more time, but just to remind that as a follow-up, of this DST call on 20th of this month, there is a discussion with all the stakeholders. It's a pre-proposal meeting, and this is to clarify all you wanted to know but were afraid to ask about quantum. That's the goal. But we really want collective work to see that all aspects are covered. So it is a mission with the deliverables, and I hope that you will all rise to the occasion to fulfill the objectives of the mission. So once again, I thank DOT for spearheading this effort. This is the second conclave, though focused on quantum communication, but you cannot live in isolation. And I am sure all aspects of quantum will appear one way or the other when you talk of quantum sensors, quantum, the detectors, single photon sources, all that different aspects are intertwined, and I am sure all of that will enrich this whole field of quantum technologies. So once again, thank you, and we now move in the last 1 year from expectations to the realm of possibilities. And the next year should be some definitive deliverables more and more as your conclaves go on. So I'm sure exciting time for all of us, and wish you all the very best. Thank you very much.
Thank you, sir, for enlightening us. Ladies and gentlemen, respected Professor Ajay Kumar Sood, Principal Scientific Advisor to Government of India. And now may I have the honor of inviting respected Dr. Neeraj Mittalji, Secretary Telecom and Chairman Digital Communication Commission, Department of Telecommunications. And I request sir to kindly guide us. Please, sir.
Dignitaries on the dais, Professor Ajay Sood, Principal Scientific Advisor to the Government of India, Dr. Subrata Rakshit, DG from the Department of Defense, Tripti Saxena from the TEC, my colleagues from the Digital Communications Commission here, colleagues from DOT, friends from the press, experts in the field of quantum technologies, eminent academicians from various parts of the world and country who are here today, people joining us online. I'm really happy to be here today. First of all, I bring greetings from the Minister of Communications, Dr. Ashwini Vaishnav, who was unfortunately not able to make it here today. He really wished to be here with all of you because the Government of India, led by the Honorable Prime Minister, feels that this is a strategic necessity for the nation. In a sense, all of you here today are participating in the most critical part of nation building. We heard from Dr. Rakshit on deep technical challenges which are ahead of us in this technology. We also heard from Dr. Sood on where the policy framework from the country is going to be. I want to speak something in between because we have a mix of people here today who possibly all of us, especially our press and myself included, do not understand the deep technology aspects of it. We all grew, me and I think most of the people sitting in the front row, reading some Richard Feynman lectures in our educational institutions, where 90% of the coursework was classical mechanics, possibly 95%. Only 5% or 2% or 3% was quantum. That too limited to studying photoelectric effect. But I think the world has changed very significantly. It's very difficult for all of us to wrap our head around when we say that we cannot figure out where a thing is, because there is no such thing in real life. As he talked, the uncertainty principle prevents us from determining two conjugal parameters where simultaneously. And therefore, it's very, very difficult for us. But I think the present generation, which is sitting all at the back, the younger ones, have had the opportunity to grow in an atmosphere where they don't see it as a challenge. For me, it is a very difficult challenge to put our heads around. And I think that's an advantage which we have today, an intergenerational advantage, so that we can leverage this technology. Even Einstein made some remarks like, God doesn't play dice with the universe, and of course, spooky action at a distance, which some of you may have read. And those actually reflect that mindset, that lack of understanding apparently with the brightest minds on the earth so far. And that shows the kind of challenges we are facing. However, that did not prevent us from using this effect in MRIs and, as he said, in our mobile phones and semiconductors. And we are all using this technology for, I think, past 20 to 30 years. The contributions of Indians, I would like to point out Professor S.N. Bose, who led to the founding of quantum statistics, and then of course led to the discovery and a very important field which has led to massive developments in science, in this science. That was 1920s. We are in 2023. Despite passage of so much time, we are still, as Professor Sood said, that we are in possibilities, opportunities, and the time of realization is yet to come. Quoting Professor Rakshit, who said, the banks are with us, and I think that led us to this shock when the Shor's algorithm, tried to, gave us exponential efficiency in breaking the prime numbers through use of quantum computing. And I think that led to this realization of the power of this technology. And it has always been the case that, necessity is the mother of invention. So we did not invent it, but we started really thinking about how all our basis of commercial transactions and of course secrecy in communications is going to get compromised. I recently visited University of Chicago, where they have one of the quantum exchanges is there. I was glad to see that the two researchers who took us around were from IIT Bombay. So we as Indians are doing cutting edge research across the world. And I think that is something which gives me some confidence that the Honorable Prime Minister's vision that we will lead in this critical technology is going to be fulfilled. As a societal need, One of the things I see which is very, very important for all of us, many of you are going to have your children in the next 10 years. You may still not have them. But to emphasize the need for focusing on basic science as parents. I remember when I was joining IIT and, was deciding which branch to join. I initially got mechanical engineering. Then I, switched to electrical engineering. But nobody wanted to go to material science. Today, the highest paid job is material science. And, unfortunately, this information takes decades to pass on. We cannot afford that to happen. We have Dr. Sood here who has worked, who has patents and, in various kinds of material phenomena. And therefore, there is a need for the press here to understand that the need and to grow in this technology is not just money. It will be a change in mindset. It will be a change in how people look at what fundamental science can do, how do we shape our children, change the syllabus in the schools. I was talking yesterday about our engineering services syllabus. We hire so many engineers every year for the ITS. We possibly don't ask them what is quantum communication, whether they have the skills, whether they have the aptitude. So the phenomena and the change has to be much wider than just money on the table. And the government is doing a lot to, do a lot of work. CDOT, our CEO is here, Mr. Upadhyay. A lot of work is happening in CDOT in terms of quantum communication. They have developed a quantum secure video phone. They are working on the recent NIST algorithms, the Kyber algorithms. They are in parallel implementing it as it is being developed by the NIST, as Professor Sood said. Our collaboration with Quad and ISET countries has to go deeper because no one country possibly solved this problem. And we as a nation have to be careful that we solve it together with like-minded parties. There are countries who have massive, resources at hand, but not necessarily who believe in the democratic values as India does. And we have to find those partners and work together with them. Professor Sood has already covered about the National Quantum Mission, and communications is one of them. And I expect that the Department of Telecommunications will, set up, participate collaboratively with all of you together to do this really massive work ahead all of us. It was also mentioned that TEC has done the general requirements for the QKD, and I'm really thankful that we have started to think about standards, because without having standards in place, standards lead the technology. It is the determining factor of which technology will survive in the commercial world, who adopts it first, and that is determined by the standards. So the role of TEC in really working together with all the stakeholders and bringing standards together as technology develops is again going to be very critical, and I hope that TEC will live up to its expectations. The role of startups again is very, very critical. I happened to visit one of the startups, the QU Labs. I think the CEO is here. He's one of the participants making one of the presentations here. And I was really amazed to see that a startup is working on creating quantum memories of about 5 milliseconds in a room of about 10 feet to 20 feet. And these are all youngsters, PhDs from, a couple of PhDs from DRDO, somebody from IISc, who have left their jobs and pursuing a dream. I think pursuing this dream, in as much as it is esoteric but critical for the nation, is really important. DOT has several schemes by which we are able to fund projects. We really encourage the startups to come and take funding help from us. We have also started, in the recent visit to the United States, we have entered into an MOU with the Pan IIT USA network to help bring experts from all over the world to help India in such high technology projects in terms of being mentors, in terms of providing guidance, in terms of helping them grow from TRL 2, 3, 4 to right up to commercialization. With these words, I hope that all of us here will really work together, including our friends from the press, who should not treat this as a esoteric subject will nobody will understand. Give it the importance in the day-to-day communications. Start a blog in every newspaper which explains some part of quantum to the children, increases their interest. Look at academic institutions who should keep evolving their syllabus, bringing in courses which are relevant. And all of us have a role to play in this journey. Not only the end goal is going to be beautiful, but I think the journey as well. So thank you so much for this opportunity.
Thank you, sir. Respected Dr. Neeraj Mittalji, Secretary Telecom and Chairman DCC Telecommunications. And now for word of thanks, may I request Shri Vinod Kumarji, Deputy Director General, Quantum Technology, Telecommunication Engineering Center, please.
Respected Dr. Neeraj Mittal, Secretary Telecom and Chairman DCC, Professor Ajay Kumar Sood, Principal Scientific Advisor to Government of India, Dr. Subrat Rakshit, Director General Technology Management DRDO, Srimati Tripti Saxena, Senior DG and Head TEC, dignitaries of the dais, officers from various government organizations, industry, academia, R&D organizations, startups, online participants, and members from media, ladies and gentlemen. A very good morning to all of you. I feel honored and privileged to get the opportunity to propose a vote of thanks on this special occasion of inaugural session of the second International Quantum Communication Conclave. On behalf of Telecom Engineering Center and the organizing committee, I wish to extend my gratitude to each and one of you for taking the time out of your busy schedules to adorn this event with your presence. First of all, I extend my humble thanks to Dr. Neeraj Mittal, Secretary Telecom and Chairman DCC, for gracing this occasion and blessing us with his words of wisdom. Sir, with your leadership and guidance, we are confident that we will be able to overcome the challenges as highlighted by Dr. Rakshit, and we'll move towards realization of goals of Government of India as highlighted by Professor Sood. And we will be able to develop the quantum technology ecosystem in the countries. I will also extend my hearty thanks to Professor Ajay Kumar Sood, Principal Scientific Advisor to Government of India, for taking out time from his busy schedule and delivering the keynote address, and also highlighting the government policies and the vision of government in the quantum technology domain. Next, I would like to thank Dr. Subrat Rakshit, Director General Technology Management DRDO, for gracing this event with his keynote address. Thank you, sir, for sharing your the concerns in the regarding the quantum QKD thing, and your views about the QKD challenges. I hope the speakers and the experts present here will take note of that, and we will jointly work together to achieving overcoming the challenges highlighted by you. Sir, also the issue of the standards highlighted by you about the quantum QKD, we will take note of that, and we will further develop the standards on the QKD, sir. I would also like to thank the driving force behind the event, Srimati Tripti Saxena, Senior DG and Head TEC, for her constant support and guidance for organizing this event. I would like to thank all the speakers who have taken the time to come from here, from various parts of the country and abroad to here, and share their knowledge in the latest technical developments in the domain of quantum technology. I also extend my sincere thanks to media for covering this event. I would also thank the organizing team for putting enormous effort in organizing this event. I would now invite all of you to proudly witness the second International Quantum Communication Conclave and gather indispensable knowledge from the upcoming sessions. Thank you very much.
Thank you, Shri Vinod Kumarji, Deputy Director General, Quantum Technology, TEC, for closing remarks. With this, ladies and gentlemen, we sum up our inaugural session, and we are grateful to all our dignitaries on the dais, Professor Ajay Kumar Sood ji, Dr. Neeraj Mittal ji, Dr. Subrata Rakshit ji, and Srimati Tripti Saxena ji. And as you all know, we have many more sessions to come. In fact, 3 sessions we have in a row. But for now, it's a tea break. So I'm requesting you all to please join us for high tea. And do explore our exhibition. It's on the first floor. We have organized an exhibition for all of you. And high tea is on the ground floor. So please do join us. For now, it's thanks to all of you. Thank you. वो तो बोल दिया सर, वो तो सबको रिक्वेस्ट कर दिया जी। बोलो।
सी डॉट को कर लीजिए पहले सेशन के बारे में ब्रीफ देके
हाँ।
सी डॉट को उनका ब्रीफ आयो पढ़ दीजिएगा। ब्रीफ आयो दिया हुआ है
नहीं,
मैंने।
सबको बैठाएंगे पहले ना उसमें।
नहीं अभी चेंज है एक एक करके बुला लीजिए।
बैठेगा कोई नहीं ऊपर?
अभी तो नहीं विल सी इन द नेक्स्ट सेशन अभी तो आप एक एक करके बुला लीजिए।
अच्छा ठीक है,
सी
तो
ओ
मैं
सी
सबके
डॉट
नाम नहीं ले रही हूँ बाकी।
नहीं हाँ अभी सिर्फ सी ओ सी डॉट को बुलाइए और उनका बायो पढ़ दीजिएगा।
हाँ, अच्छा उसमें एक चीज़ और था, दिस इज द बेसिक थीम एंड ही विल स्पीक ऑन दिस।
वो टॉपिक मत बोलिए आप
अच्छा,
बस
ठीक
उनका डिवाइड उनका बायो पढ़ दीजिए।
ठीक है, श्योर। Welcome back, ladies and gentlemen. So now in our first session of Second International Quantum Communication Conclave, we will get to hear from our eminent speakers on development of quantum ecosystem. The session will basically focus on various initiatives being taken by the government and the industry, along with the global strategies from promoting the development and deployment of quantum technologies. And let me invite our first speaker of this session, Dr. Rajkumar Upadhyay ji, CEO C. Dot. Dr. Rajkumar Upadhyay ji is the CEO of C. Dot. Basically, C. Dot is actively involved in the development of quantum technologies, particularly in the area of quantum communication, and has developed quantum key distribution systems and post-quantum cryptography systems which enable the secure transmission of information. Dr. Upadhyay is an officer of the Indian Telecommunication Services of Government of India, PhD in Corporate Strategy and Policy from the Indian Institute of Management, Bangalore. Dr. Upadhyay is also an alumnus of IIM Bangalore's postgraduate program in Public Policy and Management. Dr. Rajkumar Upadhyay has won many awards, to mention few. J.C. Bose Award by Ministry of Defense, the National E-Governance Award, CIO 100 Award by International Data Group, and Deepak C. Jain Award by IIM Bangalore. So we now welcome Dr. Rajkumar Upadhyay ji. Please, sir.
कितना मिनट है? Good morning, everyone. I think with this scintillating inaugural address, I think lot of advancements and the policy measures have been covered in the previous inaugural session. So I am going to run through you what is being done in CDOT. So my topic is R&D initiatives in quantum communication. This is the agenda. We will talk about quantum introduction, what are the trends, what are our R&D goals as a country, what has been the QKD related activities at CDOT, what is the PQC related activities at CDOT, and next one, fifth is the hackathon, which is the challenge which has been open for detecting the breach and getting an award of 10 lakh rupees per breach, and the last I will summarize. So typically the event is about quantum communication. Typically the quantum is into 4 domains: quantum computing, quantum communication, quantum sensing, and quantum materials. So primarily we at CDOT work in quantum communication domain. We are not working in the domain of quantum computing, quantum sensing, and quantum materials. You all know, it has been talked about in the previous session, the future is quantum. There is a huge, not only banks and the defense sector, there is lot many applications in the civilian sector which will come, be it drug discovery, healthcare, oil and gas, supply chain. In many areas, the quantum will be useful. So, I think this is old, दूसरा presentation load कर दिया आपने. It's not my presentation. The morning I sent, it's not this presentation. Okay, no problem. So anyway, typically in quantum communication area, we are working in 2 areas, PQC and the QKD. PQC is a mathematics-based system of quantum cryptography, and QKD is the physics-based, which was talked about in the morning using quantum physics. In the PQC area, the cryptographic key exchange algorithm is based on a new class of hard-to-compute algorithm. Even if the quantum computers come, this will not be broken. And it can be implemented using today's classical computers, but cannot be hacked using the quantum computers. Both our systems are in the exhibition area in the first floor. The QKD is based on the physics base, where the keys are generated using the photons. And the QKD offers information theoretic security in the sense that this is not assumption based. There is no assumption made. Without any assumption, this will provide you information theoretic. It's a foolproof security mechanism which the QKD provides. What are our R&D goals? Our R&D goals are, ensuring security. Hybrid systems, what we mean that you make use of PQC as well as QKD together. Ease of migration, because many of our applications can move very easily if we do the development here, like our VC tool or any of the existing applications can be migrated very, very easily if the systems are developed here. Cost efficiency, once it is done in India, definitely given the talent we have in the country, the cost will be very, very less. Multi-topology support, it can work in a hub and spoke model or a ring model. Manageability, and the manageability will be there. One of the system we have put in the exhibition where you can even generate the attacks, the eavesdropping attacks into our system. So you can simulate these attacks, and so the manageability also is available with us. This is typically what CDOT has done till now. We have developed the QKD system, which is working in both using COW and DPS protocols. COW and DPS protocols. So there are 2 protocols currently available, and there are others also. We have implemented both the protocols, COW and DPS, and the measurement device independent QKD also is coming up, because there have been reports in the literature that this QKD system could be prone to side channel attacks, and therefore there was a development which was appearing in the research literature. We have implemented this measurement device independent QKD system. The multiplex QKD system is also available. What we mean by multiplex QKD, because typically QKD requires 2 fibers, one for quantum channel, one for data classical channel. But because during our implementation in MTNL, we found that we are running short of fibers, and therefore we have developed a system in which in the single fiber the data and the quantum both can flow. But the limitation here is, for example, the system number 1 is supporting around 140 kilometers. The system number 3 can support only 50 to 60 kilometers. We also are aware that we need to do a lot of indigenization, and therefore we have developed a single photon detector. It is in the final good advanced stage. RF driver for intensity and phase modulator. So basically what our role is, first make the system and then slowly decompose the system into parts, and these parts are done within India. So the single photon detector as well as RF driver we have done. This is our setup. I think you can better see the setup in the first floor. It's a working system, and now we have also integrated this system with the free space system. We are in the free space system, we are working with the PRL, and you can see the demo of combining the QKD in the optical domain and the free space domain and the key exchange between these 2 mediums. So this particular system is also in the display in the first floor. We are the first organization in India to secure technology approval from TEC. TEC came up with GR, and we applied our system, and we were happy to receive the TEC certification for our QKD solution. We support multiple network topology. The first left part is about the ring topology. You can put the nodes in a ring so that the key flows within the ring. Even if one node goes away, the keys can still be exchanged in the ring manner. The right side is the hub and spoke model, and in hub and spoke model, the hub part we are bringing dual star technology, wherein even if the hub fails, because the hub becomes a single point of failure, and therefore hubs should be into active and standby mode. So we have both the systems, which is one works with the ring topology and the other one is the dual star topology. And this works in a trusted relay model, as can be seen with the diagram in the bottom. The keys are established between first system and the third system, second and third, first and second. You can identify the keys from the color of the keys. So using this trusted relay mechanism, the keys can be worked out between various end nodes. This is our system. I mean, you can see down, but this is broken down into hardware. What electronic design and circuit is done by us. QRNG, currently we are importing the chip. The printed circuit board design is ours, mechanical enclosure ours. And FPGA, what we have implemented, the complete key distillation engine is implemented on FPGA by us. Soon QRNG will be indigenized, because we are working with IISc, who is designing the chip, and we are designing the rest of the circuit. And the software for QKD network manager, key manager, QKD network controller, all are designed indigenously. So the full system, QKD system, is fully indigenous, other than the QRNG chip, which is imported currently. We have filed patents. One patent have been granted. Few patents have been filed. Few research papers we have published in the QKD domain, because when the Quest program came, although we were not part of the Quest, but given that this is an important area, CDOT started working much earlier, and today this QKD system is already working between Sanchar Bhavan and NIC and handling the commercial traffic for last 1 year. Almost 1 year it is handling the commercial traffic. The QKD field, we have done trials. The trial is done in the army between Chandi Mandir and the Kasauli in Himachal Pradesh in December 21. And the army trial, we use both the systems together, the PQC and the QKD together in a router. And I'm also happy to report that the routers, our routers can take the quantum keys. In fact, our friend CUNY is here, because they are also using our router. VVDN is manufacturing these routers for both BRTR and CRTR routers, which can take the keys of both PQC and QKD. One of the system we have also given to JIIT for academic research, because they have put this system for experimental research and we continuously take feedback from them. If anything is found out, we implement this in our system. This is another way of, now the QKD system, now research has started appearing that the QKD system could be prone to side channel attacks. And therefore, we have introduced a third node. This is the system which is under progress. I think it is almost TRL 8 now, where the Charlie node will take care of the side channel attacks. So this also has been done. And we have achieved HOM interference with 40% visibility to check photon indistinguishability, because this is one of the, these three scientists have worked out on that, because we need to see that the photons arriving from the different nodes arrive in the same polarization and similar characteristics, so that the maximum interference can take place. And this MDI QKD will ensure that the side channel attacks are also not done. These are the in-house sub-modules. As I said, whereas we have already rolled out the production system out, but we are working into making the sub-components used in the system, like photon detector we import from France. Now we are making our own photon detector. And we have also made our own intensity phase modulator driver. So these are the two major components which work into the QKD systems. You can also see in the PQC we have put in first floor. This is the quantum phone what we have made. Quantum phone is basically a VoIP phone, but having the PQC algorithm implementation inside. So the whole PQC, as you may be aware, the NIST had run the challenge from 2016 to 2023, and finally they finalized algorithm called Crystal Kyber, and that Crystal Kyber is implemented inside this phone. So it can work on a captive network as well as it can work on a public network. The beauty about this is it can also work on a public network. In a captive network, you have no netting issues will not come, but in the public network, because some of the machines may be behind the net, behind the netting, Therefore, we will need a central server to make these things work. The right side box is the compact encryption module. If you are two offices between Delhi and Mumbai and you want to protect them, so you put one box in the Delhi, one box in the Mumbai. The traffic which will flow between Delhi to Mumbai will be quantum safe. This particular box which we have put down can handle only 80 MB traffic currently, but now our another system which is called Pine, which is now 1 GB, which is ready. The 1 GB one, the left one, the 1 GB Pine system will come at a military grade, because military DRDO wants a SAG approval. Many of the agencies, defense people ask SAG approval. Therefore, the Pine we are designing as a military grade things, because it is tamper proof. Even if you remove a screw, alarm will come. So it is not only a tamper proof physically, it is also tamper proof in terms of algorithm and PQC implementation. The last one is the commercial grade post-quantum encryptor. All these machines you can see in the first floor. These have been the field trials till now. The POC field trial of CM is done in the Indian Army, and POC was also done between two sites of Ministry of External Affairs. We also did two POC channels are operational between Sanchar Bhavan and TC, which I was referring to you, that it is handling the actual traffic of DOT, which goes via TNIC. So I think users may not be aware of DOT that their traffic is actually going in a quantum safe manner up to NIC server. We have also done POC of PQC CM between with the Cabinet Secretariat, and this PQC can be implemented in the voice conferencing, video conferencing. If you want to be, first of all, our video conferencing solution is already having multiple layer of encryption, but if required for very sensitive communication, the PQC plugin can be inserted in the browser, and the VC communication also will be quantum safe. We have been working with the SDOs. We are very active in working with TSDSI. We are very active working with ETSI. ETSI ke saath we are working with ETSI, and we have made a presentation or approach to quantum safe migration at ETSI, because now word is talking about if quantum comes, how do you migrate to quantum safe migration. So standards are coming up, and therefore we are working with the standard agency. We also work with the NIST and that is how the NIST algorithm, while we were working with the NIST, we could implement while the standard was coming out. So the Crystal Kyber was implemented before it came out. This is one good challenge. It was announced in the first conclave. Honorable Minister announced that all our systems, quantum phone, our QKD system, our PQC system, if any of the breach is found, per breach we will pay 10 lakh rupees. So that is in our website, and it is still valid. Some 5 companies have come to us. They accessed our system, they could not break, and we encourage our industry, academics, and the enthusiasts to come and break the system and claim a prize of 10 lakh per breach. If you find 3 breach, we will pay you 30 lakh. So the prize money still remains unclaimed. I think you're looking at time is almost done. So other contributions, we have done work with we played a very crucial role in interministerial committee on quantum communication, which we also worked with DOT in forming that interministerial communication report. QRNG module, as I said, we are right now getting the QRNG chip from outside. So we realized there is a need of having QRNG inside. So we are working with the ISC. ISC is making the chip, and we are making rest of the circuit. Integration of, you can also see the demo of integration of QKD with a free space with PRL. We have been collaborating. We have recently funded CDAC for MV QKD system, CV QKD system, continuous variable QKD system. This is another advancement. We have formed a quantum alliance. A lot of quantum companies are in our alliance, and we also take part of the various standardization, and we worked very closely with TEC in forming the TCGR. In summary, CDOT has industry developed field deployable QKD and PQC system. They are not lab system, they are only production grade systems. They are already working in the, as I said, working between Sanchar Bhavan and NIC and Sanchar Bhavan and TEC. And CDOT has also pioneered, other than quantum, in other areas. Since we have our own DWDM systems and our own router systems, we have integrated these PQC and the QKT with our routers as well as 100G DWDM systems. CDOT is capable of providing customized indigenous solutions to upgrade the network with quantum security. So with this, thank you so much. Any questions I think we can take in the, yeah, thank you.
Thank you, Dr. Rajkumar Upadhyay ji. And now may I request Dr. Ekta Kapoor ji to kindly join us on the dais. Ma'am, please. Dr. G. Raghavan ji, I'm requesting to please join us on the dais. Shri Sunil Gupta ji. And Shri A. Robert J. Ravi ji. So now, ladies and gentlemen, I'll request Dr. Ekta Kapoor ji. But before inviting her, let me share a few things about her. Dr. Ekta Kapoor heads the Frontier and Futuristic Technologies Division in the Department of Science and Technology. She leads DST's 2 national missions, the National Mission on Interdisciplinary Cyber Physical Systems and the National Quantum Mission. Dr. Kapoor is a doctorate in pharmacology, and she also heads the National Good Laboratory Practice, that is GLP Compliance Monitoring Authority. With an experience of 2 decades in GLP certification, the committed and sustained efforts of Dr. Kapoor have not only led to India becoming a full adherent to mutual acceptance of data in the OECD, that is Organization for Economic Cooperation and Development, but also to India's presidency in the OECD's Working Party on GLP for the next 2 years, that is 2024 and 2025. So now we have Dr. Ekta Kapoor ji. Ma'am, please. It's all over to you.
A very good morning to one and all. Dr. Neeraj Mittal ji, Secretary Telecom, Madam Tripti Saxena ji, all senior officers from the Government of India, researchers, academicians, fellow speakers of this first session of the second International Quantum Conclave, which are present with me on the dais, friends from industry, startups, ladies and gentlemen. It's an exciting moment for me to be a part of this session of the initiatives of government and industry on quantum technologies in this second conclave. I would like to thank the organizers, the TEC, CDOT, TSDSI, to give me an opportunity to share information on the National Quantum Mission. This mission was launched last year in April to bring India at the forefront of this exciting technology, where we really believe sky is the limit. We would like to excel and bring out critical breakthrough technologies through this mission to take India to the forefront of the world. I would be talking about the National Quantum Mission, the actions that we have taken so far, and the way forward. Most of the things were discussed in the very interesting inaugural session today, where the Principal Scientific Advisor to the Government of India already explained the steps that have been taken by the Government of India to bring quantum technologies on the forefront through this National Quantum Mission. Just to give you a background, quantum technologies, that is the NQM, is one of the 9 missions of national importance, being driven by the Prime Minister's Science, Technology, Innovation Advisory Council, that is PMSTAC, through the PSA's office to leverage cutting-edge scientific research for India's sustainable development. The mission was announced by the Honorable Finance Minister. It was then named as National Mission on Quantum Technologies and Applications, that is NMQTA, in the year 2020. The mission was formally launched in April 2023 by the Union Cabinet, which approved it as the National Quantum Mission at a total cost of rupees 6,003.65 crores for a period of 8 years. The mission is currently implemented by the Department of Science and Technology on behalf of the Government of India. As rightly mentioned by PSA sir in the morning, there are other ministries which are partnering with DST in this national mission. We have departments which are contributing through their own budget for the mission. These include the Department of Atomic Energy, Department of Space, Defense Research and Development Organization, that is DRDO. We also have departments, namely the Ministry of Electronics and Information Technology and the Department of Telecommunications, which are partnering with us as knowledge partners in the mission. As already explained and discussed, we know there are 4 thematic areas in the research across quantum technologies, and these include the quantum computing, quantum communication, quantum sensing and metrology, and quantum materials and devices. The entire work that is going to be done across the world in quantum technology has to be in these 4 domains. This slide tells us about the deliverables that the mission promises to bring out. The deliverables are categorized in the 4 domains again. For the quantum computing, it is to develop intermediate scale quantum computers with physical qubits during the first 3 years, increasing them during the next 3 years, and so on. So at the end of 8 years, we hope that we are going to have a quantum computer with this kind of an output. Quantum communication, again, there has been the need for developing secure quantum communication across 2,000 kilometers within India, including both satellite and fiber-based communication, and long-distance secure quantum communication with other countries as well, and to develop multi-node quantum networks. For quantum sensing and metrology, the mission aims to develop magnetometers with high sensitivity, develop gravimeters of high sensitivity, and develop atomic clocks with, again, 10 raised to power minus 19 fractional instability. For quantum materials and devices, it is envisaged to design and synthesize the quantum materials required for these quantum computers, and also for production of devices for enabling various quantum technologies that would come out as outputs of the mission. The main activities or the mandate of the mission, it revolves around 4 major activities again, including technology development, human resource development, entrepreneurship development, and industry collaborations. And since we are all, already working with a number of countries through multilateral and bilateral agreements, it involves a lot of international collaborations to be done as a part of the mission. The mission will see a complete technology life cycle approach, starting from knowledge generation to product development to translation and commercialization. We need to understand that technology development has to go hand in hand with conducting R&D in all sub-themes within a specified domain, thus ensuring creation of an innovation ecosystem. We need to support entrepreneurship development as a part of this mission by supporting startups which are engaged in working in these technologies. We are also going to develop human resource and have a core research base developed in the country across these 4 technical domains. Of course, we are going to address problem statements given by various government departments, line ministries, and also to do international collaborations. If we look at the key milestones of the National Quantum Mission in India. It's going to be broken down into 3 phases. The first phase, which is up to 3 years, will witness prototype development. This will include establishing the 4 thematic hubs, that is T hubs, in the 4 various verticals of the quantum technologies. We are going to give fund support to the T hubs, and the mission will witness a formal kickoff very soon. The missions, the T hubs will be working on prototype development. The phase 2 will be up to a period of 6 years. We will be witnessing product development and deployment. Product development and deployment will be across various sectoral applications. The phase 3, that is up to a period of 8 years, will further witness business development and economic growth. It will witness a sustained business and increase of the job market in the areas of quantum technologies, scaling up of businesses, and finally contributing to the economic growth of the country. This is the latest development that has taken place. We at the Department of Science and Technology have announced a call for pre-proposals for setting up of thematic hubs, the call was launched on 20th of January 2024. The last date of submission of the proposals for this pre-proposal call is 21st of March 2024. The hubs that will be set up, already explained in the morning session, and I'll be explaining it further. They are to be set up as consortia. The consortia in each hub, each thematic hub, will consist of a number of technical groups working on different technologies in a particular vertical. Say, for example, we have quantum computing vertical. It will have different technologies like trapped ion qubits, developing computers based on superconducting qubits, semiconducting qubits, photonic qubits, or neutral atom qubits, etc. So these individual technologies will form different technical groups. Each technical group in a specific technology vertical will consist of at least 3 to 4 academic institutions and R&D labs, with the provision for inclusion of startups and industry partners working in the domain of respective technical group. Each technical group will be led by a lead PI who serves as the main point of contact for collaboration and coordination among the consortia members, and the lead PIs will further submit a detailed pre-proposal on behalf of the entire consortium for forming the respective technical group. The lead institutes of the technical groups within a vertical will collectively establish the Section 8 company to function as the thematic hub. I think this is a bit confusing, but all of this is to be clarified on the meeting, brainstorming meeting that we have planned on 20th of this month, which will be chaired by the Principal Scientific Advisor to the Government of India and Secretary, Department of Science and Technology. It's to be held at the India Habitat Center. Just to explain more, a little more in detail, we have the 4 hubs. The T Hub 1, say it's on quantum computing. It will have different technical groups depending on the technologies that are being used to develop the quantum computer. Each technical group will have 3 to 4 or maybe more academic institutions, R&D labs, or as partners of that technical group. Each group again would have a lead PI or a coordinator, and the technical groups 1, 2, 3, 4 that have been listed here will collectively form a consortia for quantum computing. The consortia will also include a number of startups, industry on board since right from the beginning, so that we can have the right synergies coming from the nation across to work on these challenging technologies. That's all. Thank you so much. We'll be taking up the questions later. Thank you. Thank you.
Thank you, ma'am. Dr. Ekta Kapoorji, briefing on National Quantum Mission driven by DST. Thank you so much. Our next speaker is Professor G. Raghavanji, He is presently Director, School of Quantum Technology, Defense Institute of Advanced Technology, Pune. Professor G. Raghavan joined the Department of Atomic Energy after completing MSc in Physics from National College in Trichy. He has wide experience in photonics, photonic devices, and non-linear optics, and has been instrumental in setting up laboratories in quantum information, quantum optics, and femtosecond laser spectroscopy. So may I request Dr. G. Raghavan to kindly enlighten us.
Dr. Mittal, Madam Saxena, the dignitaries, and friends from DOT, thank you very much for giving me the pleasure of being here and with friends from the quantum world. So, I think my presentation has not yet come up. So I will take off where Dr. Rakshit actually started something on the flip side of quantum, with the intention of pointing out what are the perils that lie ahead and how to prepare for them. I will say the need for quantum randomness and what we say is the ultimate in privacy, namely physically assured form of privacy. By physically assured, we mean the laws of physics, namely quantum mechanics, give me an unprecedented assurance of privacy. Now, this is the claim. This is what the theorists claim. And there we have the god of quantum randomness, juggling with things, superposition, entanglement, and whatnot, with cats that are both dead and alive at the same time and unless they are observed. And observation makes the phenomenon manifest. They don't certify. According to quantum theory, phenomena are manifest upon observation. And there we have a Tamilian like me, Tamil Chelvan, having a very dead cat or a very alive cat trying to figure out what this whole thing is about. And he is a device maker. And then between the theoretical assurance and the practicing device maker, there is the gap. And that flips out Tamil Chelvan. I'll just take the quantum random number generator as an example, because that is the heart of the deal as far as QKD is concerned, and then point out the need for standardization and for looking at problems with quantum devices. Next slide, please. So there we have the ideal is unreachable and the practical is flawed and impeachable, and we have to be aware of this when we build quantum devices. Next slide. So we have this very simple picture of the one-time pad, which I'm sure all of you are familiar with. We have the plain text, and we have a perfectly uniform random private key, and you XOR it to get the ciphertext. Ciphertext can be communicated over a public channel very securely without any problem from Alice to Bob, and if Bob were in possession of the symmetric key, then he can again XOR it with the ciphertext to recover back the original message. And just a flipping of bits. Now, quantum key distribution, as somebody else pointed out, is just no more than a trusted courier. How trusted is that courier, and how good is that assurance? Next slide. So perfect randomness and perfect keys. Now, mathematically, randomness is something that lacks a definition. We do not know how to define randomness. This is the fact of the matter. You can take any book in mathematics or probability theory. There is no definition of randomness is, and so on. And then we have the need, compelling need to say something is uniformly random and that is private. Again, there's no way of finding this out. So in an IID-RV, independent, indistinguishable random number generator, that is a toss of a fair coin, we are supposed to get a stream of zeros and ones, which are supposed to be uniformly random. So given a seed, the next output must be completely unpredictable. This is called forward unpredictability. Given the outputs, the seed must be unpredictable, backward unpredictability, and there should be no correlation between the two, whatever. But we have neither a mathematical definition, as I said, nor a practical way of testing for randomness. Because, as Kolmogorov in his early Russian edition pointed out, probability is not just mathematics, it's a physical theory. Next, please. So, I'll take the example of this quantum random number generator, which I'll call ours outputter of random numbers and random bits. So that's, we have three different flavors, or possibly four of these random number generators, the PRNG, the TRNG, and the QRNGs. So one is a pseudo-random number generator that a program with an unknown seed and an algorithm will generate it, and the objections are that if the classical seed is known, it becomes insecure. Regarding cryptographically secure random number generator, we take a PC or a laptop, look at a variety of processes, keystrokes, jitter, and so on, and then use that as a seed and then write an algorithm to get a PRNG. And then finally, we have the TRNGs, where any classical system is there, like a chaotic system and a laser or whatever. And there, the initial conditions, the system is extremely sensitive to the initial conditions. And because we cannot access all the initial conditions, the system is deterministic, but we neither have the capability of knowing the initial conditions, nor the capacity to handle so much of information. And therefore, there's a trade-off between information and randomness. More information, less random seems to be the outcome, and more randomness, less information we have about it. This sort of a randomness is epistemic randomness, or randomness that arises due to absence of knowledge. There's nothing inherent about it. Again, the argument is that if I know the initial conditions, I can break this. This is an argument, not a demonstration. And finally, we have QRNGs, which are supposed to be intrinsically or ontologically random, randomness by declaration. Quantum mechanics merely says, I do not know why something collapses into a dead state or a alive state. It just throws up its hands. But just one interpretation where it says, okay, I can, of course, compute expectation values or average values. But a single photon approaching a partially silvered mirror, whether it will be transmitted or reflected, quantum mechanics cannot predict this. And then this unpredictability, again, there are different variants of interpretations at the foundation level of quantum mechanics. To elevate it to a law of nature is simply abhorrent. This is what is written in textbooks, but it's simply wrong. Quantum mechanics is silent about the whole thing. And then we say that if I make a QRNG, it will be completely unbreakably random. So regarding PRNGs, Johnny von Neumann, who wrote this fine book on Hilbert spaces of quantum mechanics, says anyone who considers arithmetic methods of producing random digits is of course in a state of sin. Is of course in a state of sin. But is anybody talking about QRNGs in a state of sin? We'll look at the next slide. So next slide, please. There we are. So we have in this ding-dong battle between the cryptographer and the cryptanalysis, the cryptographer is with the quantum resources, the physical limits of privacy through Heisenberg's uncertainty principle, the no cloning theorem, we cannot perfectly clone quantum states, indistinguishability of arbitrary non-orthogonal states, monogamous nature of quantum entanglement, and of course, a dash of free will. Just Zarasa quantum. We actually made a device called Zarasa quantum. So Zarasa quantum, with all these ingredients, there we have, that is his Victor's secret. Give me a little bit of quantumness, and I can expand this randomness through normal hashing process. It's a brute force mathematical process that will give you the so-called randomness of QRNG, PRNG, TRNG. None of these devices will pass any of these statistical tests. And statistical tests are not the answer, because they only show there is an evidence of absence of pattern up to my computational power. But evidence of absence is not absence of evidence. One should not make this logical mistake, and therefore, I will show us next from our own quantum random number generator. Next, please. Random number generator, that we have built our own random number generators, lattice-based PRNGs, QRNGs, and we, any raw data as it is, all these things fail. And QRNGs fail more spectacularly as compared to the other ones, simply because the initial mean entropy is very high for QRNG. But however, when you do this brute force mathematical extraction process through these hashing methods, all of them pass. So on what basis? I have no theoretical basis of claiming quantum randomness to be superior, nor do I have a statistical test that will show me that QRNGs are special. And our entire security of QKDs is premised on the availability of high entropy QRNG sources. So there is therefore a very strong, in this case, physics prevents you, mathematics prevents you from doing a proper characterization. At DIIT, we have developed a variety of TRL-10 products. And our approach has been to start with making photon sources, entangled photon sources. We have made homodyne detectors and a variety of these, including FPGA-based post-quantum software, timing circuit. Timing is very, very important for QKD, especially for advanced protocols, less twin field and MDI QKD that he alluded to. So unless we know, have complete timing and synchronization control, there's no point in talking about this. So next, please. The long and short of it is this. So there we have General Bart Simpson Ling. I mean, the name, the face, and the symbol, flag. Of course, these are all politically neutral. These are incidental, notwithstanding the fact that NSA has broken through back doors into and taken advantage of the random number generator and its weakness in a variety of ways, including the bull run and so on, where they broke hardware and software devices, notwithstanding the fact that a big telecom manufacturer from certain part of the world is banned in other parts of the world. Notwithstanding this, let us see this snake oil salesman, General Bartling, sells me this magic jack or the quantum safe, whatever. And then I do this random number extraction. I pass it through my statistical test, die hard, or die hardest, or whatever, and everything will pass through. And ultimately, the solution is to run something called a loophole-free bell test to check for quantum randomness, and not a single successful case has been recorded in the entire world, because these are extremely difficult things to perform. And the heart of, again, bell test is a quantum random number generator. So that leaves our poor Tamil Selvan again wondering what this whole business is about. Next, please. So now let us look at the practical aspects and why we have to have an approach where we manufacture the subsystems, completely test and certify them before we put them together in a complete system. This is the only path of assuring that the larger system of systems, is completely secure. So QKD is a point-to-point and, of course, does not support a network topology. Key rate to distance, there's a very severe limitation that it falls off exponentially. We know that for fiber, we know that for free space. Vulnerability to quantum hacking side channel attacks. So we need to have finite key tight security analysis. So whenever somebody says, I made a QKD, you ask this question, what is the security analysis you have done? An improper security analysis, whatever key rate, is just a bad job. So detector-based attacks are very common. Then we lacked ideal single photon sources. We have made some of them at TRL-10, including entangled photon sources that generate about 2 million photons per microwatt per second. This is a TRL-10 product with us. And lack of detector efficiency. We are working on detectors like CDOT. Low key rates requiring the use of AES encryption, and all practical devices are not provably secure, at least not yet. Next, please. So these are examples, for instance, of our own entangled photon source that we have benchmarked against internationally available products. We have done a much better job in terms of visibility and a whole lot of figures of merit that I have put in there. I will not go into the details. We have also made an entangled photon source in a SIGINAC configuration of very high brightness and very high quality. Next, please. So as it was already alluded to by you, the fundamental thing about not doing what everybody does, like differential phase shift keying or COW protocol, which are all passé, we have to extend the distance, rate to key distance. This can be done with advanced protocols such as measurement device independent QKD, where the device attacks can be completely prevented. And we can also double the distance because Charlie sits in between Alice and Bob. and we naturally come to a network type of protocol with those systems. So therefore, the beginning of this is to do a Bell state measurement. We have done a series of Bell state measurements as a prelude to building a MDI or a twin field. And these type of tests are absolutely essential before we can start making devices based on MDI and twin field. And they require very, very critical synchronization of the FPGA devices, timing. And so we also need quantum repeaters that are not there. Just another minute, please. I'll be through. Next, please. So that SQT stands for the thing, what we manage, School of Quantum Technology and devices made by them. This is a well-known rate to distance limitation, why we have to go to twin field. Next. So there's a message, intercity QKD with long distance and trusted node over 2000 kilometers with a Hazard number of trusted classical nodes. This is not the way to go. This is not a solution at all. Are we going to have 100 secure nodes, classical nodes, and then secure those stations? These Chinese might have done it just to show and shock and awe the world, but we don't require it as a nation. Nor is satellite QKD with just 15-minute time window. We cannot fly satellites everywhere. This is also not an impending requirement. So we have to prioritize. Next, please. So this is coming to the last but one slide. We have the treachery of images. This is a famous etching by René Marguerite. Ceci pas une pipe. It's not, of course, a pipe. We cannot load tobacco and smoke it. And the mathematical promise is very different from the physical devices that we have tried to develop. Map is not a territory. Mathematical representations are not physical objects, and hence and therefore I strongly appeal that we must have a testing standardization procedure and an institution in place before we even start funding. And everything has to be very tightly audited, certified by a group of experts before we go ahead with the subsystems to systems of systems. Next, please. So the key points, this is my last and final slide. Threat to current encryption method is not impending. We can go about it in a measured fashion. Take our steps carefully. Careful planning and calibrated approach is called for. Focus on perfecting subsystems. Free space to satellite. Before that, we have to do free space terrestrial to terrestrial. We have established a 10-kilometer link across the Kadakpasla Lake as a prelude to doing QKD with that. Then terrestrial to high altitude platform, and from terrestrial to satellite. This is the way to go. There is a learning curve. Anybody who thinks otherwise is completely wrong or misleading. Then we have get stable intra-city fiber first for 50 kilometers within a city and run it stably for a year. This is necessary for you to show your systems are stable before you take on larger challenges. At least initial 2-3 years we should do this. And then work on advanced protocols must begin now. Long distance QKD with tens of trusted nodes are impractical. Work on materials development, especially for quantum memories, is very critical. Develop photon on chip QKD because these devices need to be compact so that a technician can bang it against a wall and then do this type of QKD. Currently, the big ones are unstable in their interferometers and so on. Develop, so talk of quantum internet is absolutely premature unless you have quantum repeaters. Need for independent, rigorous technical audit and screening. I cannot overemphasize the fact because claims have to be tested, certified before further funding is done. Establish standardization and certifying processes. Do not work for low-hanging fruit, for heaven's sake. There are no low-hanging fruits. And looking at old things will only result in a museum of junk that we don't any longer need. We have to work at the frontier. It is a technology in constant flux, and we should keep up. And finally, do not rush to the press. Thank you. Thank you for your attention.
Thank you, Dr. G. Raghavan-ji. So we just heard Dr. G. Raghavan on development of quantum ecosystem, and thanks for alarming about QRNG measurement requirements. So ladies and gentlemen, our next speaker is Shri Sunil Gupta ji, Shri Sunil Gupta is a co-founder and CEO at QNU Labs, founded in 2016 through an incubator at Indian Institute of Technology, Madras. QNU Labs, based out of Bangalore, provides quantum-safe data encryption, secure key generation, and distribution solutions. Shri Sunil Gupta is a business leader and an entrepreneur with experience of more than 30 years with specialization in products and product engineering in cutting-edge technologies. So it's now Shri Sunil Gupta, please.
Good afternoon, everyone. Dr. Mittal, Secretary DOT, Ma'am Tripti, other dignitaries present here, Dr. Upadhyay, my fellow members of the dais, and friends from the industry and startups. What I'm going to do today, you've heard this whole morning session about tech, right? About how the tech is built, the pros and cons, the challenges and the issues. But what I'm going to share with you is actually what we have learned from the market, right? Having interacted with more than 150 clients, because eventually if this technology, and the title was given to me was, how do we make this tech into mainstream, right? Of course, we can build products and technology, but until unless we build real market savvy solutions, right, which are adopted by the market and implemented, then this tech would only be a investment, right? And it won't give us the return that we want. Because the eventual objective of India venturing into this tech is to make it not only India secure, right, also become the leader in providing worthy solutions to the world, right? So I'm going to take about 10-15 minutes and going to share some of the stuff that we have learned in the last few years. So just quickly, a couple of slides just to set the tone. We are an encryption economy today. Everything that we do, from messaging, video conference, payments, e-commerce, everything is digital. Encryption is the foundation of our security today. And encryption works, right? And it really gives us today, whenever we do anything and we feel secure, it's just because of encryption. Properly implemented encryption, right? Crypto systems are one of the few things that can be rely on, right? Now what happens is, this cryptography that has served us so far actually taking its last breath, right? As we know, it is vulnerable. All our current key exchange mechanisms are under the threat from quantum computing. And that is where the two attacks that people are worried about, that some of the rogue elements, hackers will store the information and then break it later. But people are more worried about also the other pending attacks, which are live session management, where if the hackers are able to get the keys, right, and they're able to create a private keys, then they would be able to generate digital certificate. They can come into any sessions that authenticate themselves, and basically the digital identity, the faulty digital identities can be created, right? And keeping that in mind, as you know that India has been working on this, US has been working on this, United States, in fact, for the first country in the world to have actually formed a law in December 2022, saying that all the federal agencies have to implement this post-quantum cryptography. They're not recommending a quantum cryptography to implement in their federal agencies. Now, but the interesting part is the world is not waiting for quantum computers to arrive. We know the quantum computers are lagging, but one day they will arrive unannounced, but the world is not waiting for that. So what is happening is there's several efforts are being made worldwide. How do we find, in the absence of quantum computers, how do we find alternate ways to break the encryption key? And one of the stuff that happened a few months ago, when a Canadian-based, a San Diego-based company actually said that using their in-memory computing, they can actually break the existing encryption key. So the world was worried about is long-term digital identities getting stolen. And the second is, how does everything that we encrypt today, how does it remain encrypted in the future, right? So these are the two key problems. And this is also the worry of world, right? Whether it's a defense, whether it's the public enterprises, or we talk about the private enterprises, right? So if you look at it, what happened is, I've just shown a picture here. And if you look at cloud service provider, Cloudflare, what they've done, they're also getting a post-quantum cryptography implemented in their cloud offering. When we look at it, messaging apps, we have seen Signal, Telegram implementing quantum secure encryption into their messaging, right? We go to the certificate authority who issues the certificates. They are actually going and now offering hybrid digital certificates, quantum certificates, as well as the fully capable quantum digital certificates. Then other important thing is the browsers, right? Browser, everybody uses browser. So now we have seen Chrome has just said that in their another version 16 is not commercially available yet, but they have also implemented in browser the post-quantum crypto libraries, which will now be used by, it will be available to a lot of people very soon. Now an HSM, right, which is again a hardware security module, is again a very important piece of security today. Now companies like Thales and others are now gone ahead and implemented post-quantum cryptography and other new techniques into their HSM offering. So you see, world over, what is happening is the people are making effort to bring quantum, right, and quantum offerings into their existing solution, because these are the solutions which everybody is going to use, right? People are not going to use QKD as a isolation or QRNG. Those will become the engines, right, and the technology behind these offerings that people use. So as I mentioned, we have been in the market for about 4 years now. We have been talking to several customers in India, in Middle East, Asia Pacific, and the US market. And what we have gathered, right, as the 4 critical themes out of all the discussions is that there are large-scale quantum networks going to be formed, right? That is very important, that people need a large-scale quantum networks, but they don't only need in the core, they need to extend that from core to the edge, right? That's very important, right? And I'm going to talk about a little bit more on each of these points. Second important point is that quantum security is for all types of data that you have, right, that are stored, right? And it is important that which client you're using, right, whatever client you're using, they should be able to connect securely, and then should be able to store the data securely. The next important point is that we can't solve the problem only of key, right, key generation, or it has to be a total solution, which means it has to spread across key generation, key distribution, and key management, right? If you're only solving a key generation, which is quantum random number generator, or a key distribution, which is QKD, if you don't solve a key management problem, then there is still a significant vulnerability that is there, right? And the last one, while we can offer several solutions in a piecemeal basis, what is eventually required is a single platform where you can offer all this key generation, key management as a services for clients to easily consume, right, as an OpEx. So how would the next generation quantum networks will look like, right? Unfortunately, I can't read. So one important part is the last mile, right? You can build networks inside, but last mile is very important, right? How do you extend a quantum security or a post-quantum security to the last mile, right? To the radios, to the access points, and whatever else end devices are. Then second is the scalable network, right? You can't just have 100 kilometers and say that I'm done. You have to extend it to 150, 200 kilometers, 300 kilometers. You have to build using the available technology, the trusted node, right? And then we had to do, of course, the quantum repeaters are not there, so we have to use trusted nodes technology today. If it's implemented correctly, then it serves the purpose. Then interoperability is very important, because the networks are not going to be isolated networks. The customers want a large area, like if it's the 5G network, if you're trying to set up, you have to deploy that across the whole network. You can't do pockets, right? So it is very important that these isolated networks eventually needs to interop, right, to create a wide area network, right? And that is very important. For that, you need to make sure that you follow standards, you do interoperability, and you build right adapters, right, that are required for large networks. And then another important part, that if you just go with this, the cost is going to be very high, right? And the cost becomes a very important factor. So thus, we have to find out a way how we can reduce the cost of the overall network. There are several ways to do that. One way is to do hub and spoke, where you can reduce the cost by about 50% of the network by creating a hub and connecting multiple spokes to that. And that is one area that, and then of course, Dr. Upadhyay talked about how do we indigenize some of the components like single photon sources, we get RF drivers, and then we do single photon detectors, right? There's another effort that we have to make. So overall cost has to come down, right? Today is the cost of a QKD network is significantly high, right? How do we do that? And then important is quantum applications, right? At the end of the day, a lot of enterprises are not going to buy boxes and technology. They're going to buy the applications, right? They're going to access applications, and those applications at application level security down to the layer 2 level security is important, right? So these are some of the, when we have talked to several customers around the world, each one of them have raised these objections, right? How do we solve these problems, right? So these are one of the picture that is there. These are how you create a long distance QKD network by using trusted nodes, right? On the top layer is a routers which delivers the key. You have to, of course, follow a ETSI standard for that. The second layer is a key management layer. It could be a separate box. It could be a layer integrated inside the QKD. QNU has built a key management layer inside the boxes. And then, of course, all the boxes you see that can be connected over 150 kilometers. We have point-to-point as a 150-kilometer QKD. And then trusted node through which we can extend it to longer distances, right? You can take it to any distance that you want. Now, another interesting part which happens is that how do you build hybrid networks, right? Hybrid networks are important because if you have to extend the key to a much longer distances, then you should be able to create a distance near site location where you can have a direct connect location of QKD, and from there you should be able to take the keys through post-quantum cryptography to cloud, and from there you can distribute the keys anywhere you want, right? So that is another area where how do you extend keys to a much longer distances. For that we have to build a hybrid networks, right? So just to summarize this, next generation networks, which are the real need in the market, requires a hybrid approach for longer distances. Quantum entropy is mentioned. Quantum entropy is very important. Is a foundation. We call it a root of trust. How do we generate real entropy and that use it in a QKD and then extend that the entropy? How do we distribute entropy for the cloud and other longer distances? Of course, the key synchronization. And then the most important part comes to the standard, right? We will not just have captive networks. These networks have to be interoperable and so on, right? So ETSI 014 interface is very important. And then versatile quantum protocol. What happens today, there are a lot of protocols that are being used. I think CDOT is using a DPS protocol. We have also used a DPS protocol for 100 kilometer. Few people have used COW protocol. Each of these protocols have different pros and cons, right? Ultimately, what you want a good balance, because based on the application, there's a trade-off between security, distance, and the key rate. So you want to use a protocol that gives you of course, security is uncompromisable, but how do you get a optimal key rate and the distance? And then there are new protocols like DPS decoy protocol, then there's a twin QKD protocol, and several protocols are coming up. And that will continue. Versatile quantum protocol will keep coming in, and the industry will keep adopting it based on the applications, but there's a continuous process. And then, of course, point-to-point networks are no more good. We have to do a different topologies. We have to do hub and spoke, and then satellite QKD, right, to take it to the longer distances. Sorry, I've just taken another 2 minutes. So, and this is just a slide to tell you about, and I mentioned about how do we create, is not only endpoint security is the biggest challenge for the industry, right? Cyber security, right? They have cloud security is a big problem, endpoint security is a big problem. So we can't just keep a quantum localized to network security. Then it will be only very small problem we will be solving. We have to extend that to laptops, any of the connecting device. So we have to have, how do we get quantum tech sitting on these endpoint devices? How do we use quantum tech to harden the OS, right? How do we use quantum tech to harden the applications, and then use that to connect to the securely connect to the data centers. And once it comes to data center, you can access any applications you want from the data center securely. But then you have to store. Like a lot of CIOs in the world are now asked, they don't buy hardware anymore. They are asked to put their workloads on the cloud. So you have to make sure that your workloads in the cloud need to be secure. How do you do that? You have to build a quantum secure vaults in the cloud, right? So that's very, very important. CDOT is anyway better. I'm showing you, we are showing that in the booth downstairs. All these solutions are like built. which we offer as a Q Shield platform, right? So what we have, so what we are doing is, in order to help clients not to buy a QRNG and QKD and all those pieces separately, we are just building on, we have just built a Q Shield platform that offers, basically the customers want either a file service, file sharing services, they want a connect service, they want a encryption as a service, or they want, other services, right? So as we go along, we'll keep adding these services. Today, this is the way we offer to our customers. And we keep improving the technology as the engines that you see in the layer, where you see QKD and QRNG, and many other things that we are integrating into this, right? And this has both a quantum cryptography and the post-quantum cryptography integrated into the lower layer. And if you see from there, we can connect any endpoints, any network, and applications. It can be on-prem as well as a cloud-based solution, right? And that is where we make it this tech a mainstream, right? When it hits the enterprise customers, customers know that I can license the enterprise platform, I can get a service as OpEx, and that is where the things will change, right? And this is what, and standards I talked about is very important. This is a TEC team. DDG was here, and the team that has been doing our TEC testing that has just completed a CUNY Labs. Very important for us to, it's very good that India has built its own standards released by TEC last year, and now we are getting a certifications using that. That will go a very long way for us, for people to build trust in what we have built. Is not just a tech, it's something that is past the standards and go forward. Thank you very much.
Thank you, Dr. Sunil Gupta ji. Ladies and gentlemen, our next speaker is Sri A. Robert J. Ravi. Mr. A. Robert Ravi ji is an Indian Telecommunications Service Officer of the Department of Telecommunications. He is a gold medalist in engineering from the Pondicherry University and MBA in International Business. He is presently working as Deputy Director General, Standards, R&D and Innovation, spearheading the policy and implementation aspects related to emerging technologies. So now, Sri A. Robert J. Ravi.
Thank you. Respected Secretary, DOT, members of the DCC, and my colleagues from the DOT and the TEC, ladies and gentlemen. Again, a warm welcome to this Quantum Conclave, a very important conclave which we are going to discuss a lot on technology as well as part of the policy initiatives. The topic what we are going to discuss something about what is going to be the quantum ecosystem that needs to be developed. DOT has been actively supporting this cause in the last couple of years. We have funded more than 4 startups on quantum. And I'm glad to say that one of the quantum which DOT funded is also coming up with offering quantum computing as a service shortly. That's with 25 qubits. So we are really into it. The purpose, of course, I'm not going to talk much of technology. What purpose of my talk is going to be just putting thoughts. What are the initiatives we need to take up? And DOT is willing to take the step forward and as we go forward to ensure that we set the trend, not for the country, even for the world. So in that context, standardization and the technology needs to go hand in hand, and I'm glad TSDSC also, we have a working group which exactly does a lot of initiatives on quantum. We are also working on quantum standards coming up. Just to give a quick information, we all know that the quantum information process itself is tangled on 2 essential ingredients, the superinsertion and the entanglement. What I'm going to touch much, because people have been talking more on QKD, I'm not going to touch QKD because we are going to go the next step, what we can think forward. Can we think something about quantum teleportation communication networks, wormhole teleportation networks? Can we think something big about how we can take the communication network to the next level? So on the superposition, as we already know that we talk about bits and qubits, we are also talking about qubits. You know, the bits talks about 2, so we talk about qubits, which is nothing but what we have the cosmic resonance in 11 dimensions. Can we have different states from the qubit taken to qubit? That's again a study and research going on. Can we do that? This will enable real quantum entanglement for the security in a greater deal. Not only for the security, it runs a lot of applications. We can do digital twins, simulation. We can bring the real data about using status, sensors, etc., on a common data analytic thing, and we can do real-time analysis on the field. That could be done using such quantum entanglement, which will be a real power. And the real use of the Planck energy use, because we know the break-even really happens when that actually comes in. Of course, we know that a lot of theories are going on. How do we create and control this quantum ecosystem? Of course, a few are really promising, but I will strongly encourage the ecosystem, because as Professor Sur was also mentioning in the morning, we need to think something different. It's not required that always we go on a, say, photonic-based system or a single source detector. For example, the other day I was in IIC Bangalore. The professors are working on, say, a photon detector sensor, which we can bring it on room temperature. So simultaneously, recently I went to Trivandrum. Already they have a room temperature beam, laser beam sensor, which they can demonstrate on quantum entanglement. So we need to really think about what is the different options available. Can we do something on superconductor base? Or could be based on semiconductors, molecules, atoms, photonics. Acoustics is a very, very interesting area that's coming up, which this is a real maybe a game changer, where we call about linear mechanical computing, where we are not the photons, so phonons. Can these phonons be emitted and detectors? How do you bring this phase control? Can we not use the beam splitter? The beam splitter, especially the Hong model, which actually talks about, if you see that, how do we put a single phonon in and then bring in an entangled dual path photon out using a symbol, using the effects of phonon. That's what we call the Hong model. This is another aspect which is also coming on this. Even some work is going on semiconductor technology-based quantum scalable. So this, can we use one electron spin or one new nuclear spin, which could be used using purely on silicon carbide. So this is finding a lot of applications in your 5G and your SAT communication, especially because of its record-breaking lifetimes. The coherence time for some of these products has been increased tremendously. Now we are seeing a coherence time of greater than 5 seconds, which will be really, really useful for all our communication requirements. So that's where the quantum scalable semiconductor technology is going to play a real vital role. Another new area that is really emerging is the photonic green banner, what we call the GHZ, where we can entangle the photons and then using a fiber cable. It has been tested for around 1 meter of cable. Can we use such a technology to take it far away? Because our ultimate idea is, can we cover, how long are the distances are we going to cover? These are some of the technologies again coming. If you see here, again, here we are using a 3-bit. There's actually it's a 3 qubit. Suppose we are going to go on a qubit, you can again change into maybe 4, 5, which is going to have your capacity of a quantum throughput also increase in a tremendous way. So with this, I think already we know that the quantum networks are rare. We need to secure the network. Can we not do security in the cloud? Can we not have, another very critical component is synchronization. Can we bring in this synchronization into it? What type of quantum sensors we can bring? We are also talking about quantum gates. These are new areas of development. With this, if we see a stage of this quantum network itself, what is happening? We talk about, say, from the trusted repeater, what are the applications that we are, how do you prepare and measure? Can we do a real secure identification? And the entanglement generation, the quantum memory, etc. The last one, very important, was the quantum computing. If you see that, can we even do what we call the Byzantine agreement, could also be in one of the key applications. So these stages of quantum network is also going on. I request the startups to also think in a few of these areas, especially in the communication front. And as far the application is concerned, we know it's widespread. We have the entire spectrum available. A key 2-3 thing which is of interest, which I had also personally worked, is of interest. We can see that a lot of work is going on in modeling of health. One concept is this, what we can see here is the AI modeling in health. All this is happening because of your supervised and unsupervised learning. So with so much of amount of data, can we not do a real-time analysis? What we have, the quantum-based, quantum supervised layer, or the quantum learning type, which could also be one of the key things, where a simple interface of, it looks, but this could not be easily done on a classical computing. Can we not take it to the quantum level? This is one of the key research areas. Other very important areas on the communication front is we are talking about digital immortality. So where we can the entire thought process, maybe for example, tomorrow we can walk into a library and then we can even have a digital talk with Mahatma Gandhi with completely digitized immortality. So what will be his thought? Suppose if somebody, if I ask a question today to Mahatma Gandhi, what will be his response? Such things could also be done. So that amount of data generation requires real computing. And the last other one of the use case I want to touch is on the poverty level. You know that there's always say people are not going hungry because there's no food, because it's not properly managed. We did a lot of exercise because this was one of the area which I was previously working on in the African continent, where we use large amount of data on satellite. Satellite information where the maps on the day map and the night map used to be run on an AI algorithm, and then be able to predict what is the extent of poverty. This could be easily achieved in quantum. So what I request is startups to really come up with new approaches to address the critical needs of the society. When you go into the approaches, we talk about, the commonly talked approach is what? We talk about, okay, can I do a ground-based? Okay, we talk about Arise, and then we say Bob, then we try to insert Charlie, then we try to increase the distances. In this process, what is happening? We need to have quantum repeaters. What are the challenges in quantum repeaters? These quantum repeaters are challenged because, you know, the content state could not be cloned. So you cannot save this and then repeat it. You need to have another technology. So that brings in what we call quantum memories. Different memories. Can I take crystal, take the nitron alone, and then I can put one electron and then make it as a repeater or a memory. So this is another advancement. This is one solution which has been talked, which is having its ifs and buts. Again, as the morning the speaker was mentioning, that the existing fiber optic cable will not take, because it will be 657. Can we do 655? Which version of the fiber is going to that? We are going to have real challenges there. That's one area which we should think. Another area of approach is, can I combine fiber optics with satellite to a certain extent? That was called satellite-based quantum links. So we are also thinking seriously. I think we are in talks with a few startups. I think a startup called Skyroot, which is also doing a lot of work in satellites. So can we not build our own quantum-based satellite, put it to the, and then we can see how it works. That is also one of the areas we think. I would also request, apart from all this, it's a completely new approach coming up, what we call the vacuum beam guide. So it does not require fiber, it does not require satellite. It's just a simple vacuum pipe where you put lenses, through the lenses you transmit, and you can achieve large capacity up to even 10 terahertz per qubit bits per second, and even we can do it up to 10,000 kilometers, which is what we want to, if you want to do a real quantum communication. This is one particular area which really I request the startups to have a look at it, because this is the area right now being worked only in 1 or 2 countries. Yeah, of course, US is doing a lot of work in this vacuum guide. They already built one network on vacuum beam guide. So that is going to be the future. I already mentioned this quantum repeater, what are the issue we have, because even the moment we touch even 20 kilometers, we have a big problem with fiber losses. And that is going to affect my quantum repeater. So that, how are we going to take care of this operation errors is going to be a challenge. So one hand, I think the startups should think on different things. One hand, how we can go on the quantum regular one and the quantum repeaters memory. Other hand, you go on the satellite. Other than new approaches, completely think of different new approaches, like what I was talking about, the vacuum beam structure, which is completely ground-based vacuum. It's just a simple pipe, made about, what is maybe a oxygen-free pipe that is from the outer environment. And then you have reduced your hair or a medium. No need to be exactly 1 PA for a complete vacuum. It could be little reduced air sources available. And this will help in less loss of optical confinement. This one area I would request the startups. And this is the area where we are also trying to push in a lot. This is going to really help us in a long distance communication networks. And the other one which people are also talking much is on the free space quantum thing also, where we know that we take an entangled photon as a source, and then one you give it to one area, the other source you again amplify it through a beacon beam and then push it to a dichroic mirror, and the other end you have a free steering mirror which captures it and then detects it. So this is another, but the problem in free space, again you have some issues on the distances. How are we going to have the repeaters? So there's another area which we need to really think of. And once you start building it, a combination of the land-based quantum fiber optics, satellite-based, and vacuum is going to help in what we call an entangled-based free space plus a mixed network, which will become a trusted network in optics. Another new area which I would think strongly we should discuss, what I think Professor was also mentioning, because a lot of thoughts are going on whether it is secure or etc. Fully development on an on-chip photogenic turnkey quantum source is again a very, very important one. The advantages of it, in a chip you can easily build, not the qubit, you can even go qubit. Even the qubit state generation could be easily made using this thing, and already a lot of research is going on in this particular area. This is a small dream what we think of doing it in our country. So can we plan some sort of a large-scale quantum network using local fibers? So it's going to be based on a vacuum beam guide. That's what we can say. The key cities of Delhi, Bombay, Chennai is going to all be connected on the VBG, what we call it. And then at every city, we are going to pan it out and then use the local fibers that is available there. And then we put a quantum terminal. Each one will have a quantum terminal and then a quantum repeater. That is on one side at each city, whereas intercity is going to be on VBG. So can we not do it? And add this a bit to a bit of satellite also. So suppose we take the inner integrated thing, can I also put satellite it for a short distances? So a mix of satellite-based quantum also to be added here. The other important thing which we are also talking about, DOT has funded a number of own indigenous RAN operators. So can we not use this as an opportunity when they build the L2, L3 algorithm, when they have the L1, the L2, L3 algorithm, the L2, L3, can they not build this quantum thing also? So that any phone with a small chip built into your phone could become a secure network, especially when 5G and 6G coming in. 6G is more of going to be an open platform site where security is going to be, again, a big challenge coming in. So building a quantum secure network through quantum, because since of our indigenous providers available, it will be a great challenge and it will be easy for us. With this, the 6G has thrown up really, really new areas. Now we know on one hand we have this quantum learning, the machine learning available. So what are the machine learning? Artificial neural networks, the K-factor neural networks, the space vector machines, what we talk about, reinforcement of this Q learning, etc. So these are all going to be the different algorithms that is already built in Q learning. On the quantum computing side, we are now talking about platforms available, nodes, circuits, your fog computing, tensor processing units, all are all built up. So we think both of these need to marry in the near future, maybe in a few years, where we can build in, as I mentioned, in applications like health, we go into what we call a quantum supervised learning, quantum unsupervised learning, a quantum reinforcement learning, quantum neural networks, quantum deep learning, quantum deep neural networks. This is going to be the future. This is all some of the areas also which we nearly need to do in terms of real challenges. The last slide, which I wanted to just not talk more on it, is the next level of what we talk about, the quantum teleportation. Quantum teleportation says that we can transform information through long distances, irrespective of the distance, if the photons are entangled. The next towards it is what we call the worm world teleportation. So can we not create an imaginary worm world from one area to another area and then do the transportation happening? That is again on communication. So this is what we call quantum tunneling in phase. And this is going to be a real game changer when it comes. So which means irrespective of distances, you will be able to transfer huge amount of data at one place to another place. With that, I think we know that all this cannot be done without massive collaboration effort from all of you. We request DOT that to support with even funding, technology. We have the TACs available to come out with standardizations. We have the TSTAC also to work on different working groups. We'll give all support. Please, the industry, the academia, please come forward so that we all collaborate and then see that we take really a leader. We should become leader in this particular sphere for the world. So to summarize, what should be our way forward? We should, first key thing is identify the standardization gaps, enhance the participation, do the standard development process, help the quantum communication related activities. And as I was mentioning it for the country, can we start something like a vacuum beam guide quantum teleportation network, experimenting? Let us take between two cities, we are planning between Delhi, Bombay. And then can we establish the first quantum satellite? That will be a real true game changer again in the quantum side. And then we talk about real secure network on the quantum phone itself. And of course, on the worm wall, very little research is going on in the country today. Of course, again, Japan, China, and US, a lot of research. Can we do some accelerated research on wormhole related teleportation? And of course, establishment of testing, certification, feasibility. And once we make this for the entire thing available, we would like to open up this as an R&D, as infrastructure. To quote it, we are now in discussion with the Department of Science and Technology. We are going to set up a quantum lab in Guwahati. So we are going to put some of the test beds there and then ensure that this lab is functioning. And this will be thrown up again. Once the lab is set, we build the ecosystem. The ecosystem comes, so any R&D you want to do, you can always build it. So we are trying to build in complete synergy between all the stakeholders so that we have a complete end-to-end ecosystem. I'm very sure with all your support and the support from the government of India is offering in a large way, we will be definitely become leaders in this quantum field. Thank you for the time and the patient listening. Thank you.
Thank you, Shri Robert J. Raviji, for speaking on development of quantum ecosystem. And now, ladies and gentlemen, we are joined virtually by Dr. Oscar Dees from European Commission. To tell you about Dr. Oscar Dees, he is the head of quantum technologies at the European Commission, the executive branch of the European Union. Previously, Dr. Dees was head of data center at the European Medicines Agency, that is EMA, in London. He holds a PhD in computer science from Universidad Politecnica in Madrid, and a master's degree in open e-government from the University of Stockholm. He's also adjunct professor at our University in Madrid. So we have with us Dr. Oscar Dees. We welcome you, sir. Can we have Dr. Oscar on screen, please? Okay. As I've been told, there is a connectivity issue, so we'll wait for 2 minutes.
Hi, good afternoon.
Hello.
Okay, my understanding is that you can hear me. Hi, good afternoon, and many thanks for inviting me to this event. My understanding is that you can see the screen. Okay, so let me, good afternoon, and let me start with the presentation. My name is Oscar Diaz. I'm the head of quantum computing at the European Commission. And in our unit, we are working in both high-performance computing and quantum technologies, is taking care of these two parts. And I will talk today about the strategy, the EU, on the initiatives that we currently have and we had in the past for promoting both the development and the research and also the deployment of quantum technologies. So let me start giving you an overview of what are the main activities that we are currently doing. So this this image is showing on the left side the flagship. That is one of the main activities that we have. The flagship, the quantum flagship, is a 10-year project, and the idea here is to bring technologies from lab to market. Here we are talking about research and development, so it's mainly focused, is funding projects on the 4 pillars of quantum technologies, the 4 main pillars, and also on everything that is related to technological supply for quantum technologies. And this is going for TRL levels, normally from 1 to 6, 7. So it's basically focusing on research and development. This is funding with a program that is called Horizon Europe. And as I said, it's a 10-year strategy that started in 2018, and it's around 1 billion euro project. Going to the right, we focus, so we move from research-based initiatives to infrastructure initiatives. This is what we call Digital Euro program, and here what we have, it's basically deployment of infrastructures. Here we have, you can see there on the right side, you can see different, like 3 different initiatives that we are currently running. One is the Euro QCI, that is focused on build and deploy during the next years a certified secure pan-European end-to-end QCI. This will be focused on cybersecurity services, both so it will be also for private and for the EU, for public services, and this is based mainly on QKD infrastructure. Here also we are working with PQC, but this project is focused on QKD. I will talk about this a little bit later. Also, we have another project for deployment infrastructure that is called EuroQCS. And here what we are trying to do is to build and deploy an infrastructure of quantum computers and quantum simulators that we integrate with supercomputers, with a network of supercomputers that we currently have built at the European level. And another project that we have that is also related to high TRL and moving more to market, it's the European Chips Act. Here you have probably heard about it. There are different pillars where we are providing funding for creating fabrication and commercialization of standard chips, and there is a big important part that is focused on quantum chips. And you can see in the top these 3 documents that we have published. The first one is the strategic research agenda. This is a document that we published a few years ago, and it has a plan, an agenda, a roadmap for the activities that we need to do at European level. This includes research and also deployment. But it's focused mainly on research. This is public, it's a public document, it's a big document, and I think it was published a few years ago, the latest version. Together with that, we have published, and it's also public, everybody can access, key performance indicators for all the quantum technologies. So for each quantum technology, you have a key performance indicator that we will measure, and we are providing a new version of the measures every year. And the last document that it was published yesterday is the Strategic Research and Industry Agenda. This is a document that I invite all of you to have a look, because there you will see in one document, it's a big document, it's 100 and something, 50 pages, I think a little bit more, but it has for all the pillars, all the information of what we are going to do in the next 3 years and 6 years. So normally we divide all the actions between let's say a short, medium-term plan and a medium, long-term plan that is around 6 years. And you can go for all the different pillars that we have, like for example for quantum communications, and see what we are going to work on the next 3 and 6 years. So let me move a little bit more into detail, just to let you know, and this is the picture before, it was giving you a kind of overview of what are activities that we are doing. This is more or less how they are linked. So as you can see, the quantum flagship, that it's the funding that we are putting in, let's say, in more basic research, is used to as an input for other projects, especially for deployment. So the idea is that we could use the research that has been done in Europe in order to deploy deploy and commercialize that research. So, for example, I will give you an example. Euro HPC. This is a joint undertaking that we have on supercomputers, and what we are doing here is we are procuring quantum computers and quantum simulators that have been created as part of the quantum flagship. It's not mandatory, but this is one of the things that we are doing. Here, so just to let you know, I said before that we started in 2018. We started with a set of projects. We have projects, as I said, in all pillars, in quantum computers, in quantum simulators, telecommunications or quantum communications, and quantum sensing and metrology. And these are some of the projects that we had during the first, what we call the ramp-up phase that we finished last year. There is a report where it is providing information about what has been done in all these projects, and we have also projects on software and a lot of more projects that are not here on basic science. So this was a big success. You can see, I don't know, for example, projects like Pasquans that have been the embryo of the current companies, as for example Pascal, that they are currently one of the big names in quantum simulation in Europe and in the world. So and the same also for quantum communications. For example, we have projects like Civic, or that they have the majority of the big players now in quantum communications in Europe. So let me go. I will go very brief through the different pillars. So first, quantum computing and simulation. Here, what we have is that we are focusing in all the. For the moment, we don't know what are the technologies that will be the winners. We believe even that there will be different technologies. So what we are doing currently is funding all the technologies on superconducting qubits. We have the biggest projects that we have currently is Open SuperQ Plus. Where we have the majority of the vendors of superconducted qubits in Europe. On neutral atoms, we have the follow-up. We have Eureka, but we have also the follow-up of Pasquans that is called Pasquans 2. Just to let you know that all these projects are long projects, are with big funding. We are talking about more or less 7 years per project. We have also photonics that is starting now. I think it's starting this month, and we have also MB centers and spin qubits. So just to let you know, as I said, the previous one in our project it was more development. Now we are doing the same for deployment, for procurement. So in this case, the procurement and the deployment project, the deployment of infrastructure that we have is this project where we have procuring quantum computers and quantum simulators. We have currently 6 hosting sites. Well, in fact, it's 8 because this is 6 for quantum computers. We have another 2 that we have installed for quantum simulators, and they will be installed together with the supercomputers. The idea is to connect them and permit all the different the different researchers in Europe to have access to these computers, these quantum computers. One thing that also we are working on quantum computer simulation is currently open. This is a call you have here, the link that is open, that is for what we call the European Quantum Excellence Centers, where we are going to focus on software that we will develop, and we will do this together with industry, integrating it with the supercomputers. And we are continuing working here on quantum computer simulation. We are working on the benchmarking of the quantum computer. We are going to launch a call very soon, and also in the middleware, everything that is related to middleware and the integration of supercomputers, classical computers and quantum computers, and we will continue also with calls also on quantum computer applications. So we move now to quantum communication. Here we have the targets for the next year. It will be to further develop the protocols that we are using there, and specific use cases more than the one that initially we have, especially with QKD. Also, realize a full stack prototype network and establish a European platform for the development of quantum communication technologies. So here we have, as before, we have different projects on the, let's say, research, on the development. Here you can see a few. I will not go too much into detail. You can see that one of them, probably the main projects that we have there is Kia. That is basically, so we have one of the success that we have recently was a proof of concept of a quantum network with 3 nodes. So we have three quantum computers connected. And we have also projects like QRange or Civic. This is from the ramp-up phase. And the follow-up, the ones that we are doing now, is the second, is a 7-year project for the follow-up of Kia, and that is focusing on quantum internet, and the 7-year projects that we started also for QSMP, that this is for QKD. So this is to continue developing the QKD. And we have also another, a smaller project that we are focusing on entangled photons for long-distance space communication. This was on quantum communication, the development. So the same thing in all. So we are doing development. We continue to do research. We are also doing deployment of quantum technologies. In this case, for deployment, we have a big project. This is a project that is encapsulating a big number of projects that is called EuroQCI. That is basically, the idea here is to have an integrated satellite and terrestrial QKD infrastructure that it will go through all the EU. And for the moment, at the beginning, one of the first use cases, it will be the exchange of cryptographic keys. And it will be part of a bigger project that is basically the EU Security Connectivity Program, or IRIS2, or IRIS2. Here, the deployment we have, as I said, we have two main parts. The terrestrial segment, here we have 6 industrial, so that we are doing with the industry projects, and 26, one for each member state, national project. So it's at national level, each country has a project to develop the QKD network, and we have later different projects that we will connect all of them. That is the project that you see there. That is the theft project called for cross-border connections. And also we are doing also the specific projects for procurement, all the QKD, the testing, and also provide evaluation for that equipment. And on the space part that we are doing with the ESA, with the European Space Agency, we have the first part of the project is called Eagle One, and later we have a long term that is more than 10 years project that is part of SAGA. On quantum sensing, it's similar. I'm not going to go too much into detail here. There are multiple projects that we are focusing on development and research, and you can see there so a few examples. And also we are now doing, until now we were not but we are now starting with the deployment of quantum sensing infrastructure. And we started with 2 examples. One is a network of quantum gravimeters. This is a call that it will be launched in the next, I think, 2 months. And the same for a hyperpolarization-based MRI, that this is going to be on first on clinical trials for the hyperpolarization-based MRI, quantum MRIs. Just to give you a quick overview, also we are working very closely on the standardization activities. This is something that we need to do. I will not go here too much into detail. Just to let you know that we have has been in 2023. It was established the technical Joint Technical Committee 22 for Sense and Elec that is focused on quantum. And also to let you know that we have a rolling plan for ICT standardization. This is something that is done at European Commission level, where last year, we included a specific focus on quantum technologies. So we have basically a chapter that is dedicated also to quantum technologies. A very brief, this will be a few seconds just on CHIPS Act. We are focusing, this is a very big initiative. We are on quantum. We are focusing mainly on Pillar 1. That is basically the one that is for established technological capacity building on quantum chips, or basically for pilot lines. One of the things that you need to know here that we have a huge base. This is a little bit different from the standard pilot lines that we have, for example, in standard semiconductors, because here we are talking about different technologies, also different use cases, different pillars. So we have we need to take into account all these cases. I put this here. This is also we have published. This is the roadmap that we have done for the quantum in the CHIPS Act. This is a long-term initiative until 2030. We have started. We have now the part that we have on top is currently currently running. So the first Q pilot and Q test. These are the name of the two projects where we have 20 pre-commercial use cases, and we are doing this with also with customers. And we are now working on establishing what we call the stability pilot lines. We will start with specific use cases on quantum chips, and we are also will provide a basic design tools and advanced design tools for this type of quantum chips. And with this, I will finish just to let you know that we are now working on the EQTC 2024. So if you are really want to know a little bit more what we are doing in Europe, I will recommend for you to join us there. We have this year, it will be in Lisbon, and it will be in November, and I think it has been currently published, the dates. And with that, I invite you now to, if you have more questions or whatever, you can contact me, or you can also go to our website, qt.eu, where you have all this information and more information there. Thank you very much for everything. Thank you. Bye.
Thank you, Dr. Oscar Dice, for joining us and sharing on development of quantum ecosystem. Thank you so very much. Thank you. So now, ladies and gentlemen, although you all know that we are running late, but then any one question from your side, if you just want to ask. Yeah. Yeah, please. Okay.
Hello, sir. This is Venkatraman from IIT Madras Pravartak Technologies Foundation. My simple kind of a question that I wanted to ask Raghavan sir. So this is about, so we have this, in the classical thing, we have this physically uncontrollable function. So do we have a quantum uncontrollable function, and that could be harnessed for, you know, whatever problems that we are talking about? I mean, I don't want to get into the depth of it.
But am I audible from here?
Yes, sir.
Yeah, that's an excellent question. We try to see whether there is a quantum analog, possibly with continuous variable methods. We tried something with OM states, orbital angular momentum states. It is possible that such signatures can be created, but we have not explored that deeply, and I think that's one open area that's worth investigating.
So just to add, I mean, it is just all about, you know, harnessing the Hamming distance between things. So I just
yeah, in theory, but see, practical implementation has a lot of problems. With wave states, the major problem comes from distance limitations. But it is one way where, without any keys being transacted, you can still successfully encrypt and decrypt. It is an interesting problem to look at, but I know no technological approaches that are being done till now. I mean, my knowledge may be incomplete, but as of now, I don't think there are any such solutions.
just, yeah.
Okay. Thank you for the question.
Yeah.
Okay.
Hello.
So, who's this by the way?
This one.
Okay.
Namaskar. Actually, I just want to tell Dr. Ekta Kapoor, who is doing in Department of Science and Technology, that we are only looking at the Western Shastras, Western articles. But in basic science, there are a lot of materials which is available for quantum communication and quantum technology. So I will request Department of Science and Technology to organize something where this basic science related quantum things also can be discussed. Thank you.
Sure, sir. Noted, and we'll take this up. Thank you.
Thank you, ma'am. And may now request Shri V.K. Roy ji, DDG Radio Tech, to kindly felicitate our speakers. Yeah, of course. I'll request Shri V.K. Roy ji to first felicitate, yeah. Have you come? Yeah, by presenting a memento, please. Dr. Rajkumar Upadhyay ji. May I request Mr. Roy to kindly felicitate Dr. Ekta Kapoor ji by presenting a memento to her. Mr. Roy, please present a memento to Dr. G. Raghavan ji. We have Shri Sunil Gupta ji. So I'm requesting Shri V.K. Roy ji to kindly present a memento to Shri Sunil Gupta ji. And of course, we have Shri A. Robert J. Ravi ji. Thank you, Mr. Roy. And we thank all our speakers. Thank you so much. Yeah, sure. And we would also like to thank our secretary, sir, Dr. Neeraj Mittal ji, because he remained with us all throughout the session. We are thankful to you, sir, also. Now, ladies and gentlemen, we have a lunch break actually, but a humble request to all of you, kindly please, try to join in by 2:30 because as you know, post-lunch we have 2 more sessions to go. So please bear with us. So come by 2:30. Thank you so much. Thank you for now.
Like you said, you have the entire report on sources. Thank you. You have this field implemented? No, I was the first one to propose FDA about 6 years back. In India, we have developed already. Yeah, so.
Center in collaboration with CDOT and TSDSI. So before lunch break, we had a session on development of quantum ecosystem. And now our next session is on advancements in quantum key distribution. Our speakers of this session are Dr. Joy Ghosh. May I request Dr. Joy Ghosh to kindly join us on the stage, please, ma'am. Dr. Joy Ghosh from IIT Delhi. We have Dr. Anirban Pathak from JP Institute of Information Technology, Noida. I am requesting Dr. Anirban Pathak ji to kindly join us onto the dais. Our third speaker is Dr. Prabha Mandayam from IIT Madras. Ma'am, I am requesting you to kindly join us onto the dais, please. And we have Dr. Sushil Majumdar from TIFR Mumbai. So I am requesting Dr. Sushil Majumdar ji to kindly join us onto the dais, please. So we welcome all our speakers. Can we have a huge round of applause for all our speakers, please? Thank you. But first, we are going to start with Dr. Soumya Das, who is joining us from Netherlands. And to tell you about Dr. Soumya Das, he is a quantum communication expert, currently serves as a postdoctoral researcher at Eindhoven University of Technology, contributing to the Quantum Delta NL project funded by Netherlands government. He is PhD in quantum computation, information and cryptography from the Indian Statistical Institute, Kolkata. Dr. Soumya Das focuses on quantum communication and security in his current research. So we have with us Dr. Soumya Das ji. Dr. Soumya Das, we welcome you in this session.
Hello. Hello.
Yeah, Dr. Das.
Can you see the screen?
Welcome to the session. Can you hear us?
Yes. Can you see the screen?
Yeah, please, please.
Okay. So, thank you for your kind introduction. So, this is Soumya. So, I am working as a postdoc and Netherlands Quantum Delta NL project. So, first of all, I would like to thank the organizer for inviting me here, and I'm honored to present my talk on navigating the landscape of continuous variable quantum key distribution, recent progress and open challenges. So I will start with a brief introduction of quantum cryptography, the core aspect of CBQKD system. Then we'll explore the CBQKD theoretical challenges and implementation details of the CBQKD system. And then we will share some insights of the CBQKD work at Eindhoven University of Technology. And finally, I will share quantum communication work in Netherlands and what India is doing in CBQKD with some references. So a brief introduction to cryptography. We know that communication, if that is public between Alice and Bob, then no cryptography is needed. If the communication is secret, then attacker can hack this information, so we need cryptography. Now, if the communication between Alice and Bob can be done in two ways, so if they can encrypt and decrypt their information using same key, that is known as symmetric cryptography, and
if they use different key, that is known as public key or asymmetric key cryptography. Now, Peter Shor in 1994 has shown that using a quantum computer, this public key crypto
Dr.
system
Das, I'm
can be
extremely
broken.
sorry. My apologies. Actually, I'm interjecting in between, but your screen is not visible, so I've been asked to actually share your PPT, please, once again. Thank you.
Okay.
Okay. Yeah.
You can see the screen now?
Yeah, it's quite visible, but then it's not changing actually. The slides, the PPT is not changing.
Is it changing now?
I'm afraid it's still the same. If you can just communicate and help with it.
Sir, please start sharing your screen. Start sharing your screen, please.
Okay.
It is uploaded, sir. He is not sharing his screen actually. It is preloaded screen actually. Yeah, sir, please don't stop share. Don't press stop share. Yeah, that's better, sir.
Okay.
Please. Now, whatever you will do, it will be visible to us. Yeah, it's fine, sir. Thank you.
Now it's clear?
It's clear, sir. Thank you.
Okay, thank you. Sorry for the disturbance from my side. Let's start once again. So this is Soumya. So I'm working as a postdoc in Eindhoven University of Technology. So I welcome you all to this session of navigating the landscape of quantum key distribution system, recent progress and open challenges. So I will briefly introduce what is quantum key distribution, what is the CVQKD system, the theoretical challenges, implementation details, what we are doing in CVQKD at TUE, and the quantum communication system in Netherlands, and finally some references. Okay. So a brief introduction to cryptography. So as we know that Alice and Bob, they can communicate the public information, then no cryptography is needed. If they share some secret information, then we need cryptography. Okay. Now, as we know that this can be done in two ways. If Alice and Bob uses the same key, then that is known as a symmetric key cryptography, that is previously shared key. If they use different key, then it is asymmetric key cryptography. Now, Peter Shor, as we know in 1994, has shown that using a quantum computer, they can break the public key crypto system. So, we can use either post-quantum cryptography to secure our system or quantum key distribution. Now, quantum key distribution can be done in again two ways. One is discrete variable approach, one is the continuous variable approach. Okay. Now, why CVQKT? So, we have DVQKT and PQC. In PQC, we have computational security. In DVQKT, we have information theoretic security. For PQC, we have high speed, whereas DVQKT is low speed. PQC low cost, DVQKT high cost. PQC is compatible with our current classical system, whereas DVQKT is very incompatible as it requires single photon detector and a single photon source, which is inherently very costly. And finally, the distance allowance. So DVQKD is short distance, whereas PQC is long. Now, where stands this CVQKD? CVQKD takes all the advantages from DVQKD and PQC in terms of it is information theoretic secure, high speed, low cost, compatible with current infrastructure. But one of the issue in obviously CVQKD, it is short distance, but recently our group has a result that CVQKD can go for arbitrary distance that I will share later. Now, what is DVQKT? As we know that in DVQKT, the qubits can be realized in photon polarization, electron spin, or electronic states of atom, which is based on the no cloning theorem. Where in CVQKT, it is based on the Heisenberg-Isensky principle. So in CVQKT, we encrypt information in the phase and amplitude of a coherent pulse, where the short noise is the inherent noise of this coherent pulse and the excess noise is what we measure at the receiver end. So this is CVQKT is in terms of communication using noise. Now, what are the components of a CVQKT system? So, major components is obviously laser, which can be pulse or continuous wave. Then we apply some modulation. So, modulation can be either Gaussian or discrete. Then we can have transmitter monitoring, which is source or injected light. Now, this information is sent from Alice to Bob using optical fiber or free space communication. Then at Bob end, it have a receiver monitoring, which can be again local oscillator or injected light. Then Bob can apply demodulation, which can be either synchronization or optical compensation. Then it can have a detection, which is homodyne or heterodyne. Now Alice and Bob can have the classical post-processing using authenticated classical channel. So previous one was quantum channel. This is classical channel. So Bob can apply shifting if they have used the homodyne measurement. Okay. For heterodyne, this step is not needed. Then they apply a parameter estimation, which is just discarding some data and estimating the parameter of the channel. Then they apply error correction, which is either LDBC, turbo, or some other code. And finally, the privacy amplification, that is hashing. And after that, Alice and Bob have the raw key. Now, in this scenario, as what will be a simple attack model? Okay, so Alice and Bob is communicating, and attacker can generate an EPR pair, entangled pair, and he can mix with Alice's signal, and again using a beam splitter, he can take some portion of the signal and some portion of the EPR pair goes to Bob, so that finally the data that attacker has, that is correlated with some Bob's data, and Bob's data is also correlated with attacker. So in this way, attacker can gain some information without being detected at Bob end. Now, in theoretical development of CVQKD starts from 1999, where the first proposal using quadrature has been proposed. In 2005, in between 2001 and 5, we have CVQKD using Gaussian state, that is the famous GG02 protocol, and we also have reverse reconciliation and no switching protocol. In 2005 and 9, we have asymptotic collective attack, multi-dimensional reconciliation, and finite size analysis. In between 2013 and 15, scientists have developed MDI protocol, finite size effect, and first composable security proof. In recent year, in between 17 to 21, the Gaussian definitely reduction asymptotic collective for 256 QOM and short noise calibration, and finally in 2023, point to point and multi-point protocol has developed. Now comes the real issue, what are the theoretical challenges? Okay, most theoretical challenge in CVQKD domain is the security analysis. Why? Because security analysis is dependent on several parameters. First, what is the state you are using? It is coherent state, squeeze state, or thermal state. Second, what are the modulation techniques we are using? Is it continuous variable or a discrete variable? Third, the measurement we are using. Is it a homodyne measurement or heterodyne measurement? And the type of protocol we are using. It is a one-way, two-way, or measurement device independent. And we have some tools for security analysis, that is the uncertainty principle, linear semi-definite programming, non-linear semi-definite programming, or entangled photon pair. Now, if we use Gaussian modulation, the implementation is very challenging, but the security proof is feasible. We have composable security proof. But if we use discrete modulation, such as BPSK, QPSK, 64 QOM, 256 QOM, and we can increase the number of QOM, that is quadrature amplitude modulation. Now, as we increase from BPSK to 256, the implementation becomes more challenging. But the security proof, the implementation is challenging, but the security proof is feasible, right? For BPSK, say the implementation is feasible, but the security proof is very challenging. But as we increase the number of QM, the implementation becomes very challenging, but the security proof is feasible. Next challenge is designing a very good error correction code. Traditionally, what most of the people is uses LDVC code. There is other option as turbo code, polar code, raptor code, and finally, that is our team developed a simple random code book, which shows that if we use this type of code, the limitation of the distance that I tell above is lifted, right? I will tell you later for this one. And using this code, what we will do, we will calculate different properties such as SNR, signal to noise ratio, frame error rate, reconciliation efficiency, and secret key rate. Now, what are the state of the art? We know that in lab system, so it is achieved like up to 202 kilometer, and the key rate is 6 PPS, that is in China, and 100 kilometer is also from China, and France is also doing some lab test. In field demonstration, 50 kilometer again done by China and 17 kilometer by France, and for chip-based system, 50 kilometer again by China, right? Now, what all this implementation, what is again the real challenge of implementation to make a real-time system, such as the post-processing of the system should be in real time. That will be very useful for real-life scenario, for practical implementation. Interestingly, none of this implementation has made a real-time situation. So real-time system means all the post-processing in Alice side and Bob side, that will be in the real time. So this is the main challenge that we need to understand. So in theory, we have security challenges. In implementation, we have the distance challenge and the real-time implementation. Okay. Now, what we are doing at Eindhoven University of Technology, we are really focusing on real-time system. So till now we have achieved a real-time BOP in free space communication with 2.7 Mbps, that is equivalent to 20 kilometer fiber, and we have used 256 QM. And interestingly, the component we have used, that is the real life and low cost component. We have characterized the turbulence in the free space channel, and as real life scenario request co-propagation with classical signal and quantum signal, we have also demonstrated. Now, in the error correction code, we are working on three type of code. One is LDPC code, where we have achieved optimized low rate for LDPC code, and we are working very close to capacity. And we have researched the practical consideration for reconciliation of CPQKD. And secondly, we have started working on turbo codes, where the results are submitted. And finally, this is random codebook. This is a very new paper came out in the last week, where we have theoretically designed using Gaussian modulation an error correction scheme that gives positive key rate for arbitrary distances, right? So that means if our research is good and it's true, then we can get the secret key rate, that is a positive secret key rate for arbitrary distances. Then our limitation for the distance will be lifted, okay? And in future, what we are really focusing a real-time Alice and real-time Bob. That means we are focusing on a real-time system. And till now we have done experiment in free space. We can do in fiber also. And finally, the most important one, we now perform the experiment for this random codebook error for discrete modulation, that is practically used and taking all the practical consideration. This will really be change the way that we look in quantum key distribution system, right? So this is in summary our work at Eindhoven. What are the commercial CPQKD systems available? So Quantisense Lab, they have made a CPQKD system that is a coherent state Gaussian modulation, and using homodyne detection. They have also told in their brochure that they have used finite key effect, and their raw key rate is given, but maximum distance is 40 kilometers. Another company, Lux Quanta, they are also working on CPQKD system, and KeyQuant, they have told they are also working on CPQKD system. Now, what are the other projects of quantum communication in Netherlands? As I told that I am a part of National Quantum Mission of Netherlands, where we are working on three categories: quantum computation and simulation, building quantum communication network, and quantum sensing application. I am a part of building this national quantum network in CAT2 project. So we are aiming for a test bed both in DVQKD and CVQKD. And the funding that Quantum Delta NL has, 62 million, that is from Dutch government, and QSign, this is from EuroQCI, the people from the previous talk, they have told, it has 10 million. And what is our planning? So this is the map of Netherlands. So this is TUE. We are now have achieved that DVQKD between TUE and Walray, 7.7 kilometer. And we are planning to have this connection at TUE between automotive high-tech campus and Walray. And at Utrecht and also in Amsterdam, they are also building this network. So final goal is to build this quantum communication network in Netherlands and also quantum communication network with other EU countries. Now, as for we know that RP Singh group has in PRL has recently started this free space quantum key distribution with discrete phrases that come last year. I think RP Singh is a speaker here, and he will talk more about their work. CDOT has recently started its development of CVQKD, and they have released a proposal last year. And TCS is also monitoring the progress of CVQKD towards the software side, building some software infrastructure. This is our team at TUV, and we also have a startup that is working on a real-time chip-based system and making a product from our research. And I will end my talk with some very good survey paper, which if you wanted to start your research, you can really start among these survey papers, where I would recommend this paper came out in 2023, CVQKD, and if you just start looking on this paper, and you will get sufficient information. And this is our papers at TUA, and I really wanted to focus this paper, CVQKD with key rate. This is recently came where we have told that really CVQKD can lift the distance barrier. Okay. And I will, this is my last slide. So if you want to connect with me in LinkedIn, you can just scan this picture and you will be immediately connect. And as you can see that I have masters from Indian Institute of India Shibpur, IIST, and PhD from ISI Kolkata under Professor Gautam Pal, who is also a speaker here. And then I was 1 year at TCS. And finally, I am here at TUE. So thank you for listening. And if you have any question, then I am open for taking questions.
Thank you, Dr. Soumya Das, for joining in from Netherlands and sparing time for us and speaking on advancements in quantum key distribution. Ma'am, can we take some questions in between, or shall we continue later? Okay, sure. So, ladies and gentlemen, that was Dr. Soumya Das from Netherlands. And now we have Dr. Anirban Pathak with us. Professor Anirban Pathak is a theoretical physicist. He did his PhD from Vishwa Bharati Shantiniketan, India. He was a postdoctoral fellow in Free University Berlin. Dr. Anirban Pathak is a professor and head of the Department of Physics at JP Institute of Information Technology, Noida. He's actively involved in teaching and research related to several aspects of quantum optics and quantum information, with a focus on quantum cryptography. Dr. Anirban Pathak's group has recently implemented quantum key distribution over 145-kilometer fiber, and he is also a recipient of 2017 Shri O.P. Bhasin Award in the field of electronics and information technology. So it's over to Dr. Anirban Pathak ji, please.
So, to begin with, I would like to thank the organizer for inviting me, and also my apology to my fellow speaker, Professor Joey Ghosh, for changing it because I have a meeting at 4. And I'll speak on a serious topic, but probably in a bit lucid mode. And to begin with, I just want to note that we are professional quantum cryptographer, and we are supposed to be trained in making our information secret. But somehow my friend G. Raghavan was able to eavesdrop. And what I planned to speak, he spoke part of it. So it made my life easier. So eavesdropping is not always bad. For example, when Turing was able to eavesdrop, that helped to decide the fate of World War II. So I planned, when I was asked to speak, that I will become devil's advocate. So it depends on where you are. So if I'm in a funding agency and I'm speaking for a project on quantum cryptography, I'll say that it's unconditionally secure, everything is secure. This is the thing, and you cannot think of anything else. But since I asked to speak about security, I thought that I will become devil's advocate and speak about a bit negative. But take it with that spirit. So before we start, I just want to write a summary on practical challenges. So I remember a quote from Asa Paris that quantum computing is not done on Hilbert space, it's done on lab. So same is true for quantum cryptography. It's not done only on the theoretical papers where it's unconditionally secure. It's really done on lab. And when you work on lab, there are several challenges.
So many of these challenges are engineering challenges. So in the room, there are many engineers. So physicists and mathematicians prove security proof, but finally you have to implement. And we don't have good quality single photon source. So building a source is an engineering challenge. We don't have a commercial quantum memory and same that quantum repeater. And then we don't have single photon detectors with high efficiency for every wavelength. So these are primarily engineering challenge. Quantum mechanics does not tell you that you cannot build it, but we don't have. And to contribute to this field, you don't need to have expertise on quantum mechanics and do a lot of integrations, normalizations. So if you have a good engineering skill, you can contribute by making devices which we need. Now, so what the first list says that we have some devices which are imperfect. And every time the advantage we say that quantum cryptography is advantageous over classical because it's unconditionally secure. But this unconditional security is in the regime if you have everything perfect. But once you have imperfect devices, say you are using a beam splitter, which is supposed to be 50-50, but it's not 50-50, something which was not supposed to reflect, but it is reflecting, then we have a window for hacking it. So I'll give some examples. So imperfect devices is a problem. Security proofs. So many schemes are easy to implement. So I'll just show the example in the next slide that we have implemented cow protocol, what the person who was introducing me told, but cow protocol is not secure against coherent attack. So it is possible to attack cow protocol, but it's easy to implement. So sometimes we implement things which are easy, but they may not be secure. Then in all protocol, there is an authentication part, that how do I know that Alice is talking to Bob? Authentication is classical, and that's not unconditional secure. So if you can attack at that stage, you can attack the protocol. Then there are other challenges, like in Delhi, if you want to do a satellite-based quantum communication, it will not work because of so much of light pollution. You cannot see the satellite. Satellites have only reasonable time of visibility. And then there are India-specific challenges, which are not quantum mechanical challenge, not technical challenge, but these are practical challenge. One most important practical challenge is GTE. So everything you try to implement, it takes so much time to order and the lead time. You order and then when you get the device. But when you talk about practical challenges, this should come into the scenario. Okay, so now I specifically speak about two implementations which are in archive. One is for cow protocol and one is for cow and DPS protocol. So these are done in collaboration with CDOT. So we have a move with CDOT, and CDOT is showing this device outside. And those who found it interesting, and if you want to kind of see a data sheet for those schemes, so visit our archive papers where every analysis about these two devices will be there, the cow and DPS protocol. So in the cow protocol, as we mentioned that it's secure, even not all variants are secure because it's possible to make coherent attack, and especially something called zero error attack. It is possible only if you don't go for a key rate beyond a limit. So in our symbolically we write it's secure up to of the order of eta. So I'm not going in technical detail what is eta, but DPS is relatively better, but we all are making this cow and DPS because it's easier, and I'm also part of that because it's easier, we are building it. So these things has to be kept in mind. Then now we talk about this thing that QKD itself is not an application. So application is sitting above. So Sunil Gupta ji was also talking about this. So this application is above, but in the ground is authentication. And authentication in all commercial product is classical. So even Bennett in his first paper realized that authentication will be required, and he mentioned about that they are using this Wigman-Carter authentication. So if we can attack at this level, that in authentication level itself, that if assumes that if says Alice that I'm Bob, and in Bob he says that I'm Alice, so then it can be attacked. So unconditional security when you are using quantum resources. So now there is an idea that you use quantum identity authentication itself. So there are several protocols of quantum identity authentication. So this shows a chart that based on quantum resources or based on quantum communication protocol. So theoretically, many other ideas can be converted into quantum identity authentication. So in the bottom you can see two papers of ours published last year where we describe protocols for quantum identity authentication. But again, this is theoretical. So these protocols are theoretical. When you go for a practical quantum key distribution, authentication is still classical. So, and that's a window where you can attack. Now, what about the quantum systems in general? Can we attack? Yes. So unconditional security means that it's not conditioned on any computational problem. It's not conditioned on your computational power, but it does not mean unhackable. So there are several incidents of hacking, and we are showing some. So a practical challenge is to protect your device against all such possible attacks. So for simplicity, I'll give some lucid examples of attack. So this is a simple attack. It's called Trojan horse attack. So in Trojan horse attack, what happens that so the eavesdropper sends a laser. So this breaks into two beams in beam splitter. One is the reference, the other one goes through this. So this device is called circulator. So if you come from port 1, it goes to port 2, and if it comes from port 2, it goes to port 3. So it goes inside Alice's part and reflect on everything, say beam splitter, commutator, say connector or variable attenuator, and then you get the signal. So of course you don't get every information, but you get some information. So this is an attack, it's called Trojan horse attack. So there are techniques to protect it. Of course you can put another circulator in front of Alice to stop such beam to enter. But this is an easy to visualize attack. So what happens here, that when the beam goes, then it returns. Since it's coming from the path 1, it's going to path 2 is going to path 3, and then here is a reference beam, so we know what has happened to the other beam. So these are some implementations of this attack, and you see that this is the circuit and or the device, and from every point wherever there is a junction, there is a polarizing beam splitter, I'm getting a symbol that it's reflected there where it goes, etc. So in the beginning itself, I told that I'll be lucid in the talk. I don't want to discuss very serious thing. So here is everything happens between Alice and Bob. So Bob is angry on Alice and says that I don't want to see your face. So Alice says, why? And Bob says that because you reflect light. So Alice says that that's how you can see. But then Bob says, but that's the reason that Eve can also see you. So Bob is very positive, and Bob wants to see only. So it would have been better if we could have spoke about this yesterday. But anyway, so then Alice says that you give me a circulator. So circulator can protect you from certain kind of Trojan horse attack. So this is another free space QKD systems. You can hack by wavelength control. So what does it mean? Okay, so you look at this. So in beam splitter, we often say that BB84 kind of protocol that randomly we do measurement in 0-1 basis and plus-minus basis. So for that, beam splitter takes randomly in this path where there is a 0-1 measurement and this path where there is a plus-minus measurement. But this beam splitter works as 50-50 beam splitter only at certain wavelength. So if I can shift the wavelength, then it is possible that all the light goes into 0-1 path or all the light goes in plus-minus path. By shifting wavelength, one can attack. This is a simple attack which based on Malus law. So what happens here, that there are four light emitting diodes, and there are polarizer in front of that. Now it goes like this and mix up between 0-1 plus-minus. Now Eve sends a light, strong light, and it enters Alice's port. Malus's law tells that cos square theta law, so this goes here with 100% because the polarization and parallel, here it is 0, here 50-50. So the temperature changes and that change wavelength, and we can find out by measuring that which one is what. So without going in further detail, so this is another kind of attack where the detectors which are 0 and 1 are supposed to be equally efficient, but they are equally efficient at certain time. So if you make time shifting, then the detectors are not equally efficient. So whole point is that there are several windows for doing attack. So now the satellite is the idea that if for long distance things you can do satellite based schemes, and you can cover very large distance, but there are many practical challenges. So when the satellites are trusted repeaters, so how it works, that when it is above India, say, we create a key, and then it goes to above, say, another friendly country, say above UK, and then create another key, and then exhorts and declares. So this key is noted in the satellite, and satellite is behaving like a trusted node. So trusted node at its own issue. Physical attacks on satellite is possible. So ground-based, there are satellite, these are low Earth orbit, and you can destroy the satellite. Restricted time window, it's visible only on certain times, and then the weather conditions. The issues are many issues which are difficult to address. For example, normally we do communications in free space communications in 800 nanometer because the single photon detectors are most efficient there. But when you do it in 800 nanometer, then sunlight has a lot of 800 nanometer, so you cannot work in daytime. So but 1550 nanometer we use in fiber, but in 1550 nanometer is not in daylight. So you can do free space communication with 1550 nanometer even in daylight. So it's a challenge but you cannot do anything. Sunlight will have 800 nanometer. So how to address the challenge? You have to make detectors which are more efficient in other wavelength or as efficient as 800 nanometer in other wavelength. So many of these challenges are technical in engineering in nature, and turbulence, etc. also affect. So we just list them because time is also going to finish, and I end up again with a lucid visualization. So where we stand now? So in the last talk also, the speaker was talking about CVQKD, and I just want to add one thing, that he spoke about CVQKD initiatives in India. So there is something in application layer, is the direct communications. You cannot make key, without making key you can do direct communication, it's called QSDC. The only experiment on CV-QSDC is done by Jabhatta, Bellini, and Mato Paris, and it's on a protocol designed by us. So the CV-QSDC protocol, only CV-QSDC protocol which has ever been experimentally realized, was designed by us. Anyway, where we stand, so we have SNSPD, which are the best single photon detector at the moment. Quantis is a cryptographic solution. Quantis is this quantum random number generator. Clavis3 is a cryptographic solutions. We have APDs, payloads for satellite-based QKD, BBO crystal, etc. But what we don't have? We don't have polarization preserving photon number resolving detector. But quantum mechanics does not stop me to build it. So this can be possible that in some year later we get it. We don't have quantum memory, we don't have quantum repeater, we don't have 100% efficient SPD. So some of these things can be made available. So this is a shop 2024 plus delta. We don't know how big is delta between the NQM time frame or extra. But then one can say that new arrivals, we have all these things which is allowed by quantum mechanics, including darkness, because light pollution is also a big problem for communication. And we are unable to sell machines for perfect quantum cloning because these are not allowed by quantum mechanics. So some challenges you cannot address. Sunlight will always have 800 nanometer. Some challenges we can address, but there are many challenges, and unconditional means just that it's not conditioned on the computational power, but it does not mean it unhackable. So as always happened in the cryptography, that our group is trying to hack, other group is trying to protect, and that field is developing. The same is expected to happen in our field also. So with this, I'll stop.
Thank you, Dr. Anuban Pathakji. And now, ladies and gentlemen, we are joined by Dr. Siddharth Joshi from United Kingdom. To tell you about Dr. Siddharth Joshi, he is a lecturer in optical communications in University of Bristol, United Kingdom. He is associated with the Quantum Communications Hub, established as part of the UK National Quantum Technologies Programme, working on the development of quantum networks. Dr. Siddharth Joshi, can we have Dr. Joshi with us?
Can't hear me. Can you hear me now?
Yeah, certainly, Dr. Sir. And we welcome you, in fact. I mean, can we have please put your hands together for, let him understand that, yes, of course, we all are listening and watching him.
Brilliant, thank you. It's a pleasure to be here. Thanks for inviting me. So I am here to talk about entanglement-based quantum networking, and I'm part of the UK National Quantum Communications Hub, funded by the UK funding agency EPSRC and UKRI. So we're going to talk about how we build these type of larger entanglement networks spanning across the entire city, in this case, the city of Bristol.
Dr. Siddharth Joshi, I'm really sorry, but humble request, if you could just please share your PPT with us.
Right. I have sent the link by email. Can you try and download that? Otherwise, I'm sharing screen. Can you see that?
You'll manage? Okay, thank you, Dr. Please continue. Thank you.
Okay, can you see my screen? I'm changing slides now. Okay, so I'm going to continue from here. So we have the concept that we want is we want this to be uh, good on resources and scalable. So we want just a single source of entanglement serving all users within the network connected by just one fiber each with linear resources scaling for every user within the network. But at the same time, on a quantum communication layer, we want the entanglement to be as diversely distributed as possible. So we want a fully connected graph in terms of entanglement distribution so we can do the maximum possible that we can do on a quantum layer, enabling all sorts of applications on the final most abstract communication layer of the network. To do this, we start with a single source of entanglement that is broadband. And since we base this on down conversion, that means that we can divide this broadband light into several different wavelength multiplex channels using standard telecommunication wavelength division multiplexing. Each of these channels, symmetric about the center wavelength, will be entangled to each other and only to each other due to energy conservation. So I've called the channels pairs that are entangled to each other 1 and -1, 2 and -2, and so on. Once we have that, we then need to decide how we distribute these channels across the network. So we can choose a network topology and we can make this completely dynamic just by choosing how we connect these DWDMs together and distribute them. So to enable communication between A, B, C, and D, I can just distribute 8, -8, 7, -7, 6, -6, and so on, and repeat that pattern until all users are able to communicate with every other user. At the same time, we can also duplicate channels, not due to copying of the quantum information, but just simply a beam splitter, which effectively also gives us a time division multiplexing. So we multiplex in both wavelength and time domain, which basically means we can assign complex network topologies and end up scaling linearly. So we have just 8 pairs of channels for 8 users. Now, putting all of this together, we have the source of polarization entanglement that we then wavelength split using an experiment that looks like that. Distribute this to long distance loopback fibers across the city of Bristol in various locations, and even fiber spools over much longer distances. We in fact connect to the wider UK National Quantum Network, which is over 50 kilometers away. Each user module consists of an input, passive basis choice, measuring in the horizontal, vertical, or diagonal, anti-diagonal, depending on the path taken, and then single photon nanowire detectors to make good measurements with very low timing jitter. All of this is then connected to time taggers and connected to computers such that we can generate the key on the fly. So with an 8-user network, we can get a fully connected graph. We have 32 simultaneous keys. That's not only because we have a fully connected graph, but we also have some extra key generation links for those users that require higher key rates. So we can do a quality of service estimation as well. Beyond this, we want to try and introduce a completely flexible quantum network so it resembles telecommunications. We have borrowed the concept of a reconfigurable add-drop multiplexer from telecommunications and made the quantum version of that. So the source is connected to this QRODM and then sent to all these quantum receivers. The QRODM itself consists of a demultiplexing unit, fiber polarization control units, motorized fiber polarization control units to take over when the manual polarization fails, optical switches, and then remultiplexing units to combine them all together and then send to the receivers. With this, we can now look at network reliability and create some sort of arbitrary metric which we think is useful for network service provider to determine what is an average effective secret key rate such that it does not bias people who have met the minimum service threshold and severely penalizes the network when you do not have at least a minimum service level. Once we have defined such a network, we can then look at the network reliability by operating the network over a long period of time with machine learning control over the network and optimization of various routes and paths along this network with multiple links. So in this case, the network had more than 45 active links simultaneously. We can go between deployed fibers that are going across long distances with deployed users, deployed versus local, and including local area within the building fibers and connections. And we can see that we have stability for about 20 days or more. And this is completely passive stability of the polarization neutralization within the fiber with absolutely nothing being touched. So that is our polarization neutralization setup. You can have 45 simultaneous links. We have extended network stability, even though all of the polarization control is mostly manual. So this means that we have optimized compensation and polarization control protocols, and everything stays very nicely neutral because we're not using fiber spools in the lab. A further level of optimization is to look at the use cases for the network, or whether we actually are going to use the full mesh of the network, or at any point we can, because we have optical switches in there, we can turn this into any partial mesh or any sub-mesh of the full mesh. So depending on situations like the heralding efficiency, the state fidelity, detector jitter, and other properties of the fiber over time, full mesh or partial meshes can be more optimal because we are distributing the same resources of each user between the multiple connections that every user receives. In addition to optimization, we have a complete network control stack, which means that we can have an entire software-defined networking, and we can run a deep neural network for predicting the QBER and SKR, which means that we train it on about 10.6 million topologies or different scenarios, such that we can actually control the networks live. In addition to all of this, we can do coexistence of classical and quantum signals at the same time on these networks, such that we reduce the amount of optical fiber pairs that we need. And to do that, we actually do coexistence with classical communication signals and quantum signals both in the C-band. So if we have a pump channel, we have a dip in the scattering profile. So just after the Rayleigh scattering profile, there's a dip in channels very close by, and we can use the quantum signals in those close by channels to actually achieve a complete multi-user network at the same time as very bright classical signals going through that same fiber. Now, so far I've talked about QKD, which is just quantum key distribution and a method of sending your secure key from one end to the other, but that is not the only application you can have in a secure network. Instead, we can also do things like anonymous messaging, digital signatures, authentication, and network flooding, and I'll talk a little bit more about these protocols right now. So if we have the world's most secure network, we need to ensure that we not only can send the message uninterceptable, but you don't know who sent the message, because anonymity is sometimes quite important. So to get the incognito mode for the quantum internet, what we do is we use the classical cryptographer's dining problem, where all the people who need to share information share a random bit between every pair of users. You can compute the parity of all these random bits, and if you are transmitting, you flip the parity, otherwise you do not flip the parity. When everybody transmits, if somebody has transmitted, and then the sum of the total parities is going to be 1, otherwise there's going to be 0 if there's no transmission, which means that we can then start repeating this to send long binary messages. Fortunately, we have exactly the type of private random information we need, because we can share secure QKD keys between everybody and everybody else. This means that we can actually do a whole host of anonymous protocols, from anonymous anonymous broadcasting over the network to just message transmission. We can also do a veto in a voting protocol, or just anonymous notification to ping people that you have a message. In fact, we can also run collision detection protocols such that you can figure out if two people are trying to transmit at the same time and still preserve mathematically perfect anonymity. To save time, I will just briefly introduce the fact that we have been able to implement digital signature protocols on the network, and we have been able to do this in a way that we have, without compromising the failure probability, we can actually send larger number of bits which are signed. We can have these bits with several different fault tolerant verification levels. In fact, we can, for n users, we have n-1 fault tolerant verification levels, and we can also do this more efficiently than all the previous protocols. We also have authentication protocols, or rather authentication transfer protocols inspired by a peer-to-peer networking that allow you to identify users on a large quantum network, because it's extremely unrealistic to expect everybody to have a pre-shared key with everybody else on the quantum internet. So these authentication transfer protocols work via trusted intermediaries. And if you're using trusted intermediaries, then you only need to be able to trust these intermediaries for a very short temporary duration, and you do not want to be able to trust them for longer duration. So we have protocols in place that remove the trust between these by using multiple non-overlapping paths within the network. Similarly, we can optimize network key rate by using idle network resources across the entire network to provide increased key rate by using these as trusted nodes, and we use a combination of this and the previous protocol to reduce the total amount of trust. This means that we can actually get massive boosts in the key rate while reducing the amount of idle time in the network. Together with the previous protocol, even if we have trust values in a trust table for the various other users in the network, by combining multiple non-overlapping paths and combining the way in which we start concatenating or XORing keys together, we can actually get both an improvement in security risk and an improvement in the key rate at the same time. With this, I would like to thank a whole host of people who have been working with me and collaborating with my group to make all these experiments possible. Give you a brief advertisement that we are hosting the Bristol Quantum Information Technology Conference happening soon. Please register and attend, and also that we have positions available within the group. Thank you very much.
Thank you, Dr. Siddharth Joshi, for joining in from United Kingdom and sharing your inputs with us on advancements in quantum key distribution. Thank you so much. And now, ladies and gentlemen, we have Dr. Joy Ghosh with us. Ma'am will speak, but before I invite ma'am, let me share a few things about ma'am with you. Dr. Joy Ghosh is a PhD in physics from the School of Physical Sciences, JNU, in collaboration with CNRS, Laboratoire Aim Cotton, I believe it's right, Orsay, France. She is currently an associate professor leading the quantum photonics group in IIT Delhi, working on quantum technologies for free space and fiber-based quantum communication and coherent light matter interaction, among other interests. May I request you, ma'am, to please come? Yeah.
Rakesh, can I have the slide changer?
It was there.
Okay. So, good afternoon, ladies and gentlemen. First of all, it's a pleasure to come here once again in Vigyan Bhavan. I want to express my heartfelt thanks to the organizers for inviting me again. So, we are a group in IIT Delhi, and today I'm going to focus about the work that we are doing in telecom wavelength. So just before that, there were other speakers before me in this session, particularly the previous speaker, Dr. Joshi, who highlighted about the importance of entanglement, and he also spoke about entanglement utilizing the telecom wavelengths. So we do similar stuff. And in the morning session, I think Shri Robert Ravi. He also mentioned the importance of entanglement-based, protocols and of that. So, yeah, I would just, yeah. So quantum entanglement is actually at the heart of many of these applications. As we know, what is quantum entanglement? So it starts minimally with two particle systems or bipartite, that's what we call, but it can also happen between more number of particles. So they share some kind of correlation, quantum correlation. So when you also take them spatially separated, that correlation still exists and beautiful things can happen. Now there are many applications of quantum entanglement. Here in this slide I've just placed a few. So quantum computation, for example, entanglement allows to enhance the efficiency of certain computational protocols. So that's one application. Then there's a huge application of entanglement when we talk about quantum secure communication. Entanglement-based protocols are supposed to be the most secure protocols because of the inherent randomness in the system. Then there's also quantum networks as part of quantum computation as well as communication, which rely a lot on quantum entanglement for communication of information between different nodes in a network. So, yeah, just to, this is like a pedagogical slide, but when we talk about entanglement, there are certain parameters by which we characterize our system. So before we can distribute entanglement or do anything, we need to have a system that will generate entanglement. And how do we characterize them? So there are various parameters. One is concurrence, the other is fidelity. People in the community know more about that. I don't want to get into the details of it, but one of the most popular parameters is the CHSH Bell inequality parameter. So for a bipartite system, if you have a Bell state, which is one of the four maximally entangled state, then this is how you would characterize it with the S parameter. And this is something, so measurement of these, each of these parameters, this is like, these are the theoretical expressions, but there are techniques in like that we do in the lab based on certain detections by which we can measure any of these parameters. So particularly now talking about, examples of qubits. So whenever you have an entangled system, you need a quantum system at the heart of it, right? To start with. So we in the group, we are biased about photonic qubits. So you can have information in terms of polarization as well as orbital angular momentum, and there are other degrees of freedom by which you can encode information on a photon. Then there are other two-state systems such as atoms, electron spins, and there are many others. So through these we can have a qubit, and based on two such qubits you can have an entangled system. Now when coming to photons, because I'm narrowing down, so entangled photons or single photons, how do we generate them? So one workhorse technique is spontaneous parametric down conversion. This is also the process that many groups rely on, and also the very good advancement in communication that is shown worldwide, they all actually depend on this. When it is in terms of photons, they all rely on this one process, which is a second order nonlinear optical process. And through these, actually there are pairs of photons which are generated, which are correlated. This is called signal and idler due to convention. And so you can have different properties of the signal and idler. You can map them onto different kinds of entangled states and so on. Now another method or one metric to utilize or understand the correlation property of these pairs of photons is the joint spectral amplitude. When pairs of photons are generated, by doing a joint spectral study of their spectra, one can understand what kind of source it is. So there are different applications of having a heralded single photon source, or a spectrally pure single photon source. So that will have a JSI which is circular, but sometimes we need entangled photon sources or sources which are very correlated. So for that, the JSI signature is an inverted ellipse with a negative inclination. So there are different ways to characterize this. Now, entangled photons as systems are concerned, this is just a cartoon picture to show you that when you're talking about, because you can have free space entanglement based systems, or you can have fiber based systems, and there are different kinds of Bell states that you can map them onto. So typically these are BBO, so the free space crystals are PPKTP or BBO, And the left hand side of this slide shows you a free space arrangement, whereas on the right hand side everything is fiber coupled, so that's a fiber based system, at the heart of which the emitting crystal is mostly lithium niobate. Now coming to my group, so in a nutshell, this slide shows you these are all kinds of activities that we do in our quantum photonics group. We actually have researchers based on fiber-based quantum communication as well as free space quantum communication. The wavelengths are very different in these. We also work on the generation of quantum squeeze light, which is continuous variable. Then we also work with silicon nano waveguides, which utilizes not parametric down conversion, but spontaneous four-wave mixing, which is a third-order nonlinear optical technique, by which we can also generate photon pairs and have them mapped onto such entangled states used for quantum communication and so on. And silicon is lucrative because it's well integrable with the CMOS technology, so that way. And apart from all that, we also have interest in coherent light matter interaction for slow light or quantum storage of light inside a medium. So this is my group, because I must acknowledge the students, the postdocs, all the group members who actually contribute to this hard work. This is just a snapshot to show you. It's an old picture from the lab, but we have both experiments on fiber-based as well as free space quantum communication. So when we talk about quantum communication, I'm again re-emphasizing. So there are two different bands. The one is the optical band, where photon pairs are generated in the range of 700 to 850 nanometers. Here the sources as well as detectors are well developed. The detectors are particularly quite efficient, and these are utilized for free space optical or satellite based quantum communication. And there is also quantum communication based on the telecom band, and this ranges actually from 1310 to 1600 nanometers. We work around 1550 nanometers, and here the sources are pretty well developed, but the detectors are not that efficient. Detectors means I'm talking about the single photon APDs. But there are SN-SPD these days, so the superconducting nanowire based detectors, which are quite efficient, but they are very bulky as well as expensive, and they are available in both free space as well as in the telecom regime. So I'll be first, just there's one slide to talk about this. So in the free space application, so we now have a very bright source which is based on single pass PPKTP SPDC, and here we have seen entanglement. This is our published work here. We also see joint spectral intensity, and very recently in the lab, actually utilizing this particular source, which is a narrow band source based on type 2, we have seen BBM92, which is a QKD protocol based on entangled photons, and we could see a QBER of 5%. Anyway, so this source is pretty good, and it has a high S parameter. So this is just one slide to show you the free space activities are also ongoing, and this is a project that is funded by DRDO, I should acknowledge. Now coming to the telecom side, so here we have actually two sources. So we work both on a broadband source as well as a narrowband source. So on the narrowband source, we are this is something that where we are. So everything is fully fiber coupled, and it has an efficiency of about the spectral brightness is about 10 to the power of 6 photon pairs per second per milliwatt per nanometer. So that's the spectral brightness. And these graphs actually typically show you the single photon counts and the coincident counts. So based on these coincident detections, because in any such setup, you have two single photon detectors, they go and plug into your time correlator or a time tagger, based on which actually you can do coincidence detection as well as different other QKD protocols, which is based on entanglement. So this is where we are, and this is one of the best type 2 fiber based sources even internationally, and I thought I'll just highlight. Coming to the broadband source, which is the main thrust of this project, which is funded by DST Quest. This is a system that relies on broadband emission of the photon pairs centered around 1550 nanometer. Quite interestingly, it's quite similar to the source that Dr. Siddharth Joshi was talking about. And this kind of a source, since it's very bright, we can actually channelize them into multiple parties. So instead of a single Alice and a single Bob, excuse me. Instead of a single Alice and a single Bob, we can have several Alices and several Bobs. So Alice 1 speaks to Bob 1, Alice 2 speaks to Bob 2, and so on. And in that way, actually, yeah, thank you so much. And in that way, actually, we can have a multi-user based QKD. Thank you, Sushil. So the right-hand side distribution is actually data from our lab, and this shows a distribution of about, so from 1520 to 1580 nanometers, we have photons that are emitted, and they are emitted with a very good spectral brightness. The motivation to do all fiber-based, all WDM-based sources, the things are very compact. They're deployable, so you can have them in a box, and you can also take it up on a satellite if that is required. But this has been tested for long fibers, so I'll come to those results. Before that, some characteristic of this source: it's extremely bright. It's about 10 to the power of 8 pairs per second per milliwatt per nanometer. This number is very important because when you're trying to communicate with the photons, people are interested in, how many kbps, bits per second or kilobits per second you're being able to communicate. So this is a source that is very bright, and when we do QKD with this one, I'm hoping that it will be a good one. It has a very good high CAR value, which is coincidences to accidental ratio. This is something that we published when we could see the spectral correlation of the photon pairs based on this source. This blue graph there is actually data. Data is taken all over this panel. This is based on coincidence detection of the signal and the idler photons. And this negatively inclined JSI actually shows highly correlated source. So in order to have entanglement after a correlated source, we put them into a SINAC interferometer. So we pump the PPLN waveguide from both the directions. Everything is fiber coupled. Then we have a CL band splitter to split them, and then use arrayed waveguide grating in order to channelize them. So there are several Alices and several Bobs, and they are mainly centered on the C band and the L band. So these are our broadband entanglement results. This is polarization entanglement, which is mapped onto this HH plus VV, which is the 5 plus Bell state. And actually recently we have also seen that this source is actually, the Bell state is tunable. So you can have both 5 plus as well as 5 minus. So we are still taking measurements and doing those results. These are the channelized. So on a single channel, which is about 1 nanometer in width, this is the entanglement result. The S parameters are pretty high, both for broadband as well as the single channelized one. And here, here I have the result for 3 channel pairs, but actually now we see entanglement in 14 channel pairs. So it's pretty good. So there are 14 channels on the left side as well as 14 channels on the right side. And this work is under review currently. We also work on several architectures, integrated architectures based on KTP as well as lithium niobate. And these are smart architectures. If there is some company, if they can take up the fabrication, then we can have all different Bell states generated on one architecture. You can also do swappable entanglement using these architectures. So if people are interested, please visit our website for more details. We also work with silicon photonics, as I mentioned. So utilizing spontaneous 4-wave mixing, we are also interested in generating these photon pairs. And this is, again, a recent paper from our group, which was highlighted as the editor's choice. And we showed a direct generation of entangled, polarization entangled photon pairs from such a nano waveguide chip based on 4-wave mixing in silicon on insulator. Thank you.
Thank you, Dr. Joy Ghosh, for elaborating in detail. And please do take care of your throat. Ladies and gentlemen, next we have Dr. Prabha Mandayam. Dr. Prabha is an associate professor in the Department of Physics at the Indian Institute of Technology, Madras, a postdoctoral fellow at the Institute of Mathematical Sciences. Dr. Prabha obtained her PhD from the Institute for Quantum Information and Matter at Caltech, that is California Institute of Technology. Her research interests lie in the areas of quantum computing and quantum cryptography. Ma'am, please, I invite you for this.
I hope you can hear me. Good afternoon, and thank you to the organizers, to TEC, to CDOT and TSDSI for inviting me to speak in this conclave. So I was tasked with talking about measurement device independent quantum key distribution, and it is nice to be a part of this session where, in a sense, this topic nicely complements what a lot of the others have spoken before me. So I belong to the Center for Quantum Information, Communication and Computing at IIT Madras, and I should mention that this is joint work done with some of our students at the center, Valyamai and Nilesh, Shashank, who's currently a postdoc at York University, and Professor Anil Prabhakar, who's the PI of the center. So well, I'm a theoretical physicist, so it is hard for me to give a non-technical presentation, but I have made a very good attempt today. I hope so, at least. So we'll try to mix up things in the sense we will introduce some of the basic ideas again, because this is, like I said, complementing what a lot of the others spoke about in this session. And I will also show you some pictures of implementations and so on. So hopefully you'll all still be awake in time for the coffee in maybe half an hour or so. So why measurement device independent QKD? So I will start by motivating that. And then I will talk about certain practical difficulties in implementing an MDI QKD protocol. And I will present one solution that we came up with in our group. And finally, although this was not part of the mandate, I thought I should also talk a little bit about this very recent variant of measurement device independent QKD called twin field QKD, which is actually seems to be a very promising candidate if one wants to talk about long distance quantum key distribution over fiber. Sorry, you can't hear me or something at the back? Okay, anyway. All right, so I don't need to introduce QKD to this audience, so let me move on, but I just want to point out a few things. Why do we believe that QKD is secure? Why do we believe that quantum key distribution is quantum secure? And as someone mentioned, it is information theoretically secure, and it's not just computationally secure. So the distinction is the security of QKD does not rely on the hardness of a particular mathematical problem, like factoring, which was hard 20 years ago, but today, if quantum computers become scalable, then it's no longer hard, right? So whereas QKD relies fundamentally on principles of quantum mechanics, which ensure that it is unconditionally secure. And now I say unconditionally because, as Anirban also pointed out, when you do a practical implementation of a QKD protocol, there are issues with this notion of unconditional security. But if one were to do ideal in theory, the reason QKD is secure is because quantum states cannot be copied. That's a no cloning theorem. Second, measurement of a quantum state always introduces disturbance. You cannot look at a quantum state without disturbing it. This is again very counter to classical intuition, where you can make as many copies of information as you want, where you can measure multiple times and the nature of your information is not going to change. Both of these aspects in particular get highlighted when you use what are called non-orthogonal states. These are the most non-classical states that you can think of in a quantum system. And these polarization states that we all use for QKD are a classic example of that, where you have, for example, the horizontal and vertical polarization, and then you have the cross polarization. And together, this set of 4 directions, this set of 4 vectors gives you a set which cannot be measured without causing disturbance, which cannot be copied, okay? So in IIT Madras, the protocol that we implement, so I thought I'll just introduce this a little bit, is something called differential phase-shifted QKD, again, something that Professor Animban also mentioned. So in this case, we are not using polarization because Again, practically implementing polarization-based QKD requires you to have fiber that is polarization maintaining, and this means you have to relay your fiber optics network if you really want to do a QKD network. So ideally that one would like to do QKD is to not disturb the existing fiber optic networks that we have, and so then these phase-based protocols become suitable or very ideal candidates for that. Let me not go into the details of this. This is for any of you who want to know some of the details. We can also chat later. But the idea is now that you're putting information into relative phase between pulses. And in this case, I've shown this as 3 paths. This can also be over 3 time bins and so on. This is the Alice side. This is the Bob side. Let me move on to talking about what are the kind of attacks that one typically studies when one does a QKD protocol, right? We all have seen these secure key rate curves, right? I'll show one of these in the next slide. When you draw this secure key rate curve, the attacks that one is typically taking into account are all attacks done on the channel, right? There is no attack on the source, which is Alice. Neither is there any attack on the detector, which is Bob. So when one draws all these secure key rate curves saying that we have achieved security over these many kilometers of fiber or over this much dB of channel loss, you're not talking about the source or detector attacks. Sometimes these are called side channel attacks. Rather, what one typically talks about is the kind of attacks that I'm going to list on this slide. They could be individual attacks, which means that the eavesdropper is now looking into the quantum channel and sort of measuring signal by signal. Of course, she measures and then she has to do something and send the information back. She typically mimics Alice. She measures and then she mimics Alice and sends the information back to Bob and so on. She could do a beam splitter attack, which was mentioned again in one of the talks. Then one talks about unconditional security, where you believe that this eavesdropper is all powerful. But still, the eavesdropper is only attacking the channel, right? Then there are other attacks which we've studied in our group recently. For example, you can talk about a cloning attack. So I just told you that quantum information cannot be copied, but there's a caveat to that. Quantum information cannot be copied perfectly. So I can still design what is called a quantum copying machine or a quantum cloning machine, which can approximately copy the information that Alice is sending to Bob. So we study an attack where we model these kind of cloning machines and we say what is the best attack that an eavesdropper can do if she wants to do a cloning attack. So these are the various attacks that people study, and this is a typical secure key rate plot that you see. There's some details here from our recent work, but the point is that you typically see these secure key rates falling off at about 100 kilometers, or if you push it 150 kilometers, right? So now there are 2 questions. One, like I said, we do not take into account side channel attacks. So how do we tackle that, right? And among these side channel attacks, you see that many of them are actually on the detector side. So I've just listed some of the common side channel attacks that an eavesdropper could do. Many of these are on the detector side. And second, how do you improve this distance? So one common way that we think about improving the distance is to use what we call trusted nodes or trusted relays. This was also mentioned in the morning in one of the talks. So if you have security only over 100 kilometers, then at every 100 kilometers, you start putting a trusted node, and that's how you try to improve the distance over which you have quantum secure communication. But what I'm going to now tell you about is measurement device independent QKD, which promises an alternate solution to this problem of increasing the distance over which you have secure communication. It also simultaneously solves the problem of detector side channel attacks. And the way it solves this problem is that it simply outsources the measurement to a third party. Okay? Now, initially you had Alice as a sender and Bob as a receiver, but now you have 2 senders. Both Alice and Bob become senders. So like in this picture, so I hope you can see this. So there is Alice and Bob. This is the standard QKD picture. Alice sends, Bob receives, detects, etc. And the channel itself is susceptible to attack by the eavesdropper. But now at the bottom, what I'm showing you is a cartoon of measurement device independent QKD, where both Alice and Bob become senders. And the measurement itself is outsourced to an untrusted third party. Charlie here, we typically call this untrusted third party Charlie. What Charlie has to do, though, is to measure and announce the results of his measurement over a public channel for all the world to hear, right? But still, one can work out a protocol by which at the end of this, Alice and Bob still share secure key. Now you realize that by putting Charlie in the middle, you have effectively doubled the distance between Alice and Bob. So if, for example, you had secure communication over 100 kilometers, if you can tweak that protocol to make it into a measurement device-independent protocol, then ideally maybe you have 200, you have effectively doubled that distance because you put the detector in the middle and it's an untrusted detector, right? So here's an example of a measurement device-independent QKD protocol. This is called a differential phase-encoded protocol. Like I said, this goes back to the DPS QKD protocol that I showed you, except that now both Alice and Bob have become senders, and the receiver has changed. It's no longer a Mach-Zehnder interferometer like for those of you who are interested in some of the technical details, it's no longer the Mach-Zehnder interferometer that was there on Bob's side, but it's simply a beam splitter followed by a pair of detectors, right? And very interestingly, since we also spoke about entanglement in this session, this is a protocol that originally does not involve any entanglement. They are actually creating superposition. Alice is creating a superposition of a single photon state, ideally in one of three paths. Bob is creating a superposition of a single photon state in one of three paths. But by interacting through the beam splitter in the middle, what has actually happened is entanglement has been created. Okay? So this is a protocol where you're sort of dynamically using entanglement to get security, but you don't have to start off by saying I'm sharing entanglement or that I have an entangled source and then I'm sending this across. So this could be another potential advantage of MDI QKD type protocols. So this is just to say that this combines this protocol that we proposed, which is DPS MDI QKD, combines the best of both phase encoding. Phase encoding is good because it's implementable, it's robust against phase fluctuations, and at the same time, it's an MDI protocol, so it's secure against detector side channel attacks. This is a reference for those of you interested. These are the secure key rates, but let me move on and talk about, well, MDI QKD also has its issues, right? And the reason that MDI QKD itself today has not been implemented over very large distances is because what's happening out in the middle, where I said effectively entanglement is being created, happens via a process called Hongu-Mandel interference. And I think someone spoke about it also in this session. So this HOM interference actually depends on the pair of photons reaching that Charlie's beam splitter being identical. And that's a very hard ask because you're having two separate sources. So it's very hard for you to, even if you phase synchronize and so on, to say that you're going to have two identical photons reaching the detector in the middle and then your protocol proceeding based on that. So this is going to introduce some errors. The fact that you don't have this perfect HOM interference is going to create some errors. Two possible errors, for example, if you're doing a polarization-based protocol, it will create polarization mismatch. If you're doing a phase-based protocol, like using a weak coherent source, then this will create asymmetric pulse broadening. So there is problem with HOM. There is problem also with the channels themselves being asymmetric. The Alice to Charlie channel will be different from, in characteristics from the Charlie to Bob channel and so on. So how does one tackle this? Well, there is a way to work around this, and that's called plug-and-play MDI QKD. I'm just throwing out some names here with shortage of time. But essentially, the idea is now you not only outsource the detection, but you also make Charlie the source. Okay? You make Charlie a source who is going to send photons to both Alice and Bob. And the way Alice and Bob are now going to encode is using Faraday mirrors and then on top of that doing their phase encoding. So because of the fact that they use these Faraday mirrors at their ends, they're effectively cancelling out any asymmetries in the channel, they're cancelling out these pulse broadening effects, polarization mismatch and all of that. And by the fact that they choose how to encode, again, the protocol proceeds as before, so there's no new security analysis to be done, but it's just a different way of implementing now. It's called plug and play because no one is preparing and sending anything. It's just one setup where you just kickstart and then it's sort of, it's on autopilot essentially. So this is a very interesting kind of model to think about. So we have a patent on this and this is something that we are working on implementing on the field with BEL. Finally, the last point that I mentioned, which is twin field QKD. So like I said, MDI QKD still has its limitations. So until something like plug and play really comes out and we start testing what are the distances over which we can do that, we don't know if we can scale the distance well with MDI. So the new sort of idea that's in the both theoretically and I believe experimentally also, it's seeing quite a bit of success, is this idea of twin field. I think someone spoke about this where they said that the secure key rate, how does it scale as a function of the channel transmittance? So the regular phase-based protocols scale linearly, like something like cow QKD. Something like DPS and so on typically scales cow scales quadratically, the typical protocol scale linearly, so you see this linear drop in all these secure key rate curves. But when you come to twin field, you do the key sifting in such a way that the secure key rate actually goes like square root of the channel transmittance. And again, fundamentally, the physical principle underlying this is that you have moved from requiring 2 photons to arrive at the same time to the detector to actually doing what is called single photon interference. So you have a combination of vacuum and photon, and that superposition and interference at the beam splitter can lead you to a QKD protocol. So this again is something which shows great promise. So if you have very nice detectors, you can actually now do secure QKD over 600 kilometers. I believe the state of the art is actually 800 kilometers from a group in USTC in China, where they have demonstrated twin field QKD over 800 kilometers. So this again is a protocol that we are working with, which is again phase-based encoding and twin field. And just a minute or half a minute on this last slide to show you the efficacy of twin field. So these linear curves are basically what we call repeaterless QKD. So if you don't have trusted nodes, and if you don't have repeaters, how does your secure key rate go as a function of channel loss? Well, it falls linearly. It turns out that even MDI QKD, which I sold to you for the first 10 minutes, falls linearly. So the other two curves that you see here, the blue and these two curves, they are the twin field QKD protocols. And you see that you're actually beating the repeaterless bound, which is a very significant thing. It means that this is a protocol which shows some promise for scaling if you want to implement something like this, which is a long-distance QKD network from Chennai to Delhi or something, just to acknowledge our funding sources, and thank you.
Thank you, ma'am, Dr. Prabha Mandyamji. And now, ladies and gentlemen, in this session, we have our next speaker, Dr. Sushil Majumdarji. Please.
Thank you, ma'am, for inviting me on the dais. Good afternoon, everyone. And first of all, I thank the organizers for this very kind opportunity for me to come here and present what I would call a technological proposal, research/technological proposal. It reads towards free space quantum key distribution using stratospheric balloons as trusted nodes. I'd like to name this StratoQuant. So as this title slide suggests, my actual expertise happens to be mesoscopic optics, which has to do with light transport in nanostructures. But since the last 3 years or so, we have been trying our luck in quantum photonics, and this is partly a story of the same. A very short and a quick pictorial introduction. We do apologize to the experts. We have now agreed that quantum communication is the most secure form of communication, arising from 2 reasons mainly. One is the quantum key can never be duplicated because of the no cloning theorem. And the second one being the hacking attempts are always detected. So when Alice wants to send Bob some information, he first sends a key which is random bits of zeros and ones. And these keys in the quantum domain are written in using quantum attributes of certain physical entities, such as single photons in this case. And with a quantum key, Alice can afford to send to Bob the actual message which is encrypted through a common public channel, while ensuring that the key itself is always sent on a quantum channel. Now, ideally, Alice would like to place herself at any distance from Bob, but as we all know, the reality of life is that there is a lot of turbulence near the ground level. Typically, up to 1 kilometer is the worst. So, the Alice and Bob stations are usually placed at an altitude, just like any astronomical telescope, usually about a kilometer from the ground surface. And the problem exacerbates when you want to increase the distance, because the distance to horizon increases, which forces the Alice and Bob stations to go even higher. And that's why the farthest on-ground communication link, to my knowledge, at least one of the farthest or probably the farthest link was 144 kilometers across in the Canary Islands. This problem of long distance has now been, long back has been attempted to be solved using what are known as trusted nodes. These trusted nodes are supposed to be at a high altitude, and therefore the name High Altitude Platform, or HAP in short, which is supposed to float at a distance from the ground over a convenient distance, so that Alice and Bob do not talk to each other, but they rather get keys from their HAP, or they send their keys to HAP, and using some Boolean algebra, they eventually manage to have encrypted conversation between each other. Several different platforms have been proposed. For example, one of them being an aeroplane which can fly at an altitude of 10 kilometers or lower. Some of them have proposed aerostats about 4 kilometers or lower. Then there is an unmanned aerial vehicle, UAVs, popularly called as UAVs, which can go all the way up to 20 kilometers. And then there's, of course, a drone up to a couple of kilometers, if I'm not mistaken. And of course, the most commonly discussed worldwide and in India is the satellite, which is supposed to be the ultimate in global connectivity. Our proposal is motivated from these ideas, and as the title suggests, we would like to propose stratospheric balloons as HAPs, as high altitude platforms for quantum communication. Well, the idea, the name itself suggests the story. If we have access to a stratospheric balloon, which is a balloon with buoyant gases that can hover at a rather significant altitude from the ground, then we can put our payloads in the basket of the balloon and expect the balloon to do everything that the satellite has done. In the case of a stratospheric balloons, the altitudes can be of the order of 40-45 kilometers, which means from that altitude, the horizon extends to about 750 odd kilometers in either direction. So the total happens to be about 1,500 kilometers. It means two spots separated 1,500 kilometers apart can see the same balloon simultaneously. But keeping some other constraints in mind, a modest prediction of possible connectivity could be about 1,000 to 1,200 kilometers using one stratospheric balloon. If I'm allowed to imagine further, it's not that it's my imagination, such situations have been proposed for other HAPs. If I'm allowed to have more than one balloon simultaneously floating in the stratosphere, then we can again build sufficient Boolean algebra and simple key exchange to enable connectivity between Alice and Bob. But here, I can actually imagine a distance of 800 to 1,000 kilometers between the two balloons. Now, why do I feel confident about that? Because at an altitude of 45 kilometers, the atmosphere is so thin that even at that distances, you're still mostly above 99% of the atmosphere and maybe a little bit below 99, which implies minimal to zero scattering losses. And under these conditions, we are actually looking at possible connectivity over 1,800 to 2,000 kilometers, which now comes very close to our national landmass. So do we have a possibility of connecting the country using free space in long distance using stratospheric balloons or a network thereof? That's the question we are asking here. Now, the freedom offered by the stratospheric balloon also suggests certain possibilities of connectivity over two cities, connectivity over a city to a remote location which may not be easily accessible to fibers or other permanent ground stations, connectivity from one governing city to a strategic location, typically the border with hostile terrain which is not amenable to fibers, and connectivity from a land station to a station on water. These possibilities exist. Why do we come up with such an idea? Is such a wild thought? The answer is no. In 1940s, our founder director, Dr. Homi Bhabha, in yet another one of his pioneering initiatives, carried out an interesting experiment. He tied cosmic ray equipment, detector equipment, to a balloon cluster, and he flew it to an altitude of about 25 to 30 kilometers. He was a particle physicist, high energy physicist. And the results of this experiment basically started an avalanche of activity towards floating balloons. And I will cut a very long story short telling you that all the subsequent activities essentially culminated in the creation of the TIFR balloon facility in 1969. So at the moment, TIFR has a scientific balloon facility which can do everything involving scientific ballooning, such as design and fabrication, payload integration, telemetry, telecommand, related instrumentation, balloon launches, tracking, data collection, flight control, payload recovery, practically A to Z of scientific ballooning. So what you see here is the current TIFR balloon facility in Hyderabad. That's the main entrance. I invite you all to have a look at it. Here is the control room. And this facility is used by several institutions in India and abroad already, typically for atmospheric sciences or astronomy. Here's one stratospheric balloon waiting, filled with buoyant gas and waiting to be launched. And if you're not very privy to how balloons basically are launched and sent. It's quite an exciting event if you are present in the situation. So what you see here on the top left video, top left video is that's the balloon being launched to the stratosphere. This one was launched with a relatively small payload and expected to hover at about 38 kilometers, whereas the one which is shown in the lower film, which I'll get to in a moment, right, that one there, the lower film, is actually a massive payload of 1,000 kilograms. So what you're seeing there is a payload of 1,000 kilograms being sent to the stratosphere at a height of 32 kilometers. So what the table here summarizes is the capabilities of this facility. There are different kind of balloons which are made and floated with depending on the respective requirements. And our interest today for this talk are these two categories. Those that are called zero pressure balloons, which can carry payloads up to 1200 kg, up to a height of 32 kilometers, and lower is the weight, you can go higher, and something called tethered balloons, which are essentially balloons tied to the ground, but can still hover up to 1 kilometer and can carry up to 150 kgs. These tethered balloons are basically used to test your payloads that you would want to send at a higher balloon. Now, one advantage that this technology already gives us is that, in communication, you need tracking and pointing systems. So because of our astronomy experiments, we already have pointing systems that are accurate up to 5 millirads or even 1.5 millirads using star trackers. So we use GPS positioning, and we use magnetometers, which provide X, Y, Z components of the Earth's magnetic field, which is extremely constant at that height, and that allows us exact pointing to accuracy of about 0.3 degrees. And importantly, it allows us the capability of pointing at any azimuthal angle of choice during one single flight. So that, as you can see, can be very useful in communication experiments. So that's how we thought these are the capabilities that motivate us to kind of make this proposal. We have been working towards some quantum optics in this direction, and I'll quickly brief you through that. So essentially, we don't have this proposal on the way yet. Whatever equipment we have in our lab is helping us carry out these experiments. So we have now understood the concept of weak coherent pulses, and we have learned the idea of polarization fidelity over several hundred meters. This is part of the BB84 setup, but BB84 is very equipment intensive, so we are not equipped to do the complete setup. Apart from that, we have also built single photon sources using type 2 PPKTP crystals. And this plot here is what is known as the G2 function, the second order correlation function, the value of which should be below 1 for a good source, and it turns out we routinely get 0.05 with a brightness of 10 to the power 4 coincidences per second, which is reasonably good source for QKD, as I'll show in a minute. We have also managed to get entangled photon sources in the lab. So what you see on the top left is a beta barium borate crystal with two circles which interfere at 2 points, which gives you entangled photons. These turn out to be a little difficult to couple into fibers, so we have studied the art of creating entanglement using bismuth borate, which gives an entire circle of entangled photons, and that gave us respectable, from my point of view, visibilities of 80%, 90%. But we actually fell back onto our PPKTP crystal. There it is. We fell back to our PPKTP crystal. It's a single pass PPKTP entangled photon source, where we got close to 90 to 99% visibility in the plus minus and cross basis, and an S parameter of 2.66. So which I would call, I hope experts agree here, it's a fairly respectable, a very good entangled photon source. In terms of QKD per se, we have implemented the B92 protocol, which is fairly easy in terms of equipment intensive nature. We don't need much. And here are the payloads we created for the B92. That is the source, the Alice, and the Bob payloads. And we first carried it out over 6 meters in the lab. Routinely get Q-burst less than 4%, and the bit rates are 1500 bits per second. We went ahead with a slightly longer distance of 50 meters for B92 using the auditorium foyer in TIFR. We get a Q-burst of little less than 8%, which is not optimal. But we are not working at improving these numbers. We just have to get quantum caliber equipment, and I'm sure a lot of things will fall in place. With entangled photons, we have done a long distance measurement of entangled preservation over 100 meters. So this is not actually the communication protocol. The communication protocol will have some more equipment which we don't have. But nonetheless, if you look at the best rate measurements, we can sort of imply what would be the Q-bar of the communication experiment. We expect less than 5%, which I think is very good, and the S parameter drops to 2.47. It's still very good. So the distance between These two are now about 100 meters. So yes, so learning a lot about beam coupling, beam expansions, beam propagation, and so forth. And we are on course of doing bigger experiments with quantum key distribution. Coming to balloons per se, like I said, one doesn't do experiments on stratospheric balloons directly. One tends to use tethered balloons, as you can see that one there, which is tied to the ground with a dummy basket. It's called a gondola in technical terms, a dummy basket here. And if I can get this, excuse me, sorry, I cannot. Sir, can you play that movie in the middle? Yeah. So as you can understand, it's not exactly a system under my control. The middle window, if you can just click on that. Thank you. So the basket and the gondola are expected to move. Sorry about the movement is taken on the mobile phone, so the gondola rotates. So we had to characterize the rotations using an inertial measurement unit which we built in the lab. And with that, we have done some good progress. We basically built a thrust bearing that arrests motions with masses comparable to what we expect the payload to be. So the second video will tell you that while the balloon completely rotates, I hope you agree that the payload is actually fairly static. So here's a mathematical description of the same, the plot. The arrested rotation is barely plus minus 10 degrees per second, which should be countered with any active pointing technology. Well, in the end, we have also this video you have to accelerate by your hand because it's several minutes long. So what you see is the optical telescope is basically dropping downwards, and why it is doing so is because using GPS coordinates, it's tracking a descending balloon over 15 minutes. So you have to accelerate that. I hope you agree that. Can you just play the video from top, start to end? Right, that's right, yeah. Just drag it to the right. Please keep going, yeah. Okay, some of you will agree that the telescope is actually going down on its own. It's basically tracking it on the basis of the onboard GPS module, which has an accuracy of 3 meters. So these are the activities we are doing, and we think this proposal has certain strengths that we perceive. It may be a cost-effective solution for communication over national length scales. We do have a lot of experience related to the balloon technology in TIFR. The balloon allows us to make regular changes in communication protocols as per your wish, as per the customer's wish. The payloads are recoverable. Your designs can be reversible. The demands on pointing technology, because of the slow relative drift, are very low, so we are confident we can meet them. I didn't talk about this, but an extra degree of freedom in focusing is offered. And for those of you who care, it's a green project with zero or minimal carbon footprint. And we think there may be international interest in countries which don't have satellites, because the distance covered is appropriate for many countries. Now, in the end, you just don't think of an idea and try to sell it off as a proposal. You have to talk to people with experience and expertise. So we have discussed this proposal with the TIFR's Governing Council a few years ago, comprising Honorable Chairman Mr. Ratan Tata, Dr. Anil Kakodkar, Dr. K. Kasturirangan, Dr. K. N. Vyas, Professor S. Ramakrishnan, everybody a top expert in his or her own field, and they have all been extremely supportive of it and have egged us to move on. And the two subject matter experts that we have discussed with are Professor Harald Weinfurter, Munich, Germany, and Professor Thomas Genevine, Waterloo, Canada, both of them leading or at least part of the local satellite communication projects. And these were the ones who were in the pioneering experiment of 144 kilometers. So they have been very supportive and very interested in this project. In the end, thank you very much for your attention, and I must acknowledge help from Professor D.K. Ojha, who is the chairman of the balloon facility. Mr. B. Sunil Kumar, rest in peace, please. Last week, we lost him for an unfortunate situation. He was the scientist in charge of the balloon facility. My students, Vikas, Kiran, Raunak, Shriman, Rodney, Aman, Mayuresh, Amit, and the staff in the balloon facility, Anand, S. Peter, Kapaldi, Dharmesh, Nagendra, and others. And the funding for this activity, it's not a funded project yet, but we worked on remnant funding that exists from the Department of Atomic Energy. And thank you for your attention.
Thank you, Dr. Sushil Majumdarji. And I must admit that I also got actually engrossed in this Alice and Bob story or theory, shall I say. So I just forgot to introduce Dr. Sushil Majumdar. So I must say a few things about him. Finally, Dr. Sushil Majumdar actually completed his PhD from Raman Research Institute, Bangalore, after which he was awarded the TRIL, that is Training and Research in Italian Labs, fellowship by the ICTP, International Center for Theoretical Physics. And he joined as a faculty at the Tata Institute of Fundamental Research, Mumbai, in August 2006, where he has set up an experimental program in nano-optics and quantum optics, and currently serves as professor there. So thank you so much, Dr. Sushil Majumdarji. So, any questions? If you have any query, any doubt, when you want to ask anything?
Yeah, it's a good point. So actually, there are techniques to keep the balloon located in certain area, not at a spot. To keep locate them in a certain area. So the angular displacement from the ground station to the balloon is minimal, a few degrees. So yes, to answer a question on whether you can keep looking at the balloon is yes, absolutely yes, you can. Thank you.
Okay, so now I'll request Mr. B.K. Singh, DDG Telecom Security, Tech, to kindly felicitate our speakers. Mr. B.K. Singh will now felicitate Dr. Joy Ghosh from IT Delhi by presenting a memento to her. May I request Mr. B.K. Singh to kindly present a memento to Dr. Prabha Mandya. And now Mr. B.K. Singh will present a memento to Dr. Sushil Majumdar. We thank all our speakers. Thank you, Mr. Singh. And with this, ladies and gentlemen, we wrap up our second session. Now we'll have a tea break of 15 minutes because you know we have one more session to go. And the next session is on quantum communication landscape. So please do join us within 15 minutes. Thank you so much for now. Thank you.
See, C has public
Quantum Communication Conclave. And now we are going to start with our third and final session of the day, which is on quantum communication landscape. Our speakers of this session are Ms. Reena Dayal, founder and CEO, QETCI, Dr. Manjunath R. Venkatesh, QPI AI, Dr. Abhijit Mitra from IIT Delhi, Dr. R.P. Singh, Physical Research Laboratory, Ahmedabad, and Dr. Matthew Kamgana and Dr. Nixon Patel would be joining from US. May I request Ms. Reena Dayal to please join us on to today's. Dr. Manjunath R. Venkatesh, I'm requesting you to please come onto the stage. Yeah. I'm also requesting Dr. Abhijit Mitra ji to please join us on the dais. And we have with us Dr. R.P. Singh ji. I'm requesting Dr. R.P. Singh ji to please come onto the dais. Thank you. So now, ladies and gentlemen, we are going to start with quantum communication landscape. This session will focus on various facets of quantum communication required for building a quantum network. And first, we are going to invite Ms. Reena Dayal to tell you about Ms. Reena Dayal. Ma'am is a technology leader and an innovation management expert, known for her work in establishing and scaling up innovation functions within organization and incubating new tech-oriented businesses. She is the founding chairperson for the Quantum Ecosystems and Technology Council of India and the CEO and partner for Benzetton Advisors. So we are inviting Ms. Reena Dayal. Ma'am, please.
Hello. Hi everyone. Good evening. And I can already see a lot of people have left because it's been a long day. But bear with me. I'm going to be talking about a topic which I believe is intrinsically very, very important for the Indian ecosystem. And the difference between my talk and what you've been hearing till now is that you've been hearing a lot of technical talks on the various aspects of quantum security. And I'm going to give you a perspective which comes from the view of risk assessment and looking at how much the technology has evolved and what is really needed for the Indian ecosystem from this perspective. Before I launch into the talk that I had planned, I also wanted to let you know a little bit about Quantum Ecosystems and Technology Council of India. It's a little less than 3 years old entity. It's a Section 8 company, not for profit. Our focus and mission is to enable and accelerate the quantum ecosystem in India. So we want to work with all the stakeholders. We are working with all stakeholders, government, industry, academia, in a membership-based approach where we try to get people together and also act as a think tank and a catalyst entity. We also design programs which can where we find gaps in the ecosystem and we design programs that can help us either discover something new, which can become an information for policy making, or we actually, sort of enable certain aspects of the ecosystem. We have been very focused on the startups. Many of the startups are our member companies, but so are public sector units or autonomous bodies. Many of you may not know, CDOT recently became a member of QETCI. So our latest member, in fact, will be announcing this on LinkedIn and all platforms next coming week. We also recently released a report called the Quantum Value Chain, which you can download from our website, qetci.org. It's the result of several months of effort of mapping the Indian quantum ecosystem and understanding where the opportunities and the threats, the strengths and weaknesses may lie. So we did a SWOT analysis as well. The idea is to be able to connect all the dots so that things can move faster. So next slide, please. Now this is a representation, I think it's very small, you can't see much, but we sort of looked at the supply chain for quantum in India and then mapped it across the ecosystem. The concept of value chain means that we've also included entities which are not just supply chain entities. So for example, all educational institutes, all primary research that is happening in basic sciences, and various kind of regulatory entities as well as standard entities, all of them form a part of the ecosystem and the value chain because they add some value to the process. And if you just look at the supply chain and you think of interventions which will only progress the supply chain, then the ecosystem will not flourish because other important aspects are missing in the ecosystem. So hence this is a very comprehensive report. It's important to point out that this report has been referenced by the World Economic Forum in their insights report for quantum economy blueprint. And this particular diagram that I have shown you, which represents the value chain framework, this has been recommended by the World Economic Forum as a framework for other nations to follow. So they are saying that if any nation wants to start their quantum journey, they should do a value chain analysis very similar to this one. So I'm very glad that this is something we've been able to do. Of course, it is going to evolve because like I was telling somebody that we prepared this report in December and it's already obsolete. And that's a good thing because already there are 4 more startups that are not mentioned in that report, right? So that way things are evolving in quantum and a lot more is happening. So we will do these exercises at regular intervals to get some sense of where we are. At the bottom of this, if you look at the bigger square, at the bottom is this green layer which you can't read very clearly, but I'll tell you it says quantum security. And quantum security actually spans the entire value chain starting from hardware up to software and applications and beyond, right? So it's important to understand the kind of impact that security is going to have. Next slide, please. Next slide, please. Can I use this? Does this work? Okay. So one of the things that I wanted to point out is when we look at the progress in the quantum computing landscape, and we look at, when we hear people talk, very often you will see people say, you know what, we don't have a scalable quantum computer today. We have only 1,000 qubits. It is noisy system. It is not completely error-free. So when are we going to have the scalable quantum computer system? And I actually want to point out that if you take a scientific approach to looking at the data, and you look at all the predictions that have been made till now, so roughly 4-5 years ago, all the papers that were written by people who are experts in computing and who predicted the growth in the number of qubits, that was much lower than the number of qubits that we have reached. So we have already, while the number of qubits, I mean this is of course till 2022, but then we have reached 1,000 qubits and beyond, right? And in that space, we have already seen exponential growth. So we have, across the world, all the predictions have been, sort of bypassed. Now, when we look at assessing risk due to quantum, everybody is talking about the probability of the risk occurring. So everybody is saying, it's highly improbable that you have a scalable quantum computer in 2 years. But, risk is not looked at like that. Risk is looked at as a product for probability and the impact associated with the risk. So if you look at all the critical infrastructure that India has, or for that matter, any nation, or for that matter, even if a bank or a regulator needs to look at it, let's say RBI is looking at the entire infrastructure that we have from a financial perspective, most of this infrastructure is online. So your risk exposure is equal to probability, which is very small, but the risk impact is equal to the economy of the nation. So what is your risk exposure? It's extremely high. So I want to point out that our way of looking at this problem has been extremely myopic. It has always been fixed on probability and how fast we will get a quantum scalable quantum computer. That is one point. The second point is already the number of qubits that we are seeing has surpassed any predictions made in the past on the number of qubits that we will see in 2024. So both of these factors are actually pointing to something very different from what the technologists have been telling you. By the way, I'm also a technologist, so, sort of just wearing the other hat right now. So coming back to this, what is the problem? And I think I don't want to elaborate too much on this because many people before I spoke have already talked about it, that, RSA is no longer secure, most hash functions are not secure if you have a scalable quantum computer. And quantum network opens up a completely new era of quantum security, right? And again, I would like to point out that, when I talk to some people from the traditional cryptography space, they look at PQC and they say, oh, post-quantum cryptography is something which is non-quantum because these are actually classical algorithms that we are using to solve a quantum security problem. That fact is correct. But then they look at QKD and say, this is a quantum solution. So this is quantum and this is non-quantum. And therefore, it should be treated differently. But that's not true, because if you look at any enterprise or any department, for example, who wants to become secure, and let's take banks as an example. Let's say a bank wants to get secure. If they want to look at their security architecture from today till into the future, they will have to take an approach which is a combination of multiple technologies. It is not going to be, oh, I will go for PQC or I will go for QKD. It is not going to be like that. It is going to be a combination of these technologies, and the combination will change over a period of time as cost implications and technology advancements come into the picture. So a 10-year, if somebody comes up with a 10-year plan which looks static, it's rubbish, right? Because the technology is advancing at such a fast rate. And if somebody says, QKD is the solution for your problems, that is also completely wrong. QKD is a partial solution for all your problems. If somebody says PQC is just the solution for all your problems, that's also completely wrong. So I think we need to take this view, which is very important, and look at the aspect of how actually solutions are going to be deployed. And that cannot be deferred very far into the future, because all of this exercise takes a lot of time. An example is, when we talked about Y2K, right? Familiar with Y2K? People as old as me or older would understand that. Y2K was a huge exercise to move the entire software base across the world to gear up for the year 2000, right? And that was just a field change. When we look at cryptography and the impact that we need to, what needs to be done to make a system secure, we are actually talking about a much larger ecosystem that needs to be addressed, right? So we call it, in the quantum community, we call it as Y2Q, the day when everybody needs to move to quantum secure, right? And when we look at that, you have to see that we are talking about data storage, data at rest, transient data, data in the cache, intra-process and inter-process communication. Inside your box, there is communication happening between different processes. That needs to be secured. So your operating system needs to be secured. Data sharing, data in flight, network elements, compute elements, OS and firmware, applications, and of course, different kinds of software applications all need to be addressed. So it's a very, very big problem, and it needs to be solved with a very coordinated effort across the nation. So if there are cybersecurity folks out here, you know that whatever I'm representing here is true for cybersecurity. So when you transition your existing algorithms to new systems, this problem becomes very, very complex because of all these various layers that are involved. So I'm jumping through the definitions of QKD, PQC. I assume that all of you know that. Post-quantum cryptography is algorithms which are quantum secure or are expected to be quantum secure. There are some algorithms that have been recommended by NIST, which is the National Institutes of Standard and Technology in the US. Most of the world is working with NIST right now, treating them as the de facto standard body for PQC. So that is PQC. QKD, you've already heard a lot of, lot of QKD presentations in the morning. But if I want to make the solution or the problem area even more complex, I want to let you know that even quantum sensing and IoT devices, all of them will have to transition. A lot of embedded systems, they have to transition to post-quantum secure environments. If somebody tells you, oh, but that can be taken care of later, I want to remind you that most of the most critical area where embedded devices are very critical is in the healthcare sector. So anything that can be hacked in that space has to be hardened and actually made quantum secure as early as possible. This is what the quantum security ecosystem looks like. This is not a simple thing, right? It's not like, one entity you want to talk about. So at the center of it, it has to be driven by the government. If you look at the US White House has issued instructions on the timelines for the government offices to actually conform to post-quantum secure environments. And then they've created guidelines or timelines for the entities that work with the government, so the government contractors, right? And then, of course, the rest of the nation needs to follow. So it has to be driven by the government. Of course, defense has a very strong role to play in it. Quantum security research and standardization, all the researchers who are working in this space, privacy and digital identity borders, those areas have to be addressed because there is an overlap between privacy and security, and understanding the privacy implications as your security paradigms change, that needs to be understood. Critical infrastructure security, so banking is critical infrastructure, energy is critical infrastructure, all your utilities, they are critical infrastructure, your roads infrastructure is critical infrastructure for the nation. You cripple any one of these and the nation comes to a stop, right? So I think all of those areas have to work together. Then you need security testing infrastructure setup. You need a provision for training people. How many quantum security experts exist in India today? I mean, I think I meet them in every meeting like this that happens. That's it. Maybe a couple of hundred more, right? So, and how many people would be needed to do a Y2Q, very similar to a Y2K over the next 5 to 10 years? We're talking about lakhs of people because we don't just need to serve our nation. Most of the world's data center administration and infrastructure is managed by Indian system integrators. So actually we need, if we want to leverage the economic opportunity here, apart from keeping our own nation secure, we also have to build the skills for quantum security on a very, very large scale. So here's the approach that we recommend. We recommend that the approach has to be control and implement. So there are very critical areas where maybe the government works very closely, some of the defense departments, etc., where things are controlled and implemented. That is their domain. But then on the other hand, there are a lot of opportunities for guide and enable, right? And regulate and enable. So regulators need to come into the conversation. In all of these meetings that we are seeing happening, how many times are the regulators present? We have to make sure that we are, getting more regulators involved in the conversation so that wherever the heavily regulated industries, banking is very heavily regulated, insurance is regulated, pharmaceutical is regulated, healthcare is regulated, all of these important industries which are critical infrastructure, most of them are regulated, and therefore having the regulators on board is extremely critical for these conversations. And of course, some of the recommendations that we've already made in various forums, but very importantly, we believe that there is a need to set timelines and guidance for transition to quantum secure state for critical infrastructure and then for the rest of the nation. We recently, as part of QETCI, what have we been doing? So we've created a white paper on approach for quantum security. We've shared with multiple stakeholders, Ministry of Defense, NCSC, Cybersecurity Coordinator, Ministry of Finance, Niti Aayog, Principal Scientific Advisor Office, etc., and some things are moving. We also launched a Center for Quantum Security in partnership with the C.R. Rao Institute during the National Quantum Science and Technology Symposium. In this Center for Quantum Security, we want to focus on skill building and for testing for quantum security. So these are the two areas that we are focusing on. We are also identifying best practices from across the world and contributing to quantum security efforts internationally as well. So I'm on the Global Futures Council for Quantum at the World Economic Forum. I'm also on the steering committee for the Quantum Security Initiative at the World Economic Forum, and have been a contributing member to many of their reports which sort of outline the transition to a post-quantum secure environment. And call for action for various entities here is that if this is a topic of your interest, please reach out to us, become a member, and join the Quantum Security Center and Forum, where we are moving ahead with this. Remember that when we talk about we are a non-commercial entity, most of the people who associate with us, we try and look at the value that we add to them. So if you are in you are working in this ecosystem, we want to work to make sure that you are successful in what you are doing. That is our primary job, right? Of course, and then of course we make policy recommendations and so on and so forth. This Center for Quantum Security and Forum, the aim is to build a stronger quantum security ecosystem in India. And we are interfacing with industry and government agencies. And we're also creating a community. And then we are, the first workshop that we are doing is on the 14th and 15th of March. It will come online soon. I'm just informing you in advance. This is a 2-day workshop at suitable depth. We'll be covering different aspects of quantum security, and people who are interested in participating can, sort of just follow us on LinkedIn, and you will get the update when this is planned. And our aim is to fast-track quantum security measures and implementations across the nation, right? And with that, I will, this is something that I created a little while ago. It is probably a little out of date, but you have QNO Labs here. We also have, QU Labs is not mentioned here, but that's an Indian company which is focusing on some quantum security products as well, and there are other entities. But there's a lot of companies across the world that are focusing on this. So that's an important thing to understand. A lot of efforts happening through international agencies as well. And we are tuned in, plugged into all of those efforts so that we can also bring the best of what's happening elsewhere to our member companies and member entities. Individuals can be members as well. And also, that sort of figures when we make recommendations to the government and so on. This is just a representation of transitioning to a quantum secure economy report by WEF, and they have given a very structured way of how this transition can happen. I was part of this report, so I thought I'll mention it here in case this is interesting reading for some of you. That's it from my side. Thank you. I think I was within the 15-minute limit. I should get a prize for that one. Thank you.
Ma'am, we'll certainly give you a memento from our side as a token of appreciation and thanks. So, ladies and gentlemen, that was Ms. Reena Dayal, founder and CEO, QETCI, that is Quantum Ecosystems and Technology Council of India. And now may I invite Dr. Manjunath RV, and before inviting you, I'll share a few things about you. Dr. Manjunath RV is a PhD from TU Delft, Netherlands. He is the Vice President, Quantum Hardware and Research in QPI AI, developing a full-stack quantum computer and integrating quantum computing and AI to offer solutions to areas like manufacturing, industrial, transportation, finance, etc. So, it's over to Dr. Manjunath RV.
Yeah, hello, thank you for the opportunity. We're from QPI AI. We are building full stack quantum computer, mainly focusing on building our first generation 25 qubit, and then we scale it up to 300 qubits. Today in this talk, I want to present about devices that are used in quantum technologies, both in the quantum computing sector and in the quantum communication sector, and what are the challenges that that perceive in while developing these technologies. So I will cover these topics like various qubit technologies and what is the most reliable right now and going forward, the reliability of these qubits. This is within the quantum computing domain. Then in terms of quantum communication, cover some device aspect in the photon sources and detectors. So as you know, quantum computing is one of the key sector, new sector where high performance computing can be accelerated, and it's a new paradigm of computing itself. For example, in the classical you have 0 and 1 state, but in quantum it can be between 0 and 1 state, so that's where we form the qubits. And with reference to how we are going forward in the next 5 to 10 years is that we are in the age now in the noisy era, like 100 to 200 to 300 qubits, and then we move towards the fault tolerant where we can have every operation can be error free. Okay, so that is where these are, and that is why quantum will be the next generation, like a supercomputing system, and we would see in the next 3 to 5 years that this will be part of all the data centers in the world. So when we were building a quantum computer, right, so how the qubits have to behave, right? So there is a 5 criteria that states that building a quantum computer must have any like qubit technologies, whether it can be trapped ion or semiconducting based, superconducting based. If they follow these 5 criteria, then we can go towards building a practical quantum computer using this. So the first one should be that all the qubits must be well characterized, and it must be scalable. It's not like we just measure one or few qubits, but we need to have a scalable system in order to make a quantum computer. Qubits as such must be initialized to their ground state. So there should be a capability of this to be in the ground state, because you cannot do operations when it's in the higher energy levels or higher states. And third aspect is long coherence time. Okay, so this is the definition that coherence time is that the time like we can do the operation without the quantum state dying. Okay, so we need to focus on technologies that can give us long coherence time, but also it must be scalable, and the other aspect is having all the universal gate set that can be defined, operated, and processed in this quantum computing system. And each individual qubit must be properly measured, and it can be tuned individually. So these are the criteria given by DiVincenzo where we can build towards practical quantum computer. So that's why like any qubit system that you see, like it needs to have these kind of criteria to make it, as a candidate for a practical quantum computer. So with reference to how the technologies are going through within the landscape over the last 5 years and coming forward, okay, so the top right hand side is where the best performance is. That is where you have the fastest gate speed, okay, and you have highest, the error is very less, that is 10 to the power minus 6. So these are the error rates that seems to be for both 1 qubit and 2 qubit. This is from the gate-based quantum computing. And if you see across the whole aspects, right, so there are various technologies that are being added in the ages, coming from silicon mass, quantum dots, neutral atom based qubits, trapped ion based qubits, but most of it have their pros and cons, and one of the key platform that goes towards making a very good quantum computer is a superconducting qubit, and that is very scalable. That's why many of the companies have built these kind of scalable infrastructure, but still it has several drawbacks or several challenges, which I'll tell you that goes into the device manufacturing itself. So that is where the devices for quantum computing, it's very important that it's a device behavior that determines all these one of the operation, along with the environment where the qubits are kept. So superconducting qubits, so basically they are one of the first, most scalable qubit that has been made. So they mainly consist of superconducting electronic circuits. So these are like LC oscillators, that's what forms the qubit system, but where the L component is replaced by a special type of inductor, nonlinear inductor called as Josephson junction, and that forms your qubit system. And to interact with this qubit system, you use these superconducting microwave resonators to drive the qubit to excited states, and then also to read out the states of the after the operations. So this is one of the, so you can see that it's like a chip scale based system, qubit quantum processor, where you can use standard semiconductor fabrication tools to manufacture these qubits. And that is one way that, that's why it's although it doesn't follow the CMOS landscape how to build, but this requires special type of manufacturing techniques. So as a manufacturing perspective, you see that this is a very doable technology, but still there are a lot of challenges to make it a scalable system. Okay, so one of the key aspect, as I mentioned, right, if you see with respect to the process flow, manufacturing process flow, the qubit system, you start with the silicon substrate itself. You make those microwave resonators. That's the first part of the qubit system. You make those resonators, and the second part, which is designed for various capacitance, various qubit frequencies, and also reading out the resonators are designed lambda by 4 or lambda by 2 to interact with qubits in this. The second part, the most important part, is making this nonlinear junction, which is a nonlinear inductor, which is called as Josephson junction. So here the key aspect is that this doesn't go into specific tool sets. Okay, it requires a very specialized process. So here you do something called as shadow evaporation, where superconducting aluminum is first deposited on one angle, and then it is oxidized in the chamber itself to form a thin layer of aluminum oxide, and then later you have on the other direction to place the other part of the aluminum metal layer to form a Josephson junction. So this Josephson is very key. So as you see that, like for example, when you make transistors in CMOS process, you have like 10 metal layers, and you can do transistor where millions of transistor and very repeatable as it. But here, if you see, right, so this is a what I call very random process, and because of this randomness of this process, the yield as such is quite low, and that is where it is one of the drawbacks, as I was telling, in the manufacturing process. You need to get the manufacturing so accurate that you can make the perfect junctions as per the design parameters. So as I said, so the first part is the superconducting RF circuits. So this can be done with standard, UV lithography. You don't need to go to E-beam based lithography systems. And then after that, you form this Josephson junction. So this is in the order of 60 to 180 nanometer. That's from the key element. So basically, those edge patterns in the first half, you can be 100% sure that they will follow the design requirement with enough tolerances. But on the right side, the Josephson junction is where most of the manufacturing process yield comes really low. So from all the way from 80%, it can come to 20%. So this is the key element, and that needs to be well monitored, and this to make this system very well. Okay, so this is one coming from the device perspective for manufacturing these qubits. Along with these qubits, along with these aspects, right, with respect to making the junctions, there are other aspects that we need to make within the chip. It's very different from how you make CMOS chips. You need to have this kind of air bridges because we use RF based microwave lines. So if there are interconnections, they cannot get shorted. So use something like this air bridge based technologies to have this ground signal line pass through the bottom lines, which again interconnects to various qubits. In that way, using this, we can make the chips smaller. So for example, a single the single transport qubit will be around 400 like 200 microns. So we can only fit certain aspects of qubits within the space. So we need to use several different techniques in the manufacturing to have various like 2.5D integration, or even in the last one, which is called through silicon vias, where the wirings are taken through the substrate, and that makes your coax cable. So these are some of the techniques that are coming, so that we are not limited by the space in making large scale qubit systems. So various aspect when doing manufacturing of these devices. Okay, so as I said that common CMOS line cannot take this load. You cannot like as you do analog and digital processor, design these and you give it for TSMC or Samsung, you can get the fab. This requires very specialized facilities to make these qubit-based systems. Okay, so because as I said, the metal layer is not like the generic aluminum or copper that we use it for various quantum processor, but CMOS processors. So here we need to have very specific tool sets that are used. Although these tools are used for CMOS, but very specific for superconducting processor. And the final one is the Josephson junction fabrication. So that is a key device, to make good qubits. And along doing all these process, we need to take care of a lot of things in order to achieve two critical criteria. One is long coherence time, one is the high fidelity operations. So these two are determined by how this processing go within these environment. Okay, so an ideal system, I would say, like after working for so long in this, so would be like all this processing happens in a vacuum where it does not have any any exposure to moisture or air. The moment you have moisture or air, there is oxide formation on the chips, and because of that itself brings down the coherence time a lot. So that's why we have to with the available facility, we try to make it as yield, increase the yield, so that we make better qubits. So this is one of the key aspects in device manufacturing. So you can see how a certain quantum chip looks like. So it's definitely not similar like how you see your CMOS chips, analog or digital chips. You have a lot of these lines. So these are RF microwave resonators, and at the middle you have certain dots which you can see that forms the qubit. This is a 17 qubit quantum processor by ETH Zurich, which has been done. So if you see, just to get this one processor right at the right design parameters, right measurement parameters, they would have it could have been gone through 1 year of cycle. So this is also one aspect, that when we are making quantum chips for building quantum computers, we have a lot of these cycles of iteration until to get a stable thing. Still the yield is not high with respect to this, but having own facilities, or making sure that the process requirement goes up, this happens. The other thing is, I want to say, this is a planar device. So you can see that as the number of qubits increases, the planar device width increases, right? So for a 100 qubit system, you need like 200 RF lines for driving and flux control. So you can imagine this will be whole wafer size of the chip. That's why different techniques like 3D integration through silicon vias and air bridges are required to make a miniaturized chip, but still having the high performance. So this is a growing field, and I think in the future that slowly some fabs might open up, but as of now, it's all a very research fab. Across India also, we have only 2 research labs that can make few qubit systems, but not a large scale one. Then other aspects about what I mentioned about how the decoherence time is affected by the device. So the ideal device, as I mentioned, needs to have long decoherence time. The ideal thing would be having 1 milliseconds that can result to doing more than a lakh gate operations. But right now we are limited by the coherence time, and many aspects come into picture. That is, as the impurities on this part of the chips, that is the Josephson junction part, and then oxide formation. And the other aspect is also any radiations also affect the performance of the qubit, so it must be well shielded. So these are some of the manufacturing aspects that needs to be improved, and to have very good qubit systems. And after the qubit is manufactured, it is placed in in the dilution refrigerator that we have. So basically, this dilution refrigerator would connect the room temperature electronics, that is basically RF electronics, to the quantum chip system, which is shielded in the mu metal base chambers at the bottom, where you can reach 10 millikelvin, that is -273. So this is a closed loop helium cycle, closed loop helium 3 cycle that is done first to 4K, and then you have different stages that can go to 10 millik. And there are the lines, as I said, right, 100 qubit system requires 200 lines. So right now you have to fan out these lines through superconducting cables all the way from bottom of the 10 millik holders till the aspects to the room temperature. So that's why you would see any quantum computing system, you have bunch of cables that run from room temperature to the cryogenics. And yes, more than I would say the chip aspects, the wiring aspects also come into picture while determining coherence. And these are some of the different technologies that are in place. So we can make larger qubit system, go to 1000 qubit system by incorporating these. So these are still in research phases, but I think once we have certain aspects of this, we will have a better qubit system. Coming to other aspects on quantum communication devices. So both state preparation and measurements, we have these two main QKDs that are based. What are the devices that go into this? So DVQKD and CVQKD based system. DVQKD uses the single photon detection based mechanism, whereas CV use coherent based. And if you see that DVQKD requires dark fiber, but it has a low secret key rates, but it can go for large distances. Similarly, in the CV, we can go. It has high secret key rates, but the distance is limited. And performance parameter, as you know, as I mentioned, so single photon detection is one of the key device that can help us to reach longer distances, and that again, although it has secure key rate is less, but we can go for longer distance. But with other, this is one of the device, that aspect that can take very less distance, but which needs to be at the device level, needs to be improved. In terms of cost parameters, so we have very key aspects which we take care while building these systems. So you can see that most of the costs go for these detection based systems and also the optics modules, but with reference to the laser based system, these are standard lasers that can be manufactured, but if you want specialized lasers, we need to again tune the manufacturing process. But high cost is where it comes in the detection side using single photon detector. With aspects, yeah, I mean, this is some of the standard laser based system, but again, as I mentioned, these are all not standard technologies that can be made. It needs specialized foundries to make these kind of laser sources. This is a DFB laser source. It uses heterostructures, different heterostructures that are placed, and then you have these gratings that are made. So if you want to manufacture these devices, it is a huge task. So that's why like specialized foundries are required to make devices that will be helping in quantum communication also. So these are some of the aspects of how the process for this one is there. Then coming to the other key device which we see, which is the single photon detector. This is a superconducting based single photon detector that can achieve greater than 90% of detection efficiency. Again, the manufacture process is simple, as you can see, but still the complication arise in getting the specialized detector specialized for both telecom wavelength and for free space wavelength. So this is both tuning the optical cavity below the devices. This is the final chip that will be there, and these are some of the chip that we have developed at IISc. So this is mainly nanowire based, so superconducting single photon detector. Currently we are in the phase of testing the benchmarking the detection efficiency, the dark count rate, and this is again as I said, nanowire, so you cannot do with standard lithography. You need specialized E-beam lithography, and that certain things we can be done at the facility, but we have huge problem of yield again here. So again, specialty foundries for devices for these kind of needs to be explored. Yeah. And the detection system would be in a cryostat where it can be housed. Finally, just a few things on the future aspects where devices can be key, for making QKD systems, right? So we go towards photonic-based integrated circuit-based QKD. So photonics, integrated photonics is already used in various domains like transceivers, making the photonics chip for gigahertz rate transceivers. So maybe some of the knowledge from that can be used for building these kind of photonic integrated circuits for QKD system. So some of the research work that been already done where although the laser is off chip, the detector is off chip, you can have the components for the modulators, and polarizers all part of the photonics chip itself. So this is a growing field. I think this can help in miniaturing the QKD system. This is one QKD system, but not based on silicon substrate, very specialized indium phosphide substrate again. So where the key was even to integrate the lasers on chip along with the modulators. So these are some of the key aspects that are going on in the world in terms of device technologies for both quantum computing and QKD. And I think for focusing on miniaturization, higher quality, that is what it is. And again, we have to rely on specialist units for fabrication, but it will be great that if we can, as a center to the NQM or this one, have some specialized facility that can help us be ahead in this in the quantum domain for the manufacturing of the devices. Yeah, thank you.
Thank you, Dr. Manjunath R. Venkateshji. And now, ladies and gentlemen, we are joined by Dr. Matthew Kempegner from United States. To tell you about Dr. Matthew, he is Senior Principal Engineer and Cryptographer for Amazon Web Services. He oversees the design and analysis of cryptographic solutions across Amazon Web Services. He is a member of the Etsy Security Algorithms Group experts and chairman of Etsy Cyber's Quantum Safe Cryptography Group. So we have with us Dr. Matthew Kempegner. Welcome to this session, sir.
Can you hear me? Hopefully you can hear me. I will start. So thank you. I want to thank the organizers and the program committee for the opportunity to speak today. Matt Campagna from Amazon Web Services and chair of the Etsy TC Cyber Quantum Safe Cryptography Working Group. So I'm going to provide a brief background on the Etsy TC Cyber QSC Working Group, basic facts about the group today, and then highlight some of the published recommendations and standards, as well as the current set of work items that we're working on. And finally, I'll explain how to join the working group, participate in shaping the EU and global standards for quantum safe cryptography. The QSC working group started back with the first Etsy and the University of Waterloo Institute for Quantum Computing Quantum Safe Cryptography workshop in 2013. And this conference brought together members of academia, industry, and government to highlight the need to start working on quantum safe cryptography, and really made a call to action for governments and industry to start this process now, because we knew it was going to take 10 to 15 years to transition. Many of these participants were part of the migration away from RSA to elliptic curve cryptography. So this is a pretty pivotal event in that we included many government entities like NIST, NSA, the CSC, GCHQ, as well as industries, participants from Microsoft, BlackBerry, and many others. And the outcome of this workshop was a 2015 seminal paper on quantum safe cryptography and security, which roadmapped a lot of the technology that we were going to need, like these hybrid post-quantum key exchanges. I'll go into that in a little more detail, and how to adopt these to the protocols that we use today. And that started the Etsy Quantum Safe Working Group. NIST subsequently started their PQC standardization process, and that really allowed the Etsy QSC not to focus on the cryptographic primitives so much as what makes a good primitive, contributing to the NIST standardization process, how to use these primitives in existing protocols, how to use these post-quantum cryptographic schemes in concert with QKD, and really how to begin the migration in a variety of industry areas, primarily the industry areas of the participants of the working group. So as I mentioned, the organization as it is today, I'm the chair. We have two vice chairs, Philip LaFrance from ICERA and Dan G from the NCSC. Tony Barnett from Thales is the group's secretary, and our technical officer is Laura Porson from Etsy. Her role is to make sure we adhere to all the Etsy rules and procedures for standards developments. We meet 4 times a year, most of the time in Sophia Antipolis, which is in the south of France. We also meet with teleconferencing to make it convenient for participants' modular time zones to attend the meetings. We routinely have 30 to 40 participants that span academia, industry, and government, much like our initial QSC conference. We have a number of published technical recommendations, or sometimes we refer to these as TRs. The early ones were really around evaluation of the NIST proposed schemes and the suitability of them for adoption in different industry use cases. We produced early on a technical recommendation on quantum-safe virtual private networking that looked at a variety of technologies, including IPsec, TLS, SSH, and MACsec, and identified migration strategies that required updating of these standards. Many of these we continue to work on, not just within ETSI, but some of those members within the relative standards organization, and especially at Amazon, where we're using VPN technologies both internally for managing our networks, externally for how customers connect to our network, as well as internally just for our workforce. We produced a technical recommendation on migration strategies based on different use cases, and a technical recommendation to accompany NIST's stateful hash-based signature schemes, going into additional details of the complexity of managing state across distributed environments like cloud computing. We also published a standard on hybrid key establishment, which uses classical key establishment schemes like elliptic curve Diffie-Hellman with these new post-quantum schemes. The first draft was, or the first version of this standard was really focused on the ephemeral use case, where you're setting up a session for communication. It consists of two fundamentally different styles of concatenation, where you're doing both of these key establishment schemes in parallel without changing the communication pattern. You sort of augment the session with two public keys and two responses to those public keys, as well as a cascade method, which you can think of as a tunnel within a tunnel, as well as how to incorporate into that hybrid model pre-distributed keys or QKD keys. And this, like lots of standards, is accompanied with academic scientific publication of the security proofs that are really required for the adoption of standards. If you don't have good fundamental math or science behind the evidence that these are secure, it's a little too early for standardization. And that's part of the work that we're doing within ETSI. Our most recent technical recommendation is an examination of the unique challenges within the intelligent transport systems, vehicle to vehicle and vehicle to infrastructure, to adopt quantum safe solutions. They work on very limited bandwidth and shared bandwidth, and they're trying to process hundreds to thousands of messages per second. And the expansion required for post-quantum signatures or some quantum safe technique really adds to the complexity there. So the architecture needs to be reevaluated, and potential changes in how we're thinking about rolling out intelligent transport systems. We're also working on a few things that haven't published yet. Notably, we have two standards. One is an update to the quantum safe hybrid key exchange, which will incorporate the finalized versions of FIPS 203, which will be the ML-Chem, formerly known as the scheme Kyber. We're also incorporating into that sort of what we'll call CCA security model, being secure against chosen ciphertext attacks. And this, sort of enables additional applications of like using static keys versus just ephemeral communications. A second standard we're working on is quantum safe hybrid key exchanges with hidden access policies. And this is a technique that's being used today commercially within the financial industry, and we're looking to create an international standard around that use. Working on 4 additional recommendations. One, looking at the impact of quantum computing on the proof techniques that we use to reason about cryptography. As I said earlier, all our standards are most of our standards at least, are based on some academic evidence of correctness and security of these primitives before we put them into standards. A lot of those proof techniques are sort of reused from one scheme to another, and this is looking at reevaluating those proofs under the light of quantum computing. Deployment considerations for hybrid schemes beyond just key exchanges, looking at the migration issues that center around post-quantum signatures. taking a deeper look at the impact of quantum computing to asymmetric schemes like AES. There's this notion of Grover's algorithm and its impact for symmetric key schemes, and the realistic the ability to realize a quantum computer that can attack a 2 to the 128-bit system is quite a bit farther off than what we would expect for, let's say, a public key crypto algorithm. And finally, a framework for quantum safe migration. We've had earlier migration technical recommendations. This is more of a repeatable framework of teaching people how to examine their infrastructure and plan for that migration. We have one more QSC protocol inventory, which is a protocol inventory of where we have to upgrade these protocols to post-quantum. This is really an effort aligned with the GSMA's Post-Quantum Telecommunication Network Task Force. The effort takes a broad look across many industries, but it's really centered on telecommunication. Last year, I presented a mind map diagram of these standards, and this is a more carefully captured view of that work. And it's going to, in addition to sort of list out these standards, is really begin making mild recommendations on how to upgrade them to be quantum resistant. So hopefully I've motivated you to the point where you want to hear more. It brings me to a few closing slides on how to track, participate, and learn about the work at ETSI. So to track, the ETSI portal can be accessed by anyone. It's at etsy.org, and there's a members portal, but anybody can peruse what's there. And they can track work items, see by working group what the individual work items are, and see the meeting schedules. Members can register for these meetings, join email lists, and download these current work items to review and see, if you have comments, do they align with your industry needs? You can participate and express those industry needs and hopefully get the specifications that you need from ETSI. So I encourage you to view this portal and all the working groups at ETSI, but especially the Cyber QSC working group, and consider participating. As I said, if you want to participate, we have 4 meetings scheduled, including next week. All the meetings this year will be in Sophia Antipolis in France. We have one as I said, next week in June, September, and December. And ETSI meetings, members, they can attend remote or in person. So you don't need to get to Sophia Antipolis to be a full participant in ETSI QSC. And finally, you can learn more about the ETSI initiative and the broader role ETSI is playing within the standardization for quantum-resistant technology. We're having our 10th ETSI IQC QSC workshop in May. It's in Singapore, which is relatively speaking closer to New Delhi than I am to either of those places. You can find the registration link easy enough for searching for the 10th ETSI IQC Quantum Safe Cryptography Conference. If you do go, I look forward to seeing you in person. And I also hope to attend this event in person in future years. So that's what I have for you today. I want to thank you again and the program committee for the opportunity to speak and how you can reach me, especially if you're going to attend one of the ETSI meetings or our conference. Thank you.
Thank you so much, Dr. Matthew Kempegna, for joining in and speaking on quantum communication landscape. Thank you so much. Thank you. And now, ladies and gentlemen, we have with us Dr. Abhijit Mitra. Dr. Abhijit Mitra received his PhD from the Indian Institute of Technology, Delhi, under the funding of the British Telecom Fellowship. Dr. Mitra's experience has been in modeling and network planning for metro and core optical networks. He has led funded projects by DST, MIT, and DRDO in the capacity of principal investigator and co-principal investigator, and functioning as a collaborator in a project funded by the National Science Foundation, that is NSF USA. So now, Dr. Abhijit Mitra, please.
Right. So, hello, everyone. So we have had a long discussion on every available quantum technology, and so we have lived throughout the day in the quantum world. So now I'm asking you to come back to the classical world, the world where we live and breathe, right? So regarding first of all, I would like to thank the organizers for inviting me, and so in this talk, this is basically regarding how do you integrate the quantum technology with classical networks, right? That is something which we need to think about, right? And it's about time now that we take a step back and look at the things at a wider viewpoint. Okay, so yeah. So that's the classical world for you, right? Everything is, well organized, right? We have got, we are customers, right? We are having our nice iPhones or fiber to home, right? We are connected to the access network, right? And then, there's something called as Edge, which has now come up, that is primarily to address low latency services, right? And then you have got Metro and Core, right? So those things we all know, okay? So now, look, with the rise of number of subscribers and rise of the heterogeneity of applications, specifically high data rate applications, a lot of traffic is flowing from customer towards the Metro and the Core, okay? So a huge amount of volume is now, getting built up in those regions, right? Also, some of the customers, right, do need some access to some sensitive applications, okay? So now, looking at this entire ecosystem, you can see there are some color codes there written, like, with red dot it's like ultra high speed transmission. Then you have got, routers or white boxes in blue R notation. Then you have got, SDN, right? So all these technologies are well, researched and implemented as well in many of the telecom networks, right? So now the thing is that which parts do I need to provide high security, right? So high security will be there where, you have got a high amount of data volume riding, which is the Metro and the Core, right? So that is why in the figure you can see there, just above the Metro, there's a Q pointer written, right? And similarly in front of the Core, again there's a Q pointer written, okay? So those Q are the QKD, okay? That's where we would like to have QKDs securing the interfaces whenever there's a talking between the Metro data center and the Core data centers, for example, right? And then again, you'll have a QKD link between the Metro and the Edge. And of course, in the access as well, you'll have another quantum link, possibly to some of the customers who can afford it, okay? So now, this is the overall vision, okay? That is, you will have a programmable automated network which is well managed by quality of transmissions, okay? It's well managed from the management and orchestration point of view, right? And it has got well-defined APIs classically. Now, what about quantum? In quantum world, that's what we need to understand, okay? So now from an operator here, an operator needs to have a lot of checklists, okay? Why? Because there are some list of traditional and future applications which he has to honor, okay? And primarily they are driven by the service level agreements, okay? And then whatever upgrade that operator needs to do, it has to be from the perspective of minimizing the cost per bit, okay? So even if I am deploying any QKD equipment, I need to make sure that the equipment utilization is very well, okay? Otherwise, the cost per bit metric will be very high, right? So now, coming to this QKD, okay, it talks about, almost unconditional security, right? So there are multiple vendors approaching an operator, okay, that, okay, my device has a QBR and SKR with protocol, X, okay? And there's heterogeneity of vendors approaching an operator, right? So now an operator needs to think across this world, okay, how to deploy these equipments, right? And the majority of questions that operator needs to, answer is that, okay, I've got vendor 1, vendor 2, vendor 3. How do I choose these equipments and I deploy them in a very targeted manner, okay, so that I could maximize or minimize my cost per bit, okay. Also, I need to make sure that the capital expenditure does not, rise up, okay. That's the second thing. And the third thing is that I want to make the utilization of my optical fiber infrastructure which is already there on the ground, right? I don't want to incur any additional deployment of fibers as well. Okay, that's the mindset of an operator. Okay, so and the fourth is that he also needs to factor in that who will be the future customers. So all these questions an operator is going on in an operator's mind, frankly speaking, right? So these are some of the conundrums that an operator needs to look at. Okay. So now looking from this perspective, okay, let us move ahead in this talk, right? So we know that this is how typically an optical fiber is deployed within the ground. It has got a duct. Within the duct, you have got cables. Cables have got multiple fibers, right? And this is a finite space, okay? And given the rise in the traffic, which is about 30% data traffic a year, these cables will be filled up in next 10 years, okay? So when you come to an operator asking that, okay, give me a dark fiber for enabling QKD, okay, then the operator needs to find out, okay, where can I find these dark fibers? Because these dark fibers need, across what distance I need to provide QKD, okay? Maybe I can find dark fiber for shorter distance, but not for multiple hops, okay? That is something which we need to think about, right? So considering this, okay, that finding a dark fiber, okay, will be a bit difficult for future because an operator earns more revenue typically while catering, classical data over the fiber, right? That's why the optical fibers have been deployed for, okay? So considering that, okay, how can you integrate QKD into such a situation, right? And the problem also builds up more in the access network. Okay, so an operator needs to be also mindful of the cost because QKD equipments are also very expensive. Okay, right. So one possible solution that operators are now considering is to have QKD over multiband. Okay, as what Professor Ghosh also indicated, she has also talked about broadband quantum source, right? So basically, this is the idea that operators have been exploring in the access network. Okay, in the access, basically, we have got in an optical fiber, we have got all these bands available: S band, C band, L band, E band, O band, right? But right now we are just using the C band actually. Okay. So now in future, if the data traffic keeps on increasing with the rate which I've shown in the slide, maybe we need to increase our operation beyond the C band, okay? Maybe we have to use the L band wavelengths as well and the S band wavelengths as well. But then if you want to use the same single mode fiber and integrate the quantum channel, we have to integrate it over a wider spacing, okay? So here I have shown an O band, but it depends upon the distance because the detector's efficiency depends on which band you are operating, okay? So therefore, now there's an interesting question here that given the traffic size which I need to carry across metro or in the access network, how do I allocate the quantum channel and the classical channel so that enough isolation is maintained, right? And since in the access and the metro network, these channels keep on adding and dropping, okay? So therefore, the position needs to keep, I may need to keep on, recompute the position of the quantum channel so that no amount of crosstalk happens. The crosstalk minimizes, okay, and the crosstalk typically happens because the high amount of power of the classical data channels interact with the fiber, okay, and lead to your higher order nonlinear effects, okay. So this is one thing which we need to, be mindful of. Second thing is that one thing which Sunil sir also talked about is the how we can deploy the QKD devices, okay? And this is a classical kind of a hub and spoke kind of a situation, okay? Where you have an Alice which is generating, X amount of optical pulses in a given period of time. Then I have some active devices, okay, which are able to split the number of pulses into say 10:90 ratio at first, right? And then again I go through a 1:4 splitter. Okay, so like it's about like 1 out of the 4 photon get switched to the first branch, then to the second branch and to third branch, like that, right? And so that you keep on moving forward until you reach Bob. Okay, now the active one it can be a WDM switch, okay, which can be controlled by an external controller, and I can deviate the remaining 90% of the traffic in the first splitter all the way to the Bob 1, I can increase the key exchange rate for first Bob, right? While I can have the equal amount of active rate for Bob 2, Bob 3, Bob 4, okay? So basically, I can use a high data rate key generator at the Alice, okay? And I can have load key consumption at Bob 1, Bob 2, Bob 3, Bob 4, and it will be dedicated, or it will be based upon the demand required by each of the Bobs, okay? So these are some of the architectures which will also be developed in future, okay? And that's what as an operator I need to develop, okay? How to deploy, these QKD devices. Now further, in terms of IP layer, okay? So in IP, typically we use the IKE protocol, okay? And that is within the IPsec, okay? Which is the Internet Protocol Security, okay? So typically what happens in an IPsec is that it creates a tunnel between the source and destination, okay? And at the moment, it gives you two security association. One security association is for an inbound traffic, and another is for the outbound traffic, okay? But the keys that are created by the IKE are at much lower rate than typically that you can get from the QKD devices, okay? So the question is, how can I use the extra amount of key material that is generated by the QKD devices and combine it with the classical keys that you are seeing in the picture, okay, so that I can increase my SA table entries. If I am able to increase my SA table entries, then I can create multiple such tunnels between the source and destination at the IP layer, right? And I can toggle between these tunnels, so that way you can achieve much more higher security, okay, at the IP layer itself, okay? So this is one way of looking at the IP part of the integration of QKD. Now, as the next step, as an operator, as I said, an operator will be accessing multiple vendors, okay, vendor 1, vendor 2, vendor 3, each vendor will have different protocols, right? So ultimately, I need to manage all these protocols together, tie them up, and get an end-to-end key encryption, okay, to provide security as a service, okay? So basically what you are seeing in figure 6 is an SDN implementation of multi-vendor QKD, right? So basically you have the first part where QKD1 channel is there, okay? And this, if it's readable, so that's a QKD1 is a quantum channel, right? And then basically these channels are relayed up to the encryptor using the standard ETSI interfaces, okay? And then like this, these QKDs are created for each of these trusted nodes, okay? Then if I need to now do a kind of a key routing, then I need to first find out, the SDN controller, we need to find out all the trusted nodes, whether they have adequate key material or not. If they have, then what will happen is that it will form a kind of a key route where it is going to inject into the next key node the key ID of the key which it wants to use for encrypting using the trusted node key relay system, okay? So like this entire interplay happens, right, from source to destination, okay? Now if you look at figure 7, so if you look at the interfaces, okay, which are being used, so the SDN controller talks to the trusted node over netconf, which is again well-developed interface, right? The key is delivered to the destination using the HTTPS interface, okay, HTTPS protocol, and the key ID is pushed using standard Ethernet, okay? So all these interfaces, or all these southbound and northbound protocols, right, are well available, okay? So now an operator, whenever he would like to integrate such multi-vendor systems, he needs to develop a system similar to this, okay, so that it can facilitate integration of different protocols and different vendors, okay, onto its QKD network, right? Okay, so now moving forward towards the landscape of standardization, right? So basically till now what we have seen in this picture, okay, is that an operator, so this is one of the implementation where an operator is using netconf, HTTPS, okay, Ethernet, right? But then there can be many such implementations, okay? So how do you get a industry-wide consensus that, you know, some of these interfaces needs to be at the minimal available in each trusted node, okay? That's the first thing. And the other thing is that also how do you make sure that, you know, these trusted nodes are well authenticated, okay? So I'll go about through these points one by one, and this is kind of a good summary of, you know, what needs to be done basically. So first is the gaps in the protocols, okay? So currently, typically most of the hardwares, okay, are over BB84 or CVQKD, right? And in future, you know, there will be some new protocols. So as somebody said, okay, about twin field QKD as well, right? So each of these protocols will need development of some new components, okay? And again, these standards needs to be, you know, revamped, okay, and reevaluated to factor in these new requirements, okay? So again, the protocols and the QKD components will be driving some of the standardization activity, okay? Now coming to the QKD module, okay? So this is basically there to assess and certify the implementation of the security of the QKD modules, right? What are these mechanisms that are going to be making sure that, okay, a particular QKD device is actually providing you quantum security or not? What are the methods to do that, okay, for testing, right? So that is again, you know, will be part of the development standard, and a lot of work, as previous speaker has already looked into. So ETSI is doing a lot of work on that, okay, and as you can see here, ISO has, you know, part 1 and part 2 security requirements and test and evaluation methods, which you can have a look at, okay, to make sure that, okay, if you are manufacturing a trusted node, this is where you need to focus upon, right? And in terms of fiber network interoperability, so standards driven by ETSI and ITU are there, okay. Thus that there are three things which we need to look into. One is the performance, okay. So if I am an optical fiber network operator, I will need to also make sure that I can compare the outputs between vendor 1 and vendor 2 and make a cogent decision based on a given standard, okay. For example, if we talk about optical modules like SFP modules, you can always do a link budget analysis based on standards and say that, okay, you know, SFP from CNI is better than X or Y, whatever, right? So that's something which you need to focus upon, right? Second thing is that key delivery, as I said, okay, that this key delivery API security requirements need to be defined for different layers, okay. You have an encryption happening in the physical layer, which is the QKD itself, but then at the IP layer as well, you are using some key material. Then in the application layer, you have got TLS, okay, and that key material also needs to be factored in, okay, if you are providing end-to-end cross-layer securities, okay. So that thing needs to be focused upon. And last thing is the network control and management. So as I said in the previous diagram, when you are using an SDN approach, okay, so what is the minimal information that a vendor needs to provide to an operator so that he can enable SDN, okay, across different equipments, right? That is something, you know, which should be provided and standardized, right? Whether it's the northbound or southbound interfaces, they need to be standardized so that the operator can, you know, pick equipment X, Y, Z and then join them up to form a quantum network to his satisfaction, okay? So these are some of the landscape for standardization. Finally, I mean, this is the entire set of quantum technologies which you would like to have, okay, but I understand that not everything is possible, okay, but one thing is definitely required is novel key generator functions, okay. Why I'm saying this? Because typically the QKD bit rate is lower, okay, and the applications typically require AES encryption, 256 bits, okay, need to be constructed in minimal amount of time. So with low amount of key material delivered by QKD, you need better key generator functions to match those same encryption standards. That is required everywhere, okay. Second is new fibers are coming up, hollow core fiber, multi-core fiber. These fibers are being considered by an operator. Multi-band is another technology considered by an operator. So QKD needs to exist, okay, across these different fiber technologies. Okay, hollow core fiber seems to be very promising, but then the distances are very low because of higher losses. And then, of course, in terms of QKD core network, okay, this is kind of a satellite network, but then again it has got different orbits. Okay, LEO, MEO, GEO, and Professor R.P. Singh is going to talk a lot about why is it so difficult to implement this, so I will leave it to him. But the end thing here is, also there's HAPS have been talked about. From network operator's point of view, I will be utilizing services of HAPS to provide protection. Okay, suppose if a fiber link fails, say between Nasik and Surat, then I will be relying on a HAP provider. Okay, to at least keep on providing me those keys. Okay, so there is one scope of operation there. Okay, that's how we think about it. Okay, but then where I will leave this podium, thinking that if we can develop a good fiber-based QKD metro network with HAP at the moment, okay, that should be the first goal, right? And basically, fibers is something which we should be focusing on. Quantum repeaters is a technology which I am very personally very excited about, because that is going to allow me to use the fibers which are already there. Those fibers are there in the ground, right? And they are not very much easily accessible. So that is something which we should attempt, as to if these fiber networks are penetrating more and more towards the core network, then the requirement of deploying plenty of ground station reduces. And actually that should be the case, because ground stations cannot be deployed everywhere, right? So with that thought, I am going to leave this podium. So thank you.
Thank you, Dr. Abhijit Mitraji. And ladies and gentlemen, before we move forward, there's an announcement. Actually, somebody has left his or her luggage rather, at the registration counter. So if you want to collect, you can ask our organizers or officers out here. Thank you. And next, we have Professor R.P. Singh ji. Professor R.P. Singh ji is a faculty member in Atomic, Molecular and Optical Physics Division at Physical Research Laboratory, Ahmedabad. His areas of research include light scattering, phase singularities of light, nonlinear optics, quantum optics, and quantum information. Presently, he is engaged in experiments on high-dimensional entangled states, free space quantum communication, quantum imaging, and quantum radar. So, may I request Professor R.P. Singh to kindly speak on this.
Thank you for the introduction. And let me start with first thanking organizers to inviting me to second conclave as well. And second thing, what I will like to tell, that whatever I am presenting, it's a collective work. A lot of students, PDFs, and younger faculty colleagues, all of them contribute, and that's what I'm going to present before you. And I'm happy to see that Ayan is sitting there. After doing PhD from PRL and then postdoc at York, he has joined CDOT. So I'm really happy that he has come back to India and contributing to the work. So we have full-fledged quantum science and technology program, and we cover all the verticals of quantum technology at PRL. I will not go into detail. And my life has been made simpler, my work has been simpler by Sushil, Anirban, Joy, Soumya to start with. You will see the slides, you will realize that already they have talked about those things. Okay, so I will rush faster now. So CV and DV QKD, Soumya talked about. So you can do CV and DV both you can do. They are also prepare and measure and entanglement based. So I won't go into detail. He has talked in detail there. Then why do you do free space quantum communication? Ultimate aim, I think Sushil told us somebody, ultimate aim is going to satellite based quantum communication. So one can go for satellite based quantum communication. You can have trusted node as satellite as well as untrusted node. When you say untrusted node, you use you entangle photons. When you say trusted node, you use weak coherent pulses. And first thing, major challenge you come with when you are using satellite for communication, light is coming all the way 700 to 800, or if you are using MEO, then even further away, maybe 2000 kilometers, then you geo much farther. And then light has natural divergence. Even if you are using photons, they follow the mode, okay, spatial mode. So as it comes, it becomes larger, like they can be seen at larger. Sometimes here, sometimes there, sometimes there, okay. So it follows the mode. So you need larger aperture to collect that photon, very large, as you go away. So that's a major challenge. And unfortunately, till date, we don't have a single optical ground station which can receive even signal from LEO, low Earth orbit. So that is the status, present status in our country. We talk of satellite-based quantum communication, you hear, but till now we don't have a single optical ground station ready in India to collect signal from a LEO satellite, forget MEO or GEO. So that's the thing. So this is the entanglement distribution over 200 meters. That's what we did in PRL. Luckily, we had 2 buildings in the campus where I work nowadays, and they are 100 meters apart. So we wanted to show for 200 meters because that was the project by DST. So we reflected the light from one building and got to the same building terrace. So it made 200 meters. So that's non-line of sight we call it. Or standard, like you call it non-line of sight. It's not exactly in the sight because it gets reflected and come back. Then we use 35 meter also. On the same terrace there is wall, boundary wall. We put there a mirror and then collected that made 35 meters and we compared. So you will see the challenge here. You see the tower. This tower here you see. So we are keeping mirror. This is at another building, astronomy building. So when this March, April came, we were doing experiment, wind started blowing and this tower started moving around. So it was very difficult to collect the signal. We have to stop the experiment, then we got it fixed. You will see now they have fixed this and now it's much more sturdy, it doesn't vibrate. So when you go for this kind of platforms like drone or balloon, they just keep on moving around, or it's not a stable platform. Satellite also it's rotating. So you face these kind of challenges when you go for this free space thing. And then as Anirban told, I will show you. So that's what we do, 200 meters. We verified like entanglement, very nice Bell parameter. Joy has talked about how to find out the Bell parameter. So this is experimental line, middle one is like theoretical fit, and other 2 lines, upper end, they are 98% confidence interval. Points are experimental points, so very nice Bell parameter and good visibility you get. And this temporal filtering is very important, time synchronization and temporal filtering when you go for this QKD. So as you see, this around 200 meters, so this is 648 nanosecond delay. And exact delay is very important. If you off by even 1 second or even 0.5 nanosecond, you will not get this kind of counts and you will not get the good key rate. So that's very important, this temporal filtering, these kind of challenges are there. So I will not, so you get like key, yeah, no problem. So then again, this atmospheric parameters, they play a lot of great role as Anirban was pointing out. So we did at 2 days, 8th and 10th May, May only, yeah. So both days this extinction coefficient, you see megameter per inverse, that's how they define extinction coefficient in atmosphere. So both are different. So even smaller, like you see Bell parameter, quality of Bell parameter and loss even at 35 meter, because extinction coefficient was higher at 35 meter when we did the experiment. So it was poor compared to distance, it has like a smaller distance. So atmosphere affects the key rate, certainly, that's what we verified. Luckily in PRL we have a space and atmospheric research lab, and they can provide data, hourly data for this extinction coefficient aerosol concentration. So then you will see that our key rate, this is key rate, secure key rate, they follow the experimental like atmospheric parameters. So that's a very good thing. Good thing in the sense, even if you do this QKD we are doing because we are using light. So using that you are doing communication, quantum communication, quantum key distribution, and you can have atmospheric parameter as well. So you can do 2 things at the same time. Then this is entangled photon source, that's what we have made, and we have verified, that's what we are using, this design we are using. And we have verified this fidelity, very good fidelity, very near to the ideal one, 0.975 fidelity, and very robust, single counts quite robust. Okay, fine, but you are using here PPKDP crystal, this crystal in oven. Oven means you have to stabilize the temperature, 0.1 degree. Slight fluctuation in this creates problem to you. So, I don't know. So, something like they have put PPT, instead of PPT they have put PDF file, no problem, things are not coming. So what happens, as this temperature changes or mode hopping, wavelength changes, so ring size changes. So what we have done to avoid that, you see this perfect thing, so because of this wavelength change, this ring size will change, temperature will change, ring size will change. So you put this lens and hexagon, so you make perfect ring. Okay, this is perfect vertex we make. We have been working with vertex for a long time. So use the similar technique here, and we made the perfect ring. Once you make the perfect ring, even this fluctuation in this wavelength, it will remain, ring will remain same, and you can nicely couple entangled photons to the fiber. So it becomes robust against temperature fluctuation or wavelength fluctuation. So if you are taking to satellite or free space, so it's really good, very good source for that. It's coming now, yeah. So yeah, it's PPT file only. So that's what you see that. Here it's same, yeah, and here it's same. So that's what. So this you see this BB84 we talk of. This is the one of the most basic QKD protocol. You use 4 lasers. So these 4 lasers may not be same like parameters. Their wavelength, peak wavelength, or pulse width. All those parameters may be different, and because of those parameters, you can distinguish between those signals which are going. Okay, and that may lead to the information leakage. So you have to calculate that information leakage, and we have found a very good technique using cross correlation. We can find out the information leakage. This is mutual information between Alice and Eve. If they are perfectly correlated, okay, so this cross correlation at this point will be 1. Okay, cross correlation, perfect correlation 1. So information leakage to the Eve from Alice will be 0. You can see that. So that's what we calculate. It's not that difficult. Very experimental friendly technique. Earlier they were using some technique that was very cumbersome. This technique is very experimental friendly. Just you have to use instruments instead of calculating. So that's what you do. You see this plot of wavelength for 4 lasers. They are slightly different. So because of these differences in wavelength, you can do the information leakage. So this is 10 power minus 3 bit per pulse. Okay, it's per pulse. So you use giga pulses, 10 power 6 or 10 power 9 pulses if you use. So you can see the information leakage you will have. So when you do privacy amplification, these things you have to take into account. So you have to characterize your source properly when you are using for QKD. So same way, information leakage due to pulse width. Pulse widths are different. You can measure, devices are there, you can measure pulse width. Same way, you can calculate arrival time. So both all are different for 4 sources. So you can calculate information leakage. You can say like spatial mode, and because of this polarization, you can calculate for everything. You can account all the parameters and what will be the information leakage due to that polarization errors. You see very significant information leakage will be there. And you, when you do the privacy amplification, you take it. Again, like this is source side, but people use weak coherent pulses, and then it is based on mean photon number per pulse, photon number per pulse. So generally what you do, you use single detector, and in 1 second how many photons you have come, you can count, and how many pulses were there. That's how you can find out the mean photon number per pulse. So instead of that, what we did, we used 4 detectors. Okay, we have done the coincidences, we have measured, and we have utilized to find out in a rigorous way what will be the mean photon number per pulse. This is a poor man's technique. Let me tell you, if you have like good amount of money, you can buy photon number resolving detectors, and you can find out what is the mean photon number per pulse. But that's very costly setup. These are like 5 to 6 lakh. And anyway, you are going to use 4 detectors, these kind of detectors for BB84. So you have that resource. So why not to do the better characterization of mean photon number per pulse? So that's what we did. So you will see when mean photon number per pulse as increases, okay, and then error starts between these 2 techniques. If you are using just one detector, that's what you do. Generally, when you use one detector, this is the repetition rate, and this is the efficiency, transmittance, and this is the number. So this increases this, and then information leakage also you see at higher mean photon number, information leakage you see due to both the techniques you can calculate, because with one one detector, and when you are using coincidences 4 detectors. So this information leakage also you can see that you are not calculating right information leakage if you are using just one detector finding a mean photon number purpose. So that's what. Then detection side also you can do same thing, information leakage you can calculate. So if you do this, we have done like this lens. If you tilt, so this coupling between these detectors, that will change. Okay, this coupling between detectors, you will see that. So this coupling between detectors change. So when coupling is very good and when coupling is not good, you can calculate cross correlation same way, and you can see the information leakage again. So source side as well as detection side, you can characterize your system and see chances of information leakage. That's very important. This is major challenge. It's not only for free space, it's for fiber also, any quantum key distribution device. So that's what we have achieved. I will not go into that. Doing like this DST project, free space quantum communication, road to satellite quantum communication. That was the project for DST. So that's what we have done, and we are working on CVQKD as Soumya told. So this is already we have done, like this is published now. This is also published. So we have to start with start noise measurement. You will have to do if you want to have CVQKD. So free space continuous orbital quantum key distribution with discrete phases we have done. We have done with Gaussian modulation as well. That will also be out soon. And then we are trying in free space now in 200-meter channel. And we are working on looking at the effect of turbulence and key rate for CV as well as DV. And we are doing experimental simulation of satellite downlink and uplink. That's very important if you want to go for satellite based quantum communication, whether you will prefer uplink or downlink. So that experimental simulation is very important to decide. Then you always want to go for a protocol which will be more efficient. That's very important. Everybody needs higher key rate. So that's what we have done coincidence dissection protocol that gives higher key rate compared to BB84 and decoy state protocol for similar mean photon number purpose. I will not go into more detail because you are taking care of these coincidences. That's why you get higher key rate. You can see that this is coincidence detection protocol giving higher key rate, and we have done experiment also. This is for 200-meter field data. So you see that this is giving much higher key rate. And for security reasons, first we did only coincidence detection protocol, 4 lasers we are using, but later on we combine it with decoy state also. So now it is much more secure. We have verified the security, theoretical proof. Okay, that will be out soon. And now it is giving much higher key rate and secure enough. Okay, so that's what we have done. And this is the future plan. Okay. You can read out effect of turbulence, already I have told, and simulating uplink and downlink. And then we are writing this. We have done this device independent QKD. So ION is writing. ION is the first author in that work. And then entanglement swapping. That's what, because we have distributed entanglement for 200 meters. So we are working on entanglement swapping and teleportation now. And as I told, we have made perfect vertex that has made it robust entangled photon source. So same way we want to use vertex beam, pencil beam, and Gaussian cell model beam to state Gaussian cell model beam, because we have made these things in lab for robust and secure key distribution. Okay, and then one of the labs we are using to develop photonic quantum computing. That's all.
Thank you, sir. And now, ladies and gentlemen, we are joined by Dr. Nixon Patel from US. Dr. Nixon Patel is a technology innovator and entrepreneur, having experience of more than 30 years. He is the CEO of Q Labs, a mission-driven research lab to provide the world and India its first quantum internet to deliver reliable, high-quality, cost-effective, efficient, scalable, and secure quantum communication solutions with quantum internet platform and software stack. Dr. Nixon Patel, we welcome you in this session.
Thank you.
Thank
Am
you.
I audible?
Yeah, thank you, sir. Please.
Thank you. Yeah. So thanks for the introduction. I would like to start with thanking the organization for having me come back for second year in a row to share my insights. So today I'm going to speak on quantum internet, the next frontier in secure communications. So the quantum internet is a network connecting remote quantum devices through quantum links in synergy with classical internet, right? It's envisioned as the final stage of quantum revolution, opening fundamentally new ways that communications can happen, new ways computing and sensing and a lot of other things will happen. This phenomena has no counterpart in the classical networks, such as no cloning, quantum measurement, entanglement, and quantum teleportation, impose new challenging constraints on the network design, and specifically classical network functionalities such as classical information that can be safely read and copied is not possible. However, the assumption does not hold quantum internet. Consequently, there are various design challenges and require a major network paradigm shift, which we'll try to cover in today's talk. Here are some of the topics we'll be covering today. And quantum internet, right? What does it mean? Essentially, the vision of quantum internet is to connect quantum processors and enable quantum connectivity between multiple user groups, just like the way classical internet does today. It enables multiple quantum processors to intercommunicate, and there's plenty of differences with classical way of doing things. Primarily, the quantum internet will enable network users to perform very interesting applications that cannot be done with classical ones, right? So let's look at some of the nuances and differences, right? It's a classical way of doing things. We use classical light to encode information. There are qubits, such as single photons are used to encode information. There are amplifiers that boost signal as they decohere due to fiber losses. Because of no clone, it prevents amplifiers. Entanglement distribution is through quantum repeaters. It needs to be used to overcome some of these challenges. There's vulnerability and threat of eavesdropping and interception in classical world. And quantum, because the principle of quantum mechanics, there's enhanced security protocols such as QKD and QSDC, which you saw the whole day today. And there's a tough thing to support multi-dimensional data transfer once we see what's happening with the LLMs and Gen AI with quantum, with possibilities of using qubits and qubits. You have possibility to support high dimensional data. Also, so there is if you see the purple and the green or purple and the blue, the overlapping of classical internet protocol stack and the quantum internet protocol stack, there is no one-to-one mapping, right? Also, the quantum internet protocol stack cannot function independently of classical. We need almost more than 50-60% of the communications will be classical. QUIPS has a dense cross-layer dependence, it's showing here, and QUIPS must account for both virtual and physical connectivity. One of the key ingredient that drives or will drive the quantum networks is quantum entanglement, which is essentially the property of quantum mechanics that really distinguishes quantum systems from classical ones, right? And the fundamental entanglement states that we are going to focus today is the Bell state, which is quantum state of two qubits that are sitting in different processors. Let's say Alice and Bob here. And the Bell state is a state that reads ket 00 plus ket 11 or root 2, where each of these qubits sits in a particular quantum processor. Let us use a brief analogy here to understand what we mean by special property of these Bell states. When we correlate the zeros and ones with the states of a coin, that's the analogy we can use. Let's say heads for 0 and tails for 1, and in a special state, if Alice performs a measurement on her coin and obtains a head, then Bob too, when he later performs a measurement on his coin, he will also see a head. And this was what Einstein called spooky thing, right? Alice also gives you knowledge about outcome of the measurement of Bob's qubit, which is what is very fantastic. And we saw that last year's Nobel was awarded to Professors Aspect and Clauser and Zellinger on their work in that space. We also can take it to the next level in that why we need quantum internet, right? So basically, quantum internet, what we're talking about, essentially provides one of the main applications we saw whole day today is about the QKD, which essentially works for cryptography and security, where processes distribute shared keys and provide security guarantee, theoretical security guarantee based upon the laws of quantum mechanics, right? So instead of computational intractability in the classical world, which is the current way of securing things, quantum internet will enable more secure communication. Quantum internet also enables small processes to work together to solve very hard problems that classical internet cannot, right? Also, it's much easier to build smaller processors and interconnect them, which essentially give a big virtual machine rather than try to create a monolith kind of a quantum computer. Another leading application for quantum internet is high resolution sensing, and we've seen some of those talked about in today's lectures. So this is a quick capture from my last year's slide about what quantum network architecture would look like. You see there are 5 different layers to stack: the physical, the link, the network, transport, and application, which is similar to what we have kind of abstracted in the classical world. And most of these is still developing as we speak, right? So there's a lot of work to be done to complete this stack. So let's talk about Bell state, right? Bell state, I mean, for a lot of you, it's obvious, but there are a lot of people in the audience, I suppose, who are not deeply familiar with it, is a 2-qubit with ket 00, ket 11 over root 2. And the idea is that if one of these qubits is with Alice and the other one is with Bob, and if Alice performs a Z basis, there are different bases of measurements, right? So if Alice performs a Z basis measurement on her qubit, the outcome of this measurement will be same outcome that Bob will see if he measures his qubit in the Z basis as well. So to be clear here, if Alice performs Z basis measurement and sees a 0, then Bob will see a 0. If Alice sees 1, Bob will see 1. So this is very important for distributing shared randomness across large distances. And there is the whole multipartite extension of this Bell state called the GZH, GHZ, which is like the Greenberger, Horn, Zillinger state, where the extension of Bell state is extended to multiple qubits. This is very useful network management and tomography tool, and it kind of describes multiple qubits. So instead of just having 2 qubits, we have n qubits, and you can see in that formula there, we have n qubits, and the state just reads like n zeros and n ones over root 2. And again, this is a very fundamental state for many different quantum protocols, which I think we will see coming along the line as quantum internet gets built. Now, another critical important aspect is quantum teleportation. So it's a way that we can transmit quantum information using quantum networks. Let's imagine that Alice and Bob share a Bell pair, which here we are calling end-to-end entanglement, depicted by the green circles. And let's suppose that Alice wants to send a qubit, the star thing, to Bob, which we show here. in the diagram. And now what happens is like Alice performs a particular type of operation with the qubit that she wants to send, the star qubit and her end of the entanglement. And once this is done, she will yield a couple of bits, as you see 0 and 1. And this information is shared with Bob to perform operation that he would be able to get back the star which was on Alice's side on his side. So this is the basic of what teleportation does. So this is a typical teleportation circuit. Circuit is a quantum circuit. Some of you are familiar, and some of you are not. So let me try to give more basic stuff. What's happening here? This the circuit that's performed by Alice and Bob is shown here. Let us say that Alice wants to send that state psi, which you see in the ket, the vertical and the forward-looking thing in between the psi, Greek alphabet psi. That represents the quantum state, and to Bob, and that both of them share a bell pair. Then Alice will perform a CNOT control by the qubit that she wants to send to Bob, targeting its end to the bell pair. Then she will apply a Hadamard gate. You see that H thing is the Hadamard gate to the qubit, and she wants to send followed by a measurement on a Z basis. You see that Z thing on the bottom of the A part, right? And Bob, which is depicted here with these parallel lines, receives those 2 bits and performs an X gate. If measurement of the value of the bit B is 1 and a Z, if the value of A is 1, once Bob is done with these 2 operations, the qubit that is started as it is in Bob's end is now in the Bob's end, and the bell pair becomes state psi here. So that's the kind of circuit this achieves what we talked about earlier in terms of teleportation. Let's now look at why quantum communication is so hard, right? For a fiber length L, the rate at which we see when we try to distribute entanglement between Alice and Bob, which is a key thing needed for quantum communication, decays exponentially for various factors, right, with the distance. Such strong attenuation in case of classical world is kind of mitigated through amplification of the signal, but due to no clone, we cannot do that in case of quantum communication. Right? So what do we do? So no cloning tells us that we cannot perform this amplification, and this needs a whole new approach, and there are whole new techniques, right from quantum error corrections to different techniques that some of them were mentioned today, but it's too much detail for a short 10-minute talk here. So also quantum repeater is one way of understanding how this can be mitigated, right? We solve this issue of exponential decrease with the distance with something called this repeater, right? That uses quantum memories to establish, which is also another very crucial thing that my company is doing, is to build a quantum memory, warm vapor rubidium base 87, and we may be the first in India, maybe one of the few in the world to deliver a quantum memory pretty soon. And so what it does is to help establish entanglement across large distances by placing the repeater in the middle of the path. You reduce that length, thing L, connecting Alice and Bob. We are going to assume that this repeater has 2 memories and 2 qubits in its registers, and it can use to generate entanglement with Alice and one with Bob. So first thing that the repeater would do essentially is to create bell state with Alice and store one of its end and one of its qubits in its register. Then it will do a similar thing with Bob and generate, and these 2 states are generated, but the repeater will perform a very special type of measurement to propagate this entanglement. It's called something called entanglement distillation, and then purification, distillation, and swap. This can help us to overcome the exponential decay, because the R that we have between Alice and Bob is now distributed between Alice and repeater and Bob, which actually deteriorates. There's some garbage there. E to the minus alpha to the power root to 1.5, right? And same on the other end of Bob's side. So that by distributing the breaking of the distance, we kind of reduce the decay. So we see quantum entanglement network, right? That what we saw was just between two nodes. Eventually, here we generalize by adding quantum repeaters in between various end nodes and switches, and which have access to memories and will allow us to establish communication between multiple end nodes. We can imagine that these repeaters are interconnected with lossy links, which you see that we can use to generate link level entanglement that we talked about, or link level bell pairs, which is the basis of communicating between different nodes. So there are the techniques we talked about, I think, entanglement distillation. Here, what we see is to start off with several bell pairs, those zigzaggy lines, that may not be perfect, right? So we essentially perform something called distillation operations with the goal that we end up with one bell pair that is has super high fidelity, so which is shown in the bottom thing. Here's a simple circuit that takes two bell pairs. A C0 gate operation is performed on both Alice's end and Bob's end, and then Alice and Bob measure the target pair, which is the bottom thing, and send the results to each other, and then they can decide whether they come up with a better quality pair than they had before. So that's what the distillation enables. Basically, we say classical communication probabilistically convert multiple noisy entangled pairs in a single strongly entangled pair, which we saw earlier with higher fidelity, and it helps determine. So important aspect here is to determine when and how to distill. If we have two pairs or three pairs or four pairs, and if we end up getting one or two of these pairs of similar high fidelity, then we are overdoing it. So how do we kind of know how much to distill, right? So that's very critical parameter in quantum engineering design for quantum networks. And whether to distill across single or multiple links, like, or jump. So there are different techniques, possibly with minimum end-to-end fidelity kind of a constraint, right? So here's a typical classical internet protocol stack. We are aware physical link, network, transport and application layer, and each of these have, say, the physical. We have the bits that go on the wire. On the link layer, we have these data transfer things happening. Network layer, the IP and routing protocols. Transport, we know for the last 50 years we use TCP, UDP, different protocols. In applications, we are supporting various email, HTTP, SMTP, HTTPS, WebRTC, all those different kind of protocols. So a similar thing is emerging or has to be finally built on the quantum internet protocol, right? Most of the things are in the physical layer. We know photons carry on the wire. Link layer, there are various things that we already built in our quantum network simulator that we have built. Network layer entanglement generation happens between end nodes. We talked some other things in the previous slide. This equivalent of TCP and UDP, I'm just putting something fantastical thing here, QTCP and QUDP, which is still to be built. And there are various applications. We have 30-odd QSTC, quantum secure direct communication protocols, and various other protocols like BB8 all can be put as application E91, 92. And we have put some of them in our quantum network simulator in the company.
Dr. Patel, if you allow me a humble request, actually we are already late by more than 1.5 hours. So if you could please wind up.
Okay, you want me to
really
wind up?
Sorry.
Fine.
Yeah, because I'm really sorry, but then.
Okay, so all right, and there are all these challenges and open questions, which and then there's a conclusion. So I get that. That's what you get to be at the end of the session. But yeah, so.
But I'm afraid we are already late by more than 1.5 hours. So in any case, we have to wind up. I'm really sorry for that, Jay.
I mean, that's you guys should have manage time better with other people. Right? Thank you. That's okay.
You,
so this is the conclusion, so people can read it. And thanks for giving the opportunity.
Thank you, sir. Thank you so very much for joining in. Any questions if you have? Any one of you, please. So may I now request Mr. Rakesh Desai, DDG Fixed Access, TEC, to kindly felicitate our speakers on the dais, please. Mr. Rakesh Desai will now felicitate Dr. Manjunath R. Venkateshi by presenting a memento. I request Mr. Rakesh Desai to kindly present a memento to Dr. Abhijit Mitra.
Thank you. It's easy, so it's mindful to give something beyond that.
And now Mr. Rakesh Desai will felicitate Dr. R.P. Singh by presenting a memento to him. Thank you, Mr. Desai, and we thank all our speakers. Thank you so very much. So that was session on quantum communication landscape, ladies and gentlemen. And with this, we wrap up our today's session. And as you all know, this second International Quantum Communication Conclave is a two-day event. So tomorrow, that is on 16th of February 2024, our second and final day of the conclave, will have sessions on quantum networks and post-quantum cryptography, standardization efforts towards quantum technologies, and emerging trends in quantum technologies. And after that, subsequently, we'll have a panel discussion on applications of quantum technologies, deployment perspective, and use cases. And I would like to share with you that tomorrow we'll start our first session at 9:30 a.m. So for now, it's thanks to all of you. Thank you so very much. Namaskar. Jai Hind.